Good morning to all of you. We have assembled here for the national workshop organized on electric aircraft and allied technologies, jointly organized by CSIR National Aerospace Laboratory, Design Division of the Aeronautical Society of India, and the Indian Institute of Space Science and Technology. Before we start the program, I request all of you to switch off your mobile phones till we conclude the program. I now request Shri Jitendra Jayadara, Director CSIR-NAL, to formally welcome the guests and the gathering.
Morning to all. Goyal sir, Suresh, Kota, Sunday, and all other distinguished people here as well as offline, as well as online on video. So it's a great initiative by 3 institutes from CSIR-NAL, Aeronautical Society India, and India's Institute of Space and Technology. Actually, in NL, we are currently running 4 programs. One is Hansa NG2 flying 2-seater flight. So why we took Hansa NG2 2-seater flight trainer is today with the growing demand of on this civil aviation market, there is an equal growing demand for the pilots. And what we found is there is a need of about 900 to 1,000 pilots per year to train. And India is having only capacity of about 250 pilots to train. About 750 pilots are getting trained outside. And there is a huge cost because their course is around 8 months and they charge not less than 20 lakhs or 25 lakhs for 8 months. And then further to that. So we took this initiative that India need a aircraft which can meet this flying trainers demand. So we have gone ahead with the Hansa NG and it's a very successful project. The cost of the aircraft is much lower than the imported cost, and we are almost at type certification. And I'm glad to tell you that about 80 LOIs are already there, and some commitments from Flying Training Club has also received. And 2 companies, BA, HL and MESCO, 3 companies have now come forward for fabrication. Now, if you say this, now there is a need by 2026 that flying training profile of commercial pilot licensing is getting upgraded into the overseas. Because even though today we make this avgas or MOGAS based trainer aircraft, the availability of fuel and then all other commercial things are too costly. And it's not very sustainable thing from the many other things, from the green energy now. So many of the foreign competitors have started making a electric aircraft for 2-seater flying trainer, which is the easiest way to move forward at the beginning. And if we take that, now they reduce that, it should be only 1 hour and half an hour result. Earlier there were 6 hours endurance and half an hour result. Now the CPL licensing thing itself has come 1 hour endurance and half an hour result. So we feel that that is the best way that our aircraft can be reduce some weight with the new requirement of commercial pilot licensing and convert Hansa into the electric aircraft. So that is what our thing. And for that, today I think all lot of people has come from different ways. Professor Sunday himself is there. So we will discuss whether we should go for battery technology or we should go for hybrid propulsion or we should go for fuel cell in that Hansa electric aircraft. That is the first easiest way where I am finding there is a demand and we today easily do by retro modifying our airframe. So that is what it is. Next, of course, we have a lot of other projects which are 19-seater, 70-seater and all that thing. But CSIR-NG will be the beginning to practically see what are the difficulties and put it into the market. That's what I feel. And apart from that, we have taken high altitude pseudo-satellite platforms where 22 kilometers it goes and stays for 90 days. There are also one the challenges are there, but it is purely electric. One example I will give about the two-seater trainer. Pistol is the company. They had a similar aircraft which was working on avgas and mogas and all. And they were converted within a year also the electric aircraft, which is having 1 hour endurance and 1.5 hour and half an hour reserve. And now flying clubs are finding in Europe and Germany, though the initial cost is higher, the maintenance and the fuel cost is getting recovered within 2.5 hours. So that is what is they are saying. So I feel today's discussion can concentrate on which type of hybrid propulsion for what aircraft. We have 3 classes of aircraft. I can tell from HP angle. We have a 750 HP, which is Hansa. There is a 1000 to 400 HP, which is SHP, which is SARS, and 4500 SHP, which is 70-seater. So these are the 3 classes of aircraft where these technologies can be think of going. We can go stepwise. That's what I feel. And should not attempt directly 1400 or 4500 and all. Stepwise 750 HP can be easily attempted. That's what I feel. So I will say welcome on this thing, and I will look forward for all the presentations and all other whatever sessions. Saraswati joining tomorrow, and we'll have a good panel discussion. Thank you very much.
Thank you, sir. I now request the Kota Katnarayana, Chairman, Examination of the Please on the lead of today's workshop.
Good morning to you all. Jana has already welcomed you, but I would like to welcome you once again on behalf of all the 3 organizations we have worked together. Basically, we have brought together the academia, R&D, and industry together, so that as a team we are going to execute this wonderful, I think, technology whereby India gets benefited 2 ways. One is we will have 0 emissions. Secondly, I think for decades and decades we have struggled to make gas turbine engines. I would still say we are not succeeding. We're still working on. Whereas electric propulsion, I do think we will have better success, and I have a feeling we will succeed. Okay? So for that, it's not just a motor or anything like that. We have to look through a number of disciplines, we have to bring them together and work together and make it happen. It will be a wonderful thing for us to do that. I've been discussing with our colleagues at Design Division, Suresh, Goel, Jadhav, and many are my colleagues. Dr. Pai is right here. Recently, Dr. Goel has introduced me to Sondya and his team. I've been talking to them. We thought this 2-day session it is not a seminar or anything, because we want to bring together people who have done some work. It is only Indian seminar. We have not brought anybody outside other than 1 or 2 people who have developed software for simulation and all, like Siemens and all. Our whole idea is look at where we are in India, where do we need to go, and what is the way to move forward. The other side, our first target is to modify a 2-seater. Fortunately, this is an aircraft designed developed in India, so we have everything about that aircraft. We should be able to. But simultaneously, we must work to see we will see the regional aircraft. I will give you the reason why I feel it is important here. Because world over the studies have shown that next 10 years, the propulsion technology, the electric propulsion technology, will be sufficient up to regional aircraft. Beyond that, it may take much longer. Fortunately, India is the biggest market for regional aircraft in the world. And we are also the 3rd largest market for the civil aviation. With all that together, it looks to be India must take the initiative. And this is the first, if I understand correctly, first workshop on electric aircraft and allied technology. So I'm very happy that all of you are here. It is more like understanding what is required, understanding each other's strengths, and how to move forward. I'm very happy here. We have good participation from academia. We have from Indian Institute of Science. We have from IIT Kharagpur, IIT Delhi, Gandhinagar, IIT BHU. Okay, we have good. We also have good startups joined here, and of course we have colleagues from ISRO, from DRDO, from CSIR, and from Aviation. All these people are come together. We have put a program whereby we look at aircraft to start with. Then we look at what are the utilities. It's not good enough you make an aircraft. Fuel, hydraulics, fuel, everything, all has to be changed to electrically driven. So we have a session on that. We look at the first step, what we call electric, so motor and power train. Okay, we are going to discuss on that. Next day, tomorrow, Saraswat is going to be here. He's going to talk about what is the government of India's vision in terms of, because India has started a hydrogen mission. And thanks to electric vehicles, what is happening and the PLI scheme, a lot of things are happening on the ground. We can build over that. And as long we do, we'll be able to do things that are required for the aircraft. And the energy management we are talking, fuel cells we are talking, then we'll have a discussion. It is an important discussion where we can sit together, discuss, analyze, and see what is the way forward. Okay? So I'm very, very happy that all of you are here, and few more people will join here. And I look forward to this session, this 2-day workshop, as something which will help us to move forward with the what you call hydrogen mission and the PLS scheme and the electric vehicle, ground vehicle. Industrial infrastructure is getting built in the country, and a lot of good work has happened in terms of all other systems. We need to build about that. I request my colleagues who have been in the nuclear system like Devakaran and others, and FCL system, friends from HAL to look at the electrical brakes and ECS system. I think Yogesh is here to look at that one. So they have done supplemental study, preliminary stage, but we can take forward and move forward. Unfortunately, today, NL has taken the lead in terms of civil aircraft. And so this is the right place where we are meeting, and we can look at 2 seats, we look at 19 seats, we look at 40 seats, we look at 17 seats. I have a feeling we can do all of them, but then the excellent technologies we need to develop. I hope this workshop will help us to move forward. Thank you very much, and welcome you all again.
Thank you, sir. Now we request our director to release the book of abstracts for this workshop. I request Dr. Kota Srinaran, Dr. P.N. Suresh, Dr. P.S. Goyal, Dr. B.R. Pai, and Dr. Aviation to join him on the dais. I now request Dr. Abhay Pashikar for the presentation of global scenario on electrical aircraft and technologies. Dr. Pashikar is with CSIR-NAL since 1993. He joined the Flight Mechanics and Controls Division (AAN) after a BTech honors degree in aeronautical engineering from IIT Kharagpur in 1991 and an ME in aerospace engineering from the Indian Institute of Science. Subsequently, he completed his PhD in aerospace engineering. Yes, sir.
We are not going to introduce any. Good morning to all the dignitaries, friends and colleagues. It is my pleasant duty to talk about the global scenarios for electric aircraft. So, firstly, on behalf of the organizing committee, I'd like to thank the Director NAL for his encouragement, the design division of the Aeronautical Society, and the Indian Institute of Space Science and Technology for coming together with us to host this particular event. So my talk will basically focus about what we see happening in the world and in the Indian context, what is relevant and possibly some strategies for the future. So if you look at India today, we already expect that air traffic in terms of the passengers will triple to about 520 million by 2037, another 15 years or so. And
traditionally, for a long time, almost more than 2 decades, Indian passenger traffic growth has been going, averaging close to about 10% year on year. Also, we expect that by 2038, we should have quadrupled the number of aircraft that are operating in the Indian airspace. What I've done here is I've tried to correlate what is the effect of the GDP growth as against where we are today and where we are likely to go. This is the underlying reasons why we expect this kind of a growth. And you can see here, India is somewhere here. This is a log scale here on the left-hand side. This is the number of seats available per capita on the y-axis, and you have GDP growth per capita or GDP per capita. And as you can see, China is somewhere here, and of course the developed countries are all out here. So there is a plateau here, but by the time we grow and reach that plateau, that is where all of this growth is going to come from. And so it is essentially the economic situation of the country which is going to drive this kind of a growth. And of course, there are other parameters which will result from this growth, but I will not talk much about it. So what is important is, as was mentioned before, India is already the third largest domestic aviation market in the world today, and it will become the third largest aviation market as well in the world. So that's the kind of growth that we are looking for, and that is the potential which is inherent in basic civil aviation itself in India. On the policy side, the government has essentially created three policies. One, as you all know, is the UDAN scheme, which is the regional connectivity scheme, which allows new routes to be created, new airports to be brought in, and thereby regional connectivity is enhanced between various city pairs, tier 1, tier 2, tier 3, and so on. They have also realized that the airline operators need local support in terms of financial services when they procure or lease aircraft. So there is already a move on to have what is known as the International Financial Services Centers in the GIFT City in India. And the government is pushing from the Civil Aviation Ministry a policy for bringing in more maintenance, repair, and overhaul in this country. So these are the three pillars from the policy perspective. And we at CSIR-NAL believe that the fourth pillar should be design, development, and manufacture of next generation of regional transport aircraft. So that will complete the kind of initiatives that we will be taken to be able to exploit or to be able to really enhance what is happening in the country. And when you look at various states, they already have dedicated policies in this aviation sector, and here I have listed two of them. And mind you, this is all coming from the Civil Aviation Ministry side. All of this information is from their point. Now let's move on a little bit to what is happening globally. We all know, and this is, I apologize if some of you have already seen this. This is a picture of what's happening on the climate front. You have the -1 degree circle here. You have 0 degree, which is the nominal temperatures throughout the world. Then you have the +1 degree here. So we will run this video from 1880s. Then you will see what happens. Please note what happens when the Industrial Revolution started, and subsequently when some of the big economies like China and India have taken off. You can now start seeing the effects of the Industrial Revolution, and subsequently after about 1980s, you will see the rise of the big economies, and you should then see its effect on the global temperatures. Right about right now, you will start seeing major Asian economies taking off. The result of all of that climate change. So clearly, climate change is a major concern as it should be, and we can see that human activity is essentially driving that climate change. And if you look at in terms of the worldwide scenario, in terms of the energy consumption, which is essentially driving the additional rise in the temperature, you will find that the transportation sector is very high, in fact, the highest among all the various sectors of the economy. And this is true worldwide. This is on the left hand side. And on the right hand side, the detrimental effects of that, the CO2 emissions which have emerged out of those activities, again, you will find that transportation leads across the decade in terms of the kind of pollution that is created due to all of those activities. Clearly, transportation has to be a focus when it comes to tackling climate change. Here is the breakup when you look at sector-wise in transportation, carbon dioxide emissions. So, of course, aviation is only 8%, and the large part of it, about 40%, little more than 40%, is passenger cars. So, clearly, there is aviation there, but that gives us a small window of opportunity to put our act together compared to, let's say, other modes of transportation. And what is important is it is becoming clear that, of course, passenger car or similar personal mobility vehicles are going to drive the change because they are the largest contributors and there will be a lot of pressures, environmental pressures to drive that change. And here is a schematic again on what it means for aviation. The important thing is actually in certain segments, when we look at 1500 kilometers and above, there is very little other than aviation which can support those kinds of distances. So that is where about 80% of these CO2 emissions will come from that kind of ranges. So definitely, just because we are only 8% of the total emission doesn't give us any leeway really, because some of the crucial economic aspects of any country is supported by aviation, especially the longer distances involved. And there has been tremendous growth in efficiency. There are about 80% more fuel efficient jet aircraft today than they were in the 1960s. You can see that infographic out there. But that doesn't, that's not enough. Clearly, that is not enough. And we need to do more. And of course, alternative fuels is probably the way to go here. So let's look at what could be a roadmap for the sustainable aviation in future. One is, of course, to continue improving the fuel efficiency. We now know, for example, that gas turbines can go almost as good as 60% efficient. We have proven that. But even that probably is not enough. The next level is to look for alternate sustainable fuels, different type of fuels, and then move on to more eco-friendly kind of systems, propulsion systems that. So among the candidates, as has been mentioned, of course we have solar, but that is typically efficiency-wise only suitable for small aircraft. And then you have at the bottom the sustainable aviation fuels or the advanced aviation biofuels. Already we see that there is some movement both by the Indian Air Force and SpiceJet in terms of testing their existing aircraft. Big advantage of the SAF is that it is possible in principle to use an existing aircraft to be able to exploit this fuel. So that's the big advantage. The initial upfront investment is only in terms of the fuel that we need. The other emerging technologies are clearly battery based on the one hand, and then we have fuel or hydrogen fuel based on the other hand. And each one of them has pros and cons. I'm sure this two-day workshop we will get to know more about those things. Just to highlight in terms of perspective where we are in terms of what needs to be done. So clearly the immediate need is to see how best we can exploit existing aircraft systems to be more eco-friendly and to develop other alternative fuel systems which are more efficient or less polluting in terms of emissions. This is an interesting graphic. If you look at in the automobile sector, I showed you that automobile sector is the largest contributor to emissions. If you take a distance of 500 kilometers and you decide to build a power plant for addressing that 500 kilometer distance. So this is a graphic that I picked up from the automobile review papers. And you will find on the left hand side traditional fuel diesel, of course. The center part is for compressed hydrogen at 700 bar as a fuel source. And then on the right hand side, we will have the lithium-ion battery as a typical representative of the battery systems. What you have is both the weight and volume. It gives you an idea of, for example, if you look at diesel, you have two weights there, one reflecting the weight of the system, that means the power plant. This is 43 kgs for this 500 kilometer range. You need an engine of that size, that weight, and the fuel itself in that would be typically about 30 kgs. Then, in terms of volume, you see 46 liters and 37 liters reflected in the first column there. And as you move to the next one, which is the other fuel, hydrogen, even if it's compressed at 700 bar, you find that both the weight and volume is dramatically different. Of course, clearly energy density is at play here, both volumetric as well as weight-wise. And then when you move on to the battery, you find that you need much bigger system. So clearly because of the energy density, and this obviously has a major impact on the size of the aircraft or any kind of system that you get around that. So this gives you a comparative idea of what will happen if you replace one fuel system with the other. Clearly, therefore, there is a need to see how best we can progress even this technological challenge that we have. What is not reflected here is other aspects. For example, when you look at refill time, it's very easy to refill a vehicle which is using diesel or any kind of other fuel. And so you can do it with hydrogen, but charging a battery, for example, takes its own time. So clearly, that aspect also cannot be ignored from a system perspective. And of course, most important is what is the cost to pay to build that system. So this is purely from the perspective of assuming you have a system, what its size, shape, volume will be, and its cost implication. It doesn't talk about how you get there, so we'll see a little bit later why that is also. So clearly, if we have a roadmap moving towards more electric, all electric aircraft, so one needs to keep in mind, firstly, typically, though we do use a lot of fossil fuel, but clearly in terms of internal combustion, efficiencies are in the range of 35%, gas turbines 45, maybe now touching 60% or more than that. And efficiency is clearly driving the move towards electric. But once you have the energy source, the electric powertrain is very efficient compared to the other. Of course, as mentioned, there is the benefit of reduced noise, reduced maintenance for the less moving parts involved, lower emissions, obviously, fuel source in many cases is different, it's not hydrocarbons, and as a consequence of all some of those points, more reliable. So this is what is essentially driving the move towards these kind of technologies. And when we look at the options that are available to us to gradually move towards this solution, we are looking at, as Dr. Kota mentioned, systems which are more electric to begin with. So you leverage your existing aircraft, don't have to make major changes, but you start changing some of the systems to more electric. Candidates are flight control, brakes, ECS, and DIC. You could consider hybrid propulsion solutions, whether it will be series, parallel combination of these power sources. You could also consider that strategy where typically in an aircraft, for example, in the climb and takeoff phase, you need a lot more power. So you would probably decide to use both sources or more than one source, out of which one is electric, during this high peak power demand phase, and then switch over to a more eco-friendly phase or power source during, let's say, cruise. like that. Or if you don't want to take all of that risk, then probably most of the ground operations, for example, you could, you taxi the aircraft or when you sit off the ramp and things like that, you could use more efficient systems, and they're already designed and already available for those kind of operations. And then you could start looking at sustainable aviation fuel, hydrogen, and batteries that we discussed. So probably in this sequence would be a good way to migrate or gradually move over towards these kind of things. And then ultimately. So here is a quick glimpse of some of the ideas and configurations which are already under development. You will find most of the major aviation companies are on board on this. Clearly, it is a global concern. And you will also find that many of these aircraft are already existing aircraft and not completely new aircraft, which have been retrofitted in some sense, as we intend to do, for example, in Hadsa, to achieve more electric or a less polluting kind of vehicle. When we look at the technology content involved, the components that we are talking about, clearly there is requirement for motors, highly efficient motors, propellers to match up with that, battery or fuel cell, the power source, and of course the power management electronics associated with that. And in motor space itself, there's lots of development happening, particularly on the electric vehicle front. When you have custom designed motors for various terrestrial vehicles, people are talking about developing superconducting motors, low magnetic loss for ironless, and using hardware carriers achieve magnetic flux densities. So my colleague Dr. Pankaj, he has done a patent survey, and you can already see that what is the kind of activity that is going on in this space. And today, some of the leading power generation companies, especially in the aerospace field, they are all actively investing in kind of technology, leading in terms of development of many of these components that or systems, power systems that we are talking about. Other colleague of mine, Devendra, he had looked at the option of whether we can take an existing aircraft, so in this case, a 90-seater passenger, one of a study, where you have traditionally about 2 engines, each of about 5,000 horsepower, fairly big engines. Can those less efficient engines be replaced by 2 smaller gas turbine engines? So it's a hybrid concept, hybrid electric concept, and additional 6, total 3 on each wheel of electric motors, which are readily available. So this is more like a integration kind of a solution. You have everything existing, you have existing engines of both classes. You see what happens when you mix them together in series or parallel. And then the concept is that during takeoff and climb, like I said, you combine both the engines, both are operational, both types of engines are operational. And during cruise, you partially use the turbofan, and then turboprop and try to optimize the electric motors for achieving overall an optimal cost. And of course, there is some penalty to be paid for the additional engines. So that's what they wanted for. And what he found was that it is possible to reduce CO2 emissions by about 45%. Emission fuel reduction also was there. Direct operating cost was about 5% benefit. And clearly, because you now had more power on board, more efficient power on board, so you could also operate on some of the hot and high elevation conditions in this country. And of course, greenhouse gas and noise emission also increased. However, since he was concentrating primarily on the battery side of things, so he found that he would need very high energy density. Today, these kinds of 1100 watt-hour per kg is not really available. It's on the horizon, but it's not clear when technology is feasible. On the other hand, for smaller aircraft, he also looked at 19-seater. Hydrogen is certainly viable for short range. That was his conclusion. Similarly, the government of UK has sponsored a Fly Zero concept, wherein they want to do a complete zero emission studies. So what they have taken is a very similar aircraft. It's the ATR-72. So this is their design of the ATR-72-600, one of the latest series, and you have the option of using jet fuel, which is standard, and you have in the second column the sustainable aviation fuel, which is biofuel, and the last column is if you completely replace it with nuclear. So again, we are talking of cryogenics and all the associated things. So what you will find quickly is that the payload is what they have done is they have taken the current version of ATR-7600 and assumed a requirement in 2030. Typically, what they have done is they have increased the payload. So in 2030, they expect that what payload will be required. So 7,200 gone to 7,800. And obviously, there is an impact on the max takeoff weight and the operating weight, as you can see here. And they have also increased the range. Again, this is more of a study in terms of what these technologies can bring to us, but important enough for us to pay attention to that. So 448 range is increased to 800 nautical miles. And what they have then done is basically resize. So you see here on the left-hand side, an aircraft with now 6 engines, which are running liquid hydrogen, as against 2 which are running jet fuel or a replacement like sustainable aviation fuel. And you effectively have the same kind of block time and block distance. There's a slight increase in block time here. And then again, to find effectively that it is in principle possible to use liquid hydrogen with current technology levels, be able to replace essentially jet fuel and still have a viable mission targeted to 2030. And so that was there. So now let's switch to, as Dr. mentioned, we have 4 programs. I am going to highlight 3 of them which are related to the civil aviation side. We've already talked about HANSA and its importance to the Indian context, why it is so important for that aircraft to develop, design. So we have the HANSA NG on the left-hand side, which is close to certification, a very good candidate for trying out our first version of the electric technologies or hybrid electric technologies. Then we have the CSIR Mark II under design development, currently in the critical design phase, which is a 19-seater variant of commuter category aircraft. And on the right, you have the regional transport aircraft, which is 70-90 seater category, very similar to the ADR that I talked about. And again, related to the regional connectivity that we are aiming for. Its project definition phase is just started. And clearly, these aircrafts we can target in the future these kinds of technologies that are available with us, should be available to us if we all come together. And so with that, let me conclude. I hope I have convinced you that India is going to be a growing market for civil aviation. Certainly, as we discussed, climate change is real and we need to address that. We also see that the government on its part has started many initiatives for better energy management, for more eco-friendly energy sources, not only for aviation, but for the power generation and so many other sectors of the country. And so we need to leverage that. We also feel that based on our work, and you will see some of those presentations by my colleagues and others, that it should be possible to use some of these alternate fuel sources and also electric fuel cells for smaller aircraft to begin with. And as you can see, the big drive will be coming from the automobile sector, and I'm sure we can leverage that part of the development as a system integrator house to be able to achieve those goals. And lastly, I want to, you must have seen some of those concept aircraft. So many of those concepts have been well studied. There is a lot of opportunity in many fields of aeronautics directly relevant to CSIR-NAL. For example, on the aerodynamic side, a lot of these capabilities allows us to distribute the propulsion units, and every engine designer knows that instead of having one large engine, it's always better, more efficient to have a lot more smaller engines. Same work that gives you efficiency directly. Also, many of the devices that we typically use, which are passive devices, can be replaced. For example, wingtip vortices or on the tail cone. It is known, for example, that you can ingest the boundary layer and thereby speed up the airflow and improve the overall aerodynamic efficiency of that shape. The boundary layer ingestion is one very useful thing, and by effectively blowing over all the lifting surfaces, you then can reduce the size of the surface. Okay, because you're creating more dynamic pressure locally. So therefore, you don't need that much big area to do the lifting or do the control and so on. And clearly, with multiple redundant, so it helps to have redundancy as well. When you have multiple power sources, failure of one does not create an immediate emergency. So you have many more which can counteract the effect of loss of power on one of them. So that also, in some sense, helps to reduce the control surface sizing and so on. So all of these benefits are immediate and can be studied within who have wherewithal to do that. Of course, couple of caveats when you look at battery technology or even other technologies like hydrogen. Clearly, safety is important, and in case of battery technology, thermal management is very important. And also, when you're talking of high voltage electric drives and so on, you do have all of these associated problems which you have to tackle. So it is not all a rosy picture. There is a lot of work that needs to be done to realize those technologies, and those need to address as we go along. And of course, at CSIR-NAL, the aircraft house, we look forward to these technologies and incorporating them in our aircraft. So with that, thank you.
Thank you, sir, for the interesting and great presentation on global scenario of electrical aircraft and technologies. Now, we will have a small break for tea. The dignitaries and the events to join us for high tea. Arranged at the launch outside the auditorium, and I request all of you to assemble here in a few minutes for the next.
So this is the existing Hansa NG. So we can see the brief specifications of the aircraft, and on the right hand side we can see the empty weight breakup, which is about 560 kg, and we can see that the payload weight is about 150 kg, and the total all up weight is about 750 kg for this aircraft. So for the studies, these are the brief assumptions which we see on the slide, and so the calculations have been carried out for a cruise altitude of 8,000 feet and ISA conditions, and also additional 3 horsepower that is required for as the offtake has been also incorporated in the computations. So this is a brief mission profile which we have considered. So we can see the requirements at different phases: takeoff, climb, cruise, descent, and landing for the present existing Hansa NG. So we can see that the power requirement for takeoff, it is about 78 kilowatt, climb 63 kilowatt, and cruise about 40 kilowatt, and descent and landing as takes a very less amount of power. And this is the time taken and the range for the existing one, what we have considered, the condition what we have considered. So now in the existing Hansa NG, these are the components which we can see, we can replace it with the electrical components. So these components weights are listed out in this table. This is about 163.1 kg. So this components we have replaced with the electrical components for retrofitting it into an electrical aircraft. So this slide shows the motor which we have selected. The motor which we have selected is a Slovenian company motor, that is a Imrax motor. It's an axial flux synchronous motor which has a max voltage of 500 volts, and it has a peak power of 109 kilowatt. Similarly, the controller, we can see the controller one, it's weighing about 6.7 kg, and also a DC-DC converter, which is weighing about 4.2 kgs. And this is a slide regarding the high voltage systems requirement, like the isolation unit, the fuse, and all other allied components. And that weight comes up to 8.25 kgs. And the efficiencies for the various components has been listed in this table. So we can see the efficiencies in the different phases, that is takeoff, climb, and all the other phases, the different overall efficiencies. Now, based on this, so all these electrical components, the weight is about 36.25 kgs. Now, so now the whole total weight available is 163.1. So from this, if we deduct this weight, 126.85 kgs is what we get for the battery. Now, additionally, to consider for the packaging factor of about 1.32, the battery which we have selected is this one, which is the Ampere's cell. So this has a specific energy of 360 watt hours per kg. So now considering the packaging factor, that is 1.32, the effective specific energy would be about 272.7 watt hour per kg. So this value will be used for finding out the weights of the battery required for various phases. So this slide shows the calculations for the weight. So we can see here, for the takeoff, 73 watts is required. The time for all the aerodynamic performance calculations are done. The time required is computed. So power into time, we will get the energy. Also considering the battery discharge efficiency, we will get the energy required for the takeoff phase. Now this energy required divided by the specific energy of the battery will give us the weight of the battery. So for all the phases, that is the takeoff, climb, and descent and landing, we have calculated the weights, and this total weight comes about 71.89 kgs. Now, from the total weight, if you minus this weight, we have is about 54.96 kgs, which is available for the cruise phase. So for the cruise phase, we know that our power available is about the power required is about 40 kilowatts. Considering the battery discharge efficiency, we can get a time, the time taken is about 0.36 hours for the cruise phase, and the range also is given. Now coming to the battery cell for the cell arrangement, the motor requires a voltage about 500 volts, and the cell voltage we are seeing each cell voltage is 3.8. Yes, sir. Cruise duration is about 0.36 hours. Cruise parts. Climb also is there. Yeah, I will give that. I'll show the whole total summary table. I'll show. So for getting that voltage, so 132 cells have to be put in series, and for the parallel, the weight available now, considering the packaging factor would be 96 kgs. So the number of cells to be connected in parallel would be 23. So its a battery pack arrangement is 132S, that is serial, and 23 in parallel. So this is the total summary of the table. So you can see that the total endurance or the time what we get is approximately 1 hour, that is about 52 minutes. Now the point to be noted is that our aviation gasoline, it has a if you see that it has a specific energy of about 12 kilowatt hour, whereas the battery what we have taken, for example, it is 350 watt hour. We should also account that the IC engine efficiency is very low. It is only about 30%. So ultimately what happens is, whatever the battery weight which comes for this kind of calculation is usually 10 times higher than that of corresponding a fuel based calculation. So this is the summary of summary of the whole thing, and we get a range of about 126 to 127 kilometers. Now this is the wiring diagram. For the same. This is a brief layout. Coming to the second case.
Exercise will not think you can convert to a product.
Exactly. Exactly.
Also growing. So, it's an experimental process. There can be various sections and how we can do that. But as an experiment, we didn't want to modify anything. So this is roughly the time. Can be a few minutes less, roughly you can say 1 hour. Something else. We have to think about an alternate also.
We have to look at now these grades again, whether they are 120 with maximum effectivity to, so that we can improve some levels in the. Because we do that, actually this, we are doing 20 minutes of time. Okay.
I can reduce my cruise speed, thereby I can increase my speed. This is the recent calculation. If you reduce the cruise speed also, I can increase it. But roughly you get about an hour.
See, that's not you by a trainer.
Sir, this is a direct retrofit.
Also, we can increase the weight of this from 750 to 780 or so. Two regulation doesn't give this restriction. Earlier there is a restriction. Two regulation, no restriction. So we can do that.
That will be not.
Huh? We can do that. Regulation recently has come, says no restriction, electric we can do. No, that is the law. Simple. Initially, we didn't want to go on increasing weight and all that. We are going to that. So that is the law. Okay. 1.5 hours we can certainly get. But
So now I will go to the second case. So anyway, tomorrow Sonde sir will explain the fuel cells related all the details. But I'm just 1 or 2 slides I'm just showing. So here now in this second case, what we are considering is we will use fuel cell and battery for the takeoff and climb condition, and in the cruise, descent and landing, only the fuel cell will operate. So we have given the share of the fuel cell power and the battery power in the takeoff and the climb phase. Now, as explained, the time required for the takeoff and the climb is known, calculated. So based on this, the energy required for both the phases are calculated. So we also know how much is the battery weight required for the both the phases. Now coming to the fuel cell. Now we have 126.85 kgs. If I deduct the battery, I will have 111 kgs for the fuel cell. So here we have assumed that the whole fuel cell system weighs about 84 kgs. So now if you deduct this, what we are left out is with 27.35 kgs for both the hydrogen and the hydrogen content. Now the thing to be considered is hydrogen has 3 times higher the specific energy than the aviation fuel, but its volumetric density is very low. So even at 700 bar, the density obtained is only 43 kg per meter cube. So the efficiency of fuel cell is still better than a normal IC engine. So we can obtain, let us say, about 60% efficiency for the fuel cell. Now the major other drawback here is the mass efficiency for storing this hydrogen even at 700 bar is very low. That is 5.7%. That means if you have to take 1 kg of hydrogen, the container weight would be about 20 kgs. So based on this, the hydrogen storage tank weight is as given 25.87 kg. So the weight of hydrogen what we can take is about 1.47 kgs. So these are some of the equations for computing the flow rate of the hydrogen, and we can, based on this equation, once we know how much hydrogen we are carrying and the flow rate, we know the time for that particular phase. So this is a summary of the whole thing. So here we can see in this hybrid mode, the time is slightly better, means it is nearly coming 1 hour. The other thing to be noted here is, for example, just hypothetically, if I increase 25 kg, I'm able to carry, let us say, extra 25 kg of battery. The endurance will only improve by 10 minutes. Where I go for a fuel cell, I can carry additional 1.5 kg, which will improve the endurance by 45 minutes. So this is how then I conclude. So that the battery only energy system could become optimal only for a small aircraft with high specific energy if we are achieving high specific energy. Whereas in the mid-range, hybridization with a battery and fuel cell would be beneficial. But however, we should note that the battery would be a dead weight for all other phases of the flight. And in case of longer flights, a fuel cell or hydrogen-based technology or liquid hydrogen or this gaseous hydrogen with hydrogen-powered engines would be the suitable one. So the reduction in noise, exhaust emissions, these are what is driving the clean energy initiatives. And there are other advantages like reliability, improved reliability, novel aerodynamic designs, etc. And there are also things to be noted like the safety related concepts and other certification related aspects for electric aircraft. So these present studies are just an attempt to initiate these activities in line of that.
There were some questions. Yeah.
Understand that that's just preliminary, but I think the number that you're showing, I miss many things. For example, in battery, I mean the temperature effects, period effects, everything is clear. These calculations are really simple. I think a much better idea is to get into do a simulation.
Yeah. Yes.
So unless you do a simulation, these sort of
Correct.
calculations are.
We have to do detailed studies.
Let him complete. Let him complete.
The second thing that I think is that because you are.
It's not switched on.
Yeah. The second thing I'd like to say is that because you have chosen to adopt an airframe, you are constrained on the energy side.
Exactly.
If you redesign the airframe, you will do much better on the engine. Right. So you will get some through this you will get some preliminary technology experiences, but they are not really realistic and anything. This is not an electric aircraft design from aerodynamic point of view. That is the second point. And the third point I want to make is that this is a case, normally aviation leads automotive in technology. This is a case where automotive is actually leading aviation. So there are lots of other things that you have to pay attention to. For example, safety, reliability, they're going to be very, and then, I mean, during the first session, I mean, we understood technically, but there are lots of costs. If you're talking about civil aircraft, then we have to talk about ownership costs, life cycles, manufacturing. So there are even those. So, but anyway, it's the beginning. That's interesting.
Yeah. This is totally excellent. Compliments you. The only request is that we do this analysis for comparison. Maybe end of life at a party or something, because I can't say anything more about end of life. Anyway, the GDP may take about 0.2% per year on reduction in the matrix. We may this kind of a phenomenon. We can understand maybe 0.6%, and which means may come down to 300. So if that you can't change the practice or cost and 100% when I'm waiting for the fuel. To call the UN, of course, the simulations and everything and you are
one small suggestion that I want to give you. Otherwise, thank you very much.
Thank you.
If there is no more question, thank you very much for it.
Thank you.
Yeah. So we'll go for our next presentation, which is from Dr. B.R. Pai for the electric powered hand guidance.
Pointer? Maybe. Pointer is there, sir, but you have to change like this one. I don't know. This pointer have to this. Use this one. Pointer. Pointer. No. This is one. Pointer. Okay. Right. Okay. Good morning, Chairman. Good morning, friends. I'm very happy to note that proposal we had made for two-seat Hansa with either battery or hybrid propulsion using engine and battery about a year and a half ago has now taken the next phase, and the lab is seriously considering a two-seater version of the Hansa with battery operation. But as has been pointed out, there are challenges with the present level of battery availability. So I want to take a slightly different view in today's presentation. My plea to you is, sir, is that India is already very late in making its presence in the field of electric manned propulsion, though there's a lot of effort in UAVs. And we can endlessly go on discussing the best aircraft and so on. It will take time. But meanwhile, the rest of the world is moving on. As the chairman had pointed out, Pipistrel has already come with a trainer two-seater, which is doing quite well purely on battery. For training, it's very good. So let us start somewhere, even if it is at the bottom of the scale. And my proposal is that we use the powered hang glider, which I'll explain because many people may not be familiar with it, as a platform for checking out new ideas. Now, the next slide. Okay, this is a powered hang glider. This activity was recommended by our chairman, Professor Satish Dhawan, in the late 80s, saying that all the people working in aviation must have some first-hand experience in flying any aircraft or this it. So NAL chose the powered hang glider, which was being developed indigenously in Bangalore and Mysore. And we have been carrying on that activity for the last 30 years. And many staff members have been trained in flying this kind of aircraft. And so it's quite a well-known animal, though it's not very well-known in the general parlance. Just two lines about what this aircraft is. As you can see, it's got a wing made of cloth, and it's a delta-shaped wing without a tail. But years of development have made it a very safe and stable aircraft. And it relies on weight shift control rather than individual controls of ailerons and fins. That is, the weight of the pilot and the suspended mass from the wing is controlled by the pilot, and the position of the weight actually controls the movement of the aircraft. So it's very simple, and it's now very safe and easy. It can be packed very simply by taking out the wing and so on. I won't go into the details of the aircraft, but as you can see, two people can sit in it, and there's an engine at the back which is pushing you forward. And you can undertake journeys of, let's say, 100 kilometers up to 200 kilometers. Main thing is the stall speed is very low, so it is about 55 kilometers per hour. So landing speed is low, and it's quite a safe aircraft. Of course, the main thing is it doesn't need a certified engine.
We used to use an engine on which we had to write a board. Okay, so next thing is, yes, thanks for the warning. So I've already said that it's already available with us, and some time back we have converted to fly a Wankel engine to be fitted to this, and we had no problem with the DGCA. They let us fly it, and so we got a very good performance with this rotary Wankel engine. So I want to spend 2 minutes on this. So idea is either a pure electric powered hang glider or a hybrid with a Wankel engine and an electric motor. So the next slide. Can we play this video, please?
On National Geographic Channel's Hot Science from India. A testing time about the outskirts of Bangalore. A test of an engine designed by a German, then embraced by the Japanese. An engine that's been refitted to the needs of India. The needs of Indian skies and of Indian roads. Working on another type of engine. An engine designed originally in the 1930s by the German engineer Felix Wankel. It's called the Wankel rotary engine. Instead of pistons and fixed cylinders, there's a single rotor. This rotor spins around a chamber, a journey that drives 4 phases of combustion: intake, compression, power, and exhaust. The engine is light, compact, with few moving parts, and because the rotor spins in a single direction, a Wankel's performance is smoother than that of an engine driven by reciprocating pistons. Over the years, however, the Wankel has been plagued by 2 design problems: proper sealing of the motor and effective cooling. Indian researchers in Bangalore have been working to overcome these issues. The alloys used in the seals have been hardened and a new cooling fan added. After exhaustive testing in the lab, the ultimate test of the sky. An ultralight hand glider is a test rig. The glider's low speed will give the new cooling system a thorough workout. Dr. B.R. Pai is the pilot. His machine is fitted with a Wankel rotary engine capable of 35 horsepower. The team is continuing its Wankel work. But for Dr. Pai, it's all systems go. The test flight suggests the NAL's modifications have overcome the heating problem.
We have done some instrumentation on it so that we can measure the critical temperatures. And
Can we go forward?
Coming back to this, certificated engine is not required. So let's globally what is available in electrical powered hang glider. Next slide. Yeah, please play the video on this. Very short video. Yeah, so just 1 second. This is a powered hang glider with an electric motor at the back. And we can show 30-second video on this. So you can see how it is. So this CNC is now commercially available. So the point is, if we want to get into the field, what happened? No. It's okay.
I think you have to speed up, sir.
Okay, so two versions of the hang glider are shown. One is electric with an electric motor, and the other one is a hybrid. If you go to this slide. This is the vacuum engine. One before this slide. Yeah. Here we have proposed that we have a larger combination of motor and yeah, this is the vacuum engine, the propeller. This is the electric motor. Just have two beds, different ratios, and it drives the propeller. So very simple. It can be very fast accomplished, and we can have this working in about 1 year and a very problem. Next slide, please. So this is a vacuum engine developed by India. It has already been certified by Similac for UAVs. So that's quite sufficient for us for testing out on the high level. It develops 55 horsepower.
See, all the years same story.
Okay, next slide, please. This is pure electric version. So next slide, please. This goes into the details. We'll skip that just to say that we have enough power and battery model. Next slide, please. This is the controller, which again is that one here. Next slide, please. So this is a battery pack, which is a little 22 minutes only. So this is a battery pack of about 11 kg weight and about 205 watt hours per kg. These are being already used in aircraft. So this is what we can use today. We use a very high energy density. Those are not yet safe enough for use in aircraft. So this I can use. So we would like to use this. Now with this and the next slide shows that now we have to control two throttles, one for the electric motor and one for the engine. And we worked out that either you can have two mechanical throttles or they can be coupled through a microprocessor, straightforward thing. Again, we won't go into the details, but we are given enough thought to say that it's fairly straightforward and it can be done safely. Next slide, please. So this is the microprocessor with controller. And the next slide. Mostly what we're trying to achieve was whatever performance we were obtaining with the Rotax engine, 65 alpha, same kind of performance we should be able to get with either the hybrid or the pure electric. So, and we are given a very simple requirement. Line take off in 1 minute, line for 2 minutes, and cruise as long as the battery are clear. So this next slide. So we come to the final slide, which says the two options. One is the configuration with 55 horsepower vehicle and 15 kilowatt electric, and either with 2 persons or 1 person. So with 2 persons, you can carry 23 liters pure, 26 kg battery, and 23 So we get endurance of 72 minutes at an electrification factor of 0.17. Now, you should remember that we could always carry more, little more liquid fuel, and we could have a 2 or 3 hours life. So this is a aircraft which people would buy, they would like to buy, and if we can increase the battery by factor of 2 with the 2 packs, we could get run over an hour flight at a higher electrification factor of 37%. Because communication and combination. So which means that hybrid version is quite attractive. This will be a first in the world. And so we would recommend this option. Pure electric option has also been considered. But what is happening is single shift operation, maximum of the battery, we get about half an hour of flight. With 2%, we are only getting about 15 minutes of flight, which makes it a non-starter in my opinion. So this is kind of state of things. We got two options to electric. This can go in Bangalore with the on-site development. It will take much less cost and can complete it. That's why the people. I will skip this slide because there was, yes. So this is basically my conclusion. This will concept of hybrid pure electric will be able to early management. Thank you.
Any question? Take one or two. Actually, what we are using, that's the technology is improving. We can increase the endurance.
Yes.
Yeah, technology is
Yes. So both options are there.
Scale, I don't see any advantage of hybrid. Actually, either electric or hybrid is much better than this. At the scale of operation. This is
a demonstration.
Why? You're putting both the hardware, you're putting battery and the what?
I don't see that one. Was appreciated. What was appreciated. What really make it a life different more. But by making two, if we buy more of the liability, then we will get everything. Like the current money technology is much better for like
Become operating cost.
actually company cost much lower than the fuel cost. That's not a point. If you want the salary about 10 years back, we didn't know enough, but today we have enough back to capital. We don't need one as a all. So we have an excellent one. And they are present there. So we have to
Development.
yes, that's the development. We know what are the problems. Take the next presentation on electric RT by Dr. Kota. Yeah. Gentlemen, this is a concept study, not even a feasibility study. I want to mention to you because the whole world, we are just thinking how to move forward. A tremendous amount of uncertainty. I presented to you our ideas about what could be done. Okay, and a lot of simulation has to be done. A lot of what you call sensitivity study has to be done. And but I thought here is a team where we can look at it, what are the issues, what are the probabilities, and some of the slides are skipped, and because already we are. Why India should do, I thought this slide is important. We are the third largest emissions in the whole world. We should not think per capita we may be low, but we are the third largest. We have to take care. If we don't do, the country will go down. It's not the world what we are worried about, even the country will go down. And there are changes. All over the world, there are problems. And today there is a mandate that we have to reduce. There is no escape. If we want to be part of the aviation scene, we have to do that. I don't think there is any shortcut for us. But the problem with India is, fortunately for aviation, road transport, they have done a tremendous amount of work. A lot more industries are investing and all. We can piggyback on that. We have to do incremental investment, and by doing incremental investment, we will be able to make this technology amenable for aircraft. I think that is the key point we have to keep in mind. Otherwise, the investment will be extraordinarily high. So incremental, but that much we need to do. The Indian scenario is we are the third. Our traffic is growing largest. In spite of all the COVID, and everything, we are the largest traffic growing. In fact, next 10 years, the prediction is we will 4 times more traffic will be there per passenger. So that is the thing. And domestic, we are already third. In a matter of 2-3 years, Bashilkar has said we will become the third largest. And important point is all the crude oil we are importing, 80%. So we have to find a way how to move. And I do think electric is a solution for us. And we should invest in electric technologies so that our efficiency will increase, reduce the weight and volume, insert it in our aircraft to reduce emissions, and also reduce cost. Not enough data is available on cost, but I have a feeling from what little I will show you some slides. We have not done verification because we don't have enough data. As we go by, we will see how to do. I think Pashilkar has already shown that you reduce fuel costs, quieter operations, increase it, reliability. Reliability will increase quite a bit because there are hardly any moving parts, very few. And emissions are not there. And with tech startups and established companies joining forces, fossil-free flight is quickly transforming from a futuristic vision into reality. And also I want to tell you, there is a comment that we are late. That late, let me put to you. Only last year, 2021, UK has started investigating into this one. And there is a report which says in March 2022, what is the way forward? So if we start working, we'll be able to do that. No, I just want you to spend a little time on electric aircraft configuration design. See, for a conventional aircraft, large statistical data is available on component weight, geometry, performance, system characteristics. From previously designed, hundreds of aircraft have been designed. For electric aircraft, no such data is available. And as configuration system modeling cannot be generated based on statistical data. We have to use physics. Maybe as we generate data, we have to fine tune it. Even the regulation do not. There is no regulation today which says how to design an aircraft, how to certify. That itself is the way energy storage is totally different from conventional energy in wing tanks with significant impact on structural design. Because my weight of the fuel is a relieving load. But here there is no fuel. Okay, so the structural weight will increase unless we have some alternate options to look at it. Then the operational characteristics are also different. The conventional gas turbine propulsion directly an ambient condition. As my altitude increases, my density comes down, my temperature comes down. So the propulsion thrust will come down. Here it's not so because my battery will continue to work. Only the propeller will have a problem. But all other things are so the way we operate the aircraft, the way we do is totally different. So there is a need to modify existing aircraft, carry out series of experiments, generate data for updating the model to size the aircraft. This would enable as in safety and life. So you may ask, there are cost increase and all. Let us understand. You have to take an existing aircraft and modify that, understand the whole thing. It is not good enough that you have a motor and all. There are safety issues, there are EMIFC issues, there are other issues, and all that must be understood. For that, an existing aircraft, if we take and start experimenting as early as possible, and a 2-seat and a 19-seat and all is important. So that we must keep in mind, even though it will be not cost effective and all that. Here is the zero emission technologies. You are aware of that. People are working on what you call biofuel, hydrogen for fuel cell, and battery electric. What I am now talking will be the last two. Okay? Because biofuel and all is there, but biofuel and internal combustion needs a gas turbine engine. Okay, they are modifying an engine. Here we are talking about an alternate, because anyhow in India, all the gas turbine engines we have been importing only, whether it's for fighter aircraft, transport aircraft and all. As well, we look at the alternate, where the chances of success are quite high. I find this particular technology roadmap by IATA to 2050 is important for us. Electric aircraft up to 2000, let's say 2025, maybe you can make 1 or 2 seats. That is what certified. That's what is going on. Then hybrid electric will go from 25 to 30, or 30 to 35, bigger aircraft. Maybe 25, 30, they're talking about 19-seater, and battery and fuel cell powered aircraft, we are talking about 35, 40, 45 and all. That is the kind of time frame because technologies have to grow. knowledge about how to integrate this technology have to do, and this is where the challenge is there, and this is the kind of time frame we are talking about. Most of you are aware that today we operate ATR, Bombardier, and IL-114 we don't operate, but is available in the market, and there are problems. It's an old aircraft, old technology is at least 3 decades old. Okay, that is what is the kind of thing. And we have a requirement. The requirements are that we must improve the prime thing is not so much speed, this, that, and that. Operational cost has to come down, noise has to come down, and that is what quite some time, for almost a decade, we have been working on this one. We continue to work because electric technology will take about 15 years to come. But before that, we should be able to have a regional transport aircraft, and that is what is going on. And these are the kind of technologies I marked in red, 2 areas where you are talking about. It's no longer a gas turbine engine, you are talking of an electric motor along with fuel cell or battery or a combination of that. Other thing is, our aircraft today are hydraulics, pneumatic, and all that kind of things are there. We have to change to electric. So in this program, what we have today and all, we will be talking about what are the changes that needs to bring. Some of the experts in the field they will be talking about. Now, this is the kind of thing, I think Pashilkar has already told. The benefit is battery 100%, but net it will come to 73%. And fuel cell net will come to about 44-45%. That is the kind of. But where you are talking about turboprop may come to 35% net. Turbofan will slightly better because bigger engines have better efficiency, but smaller engines will be inferior to prop. So after class, what we are talking, in fact, a turbofan is inefficient compared to a turboprop. That is the reason why people use turboprops regional aircraft. So this gives you as an idea that battery, if you are taking a 2, hydrogen 120, kerosene 43, and ammonia is 18. We are not talking about ammonia, but ammonia is also an important element. You could see the ratios as weight is concerned. Ammonia, hydrogen is great, volume density is extremely poor. That is where the challenge comes. That is where how we handle that is an important thing for us. We have done an option study like this. Okay, it's not an exact option. We have done this one. Battery today, what we already have is 370. I thought we start with 500 because the very projection is by 2023 it will become 500. It could even become 750. So we look at 500, 750, 1000, 1250. In my opinion, 750 and 1000 could be a viable thing, but 750 certainly. Fuel cells, whatever Professor Sondhi is trying to teach us, we are looking at 4 kilowatt and also 7 kilowatt because today the analysis shows 7 kilowatt has been already achieved, and today that is the state of art. Okay. Then motors, we looked at 1 megawatt, 1.5 megawatt, and 3 megawatt. And I will tell you what we have done that. The thermal management system, air cooled, air plus liquid, and liquid cooled. Whether air cooled can be used for a big aircraft, we need to see. Looks to be may not be possible. These are the options we have looked at. And I want to use to see this. If a 90-seater, 90-seater aircraft has to burn, if you have to have a 2 engine, you need 3 megawatt motor. This is the drivetrain option. If you have a 1.5 megawatt, you have to have 4 motors. If you have 6, you can manage with 1 megawatt. There are advantages and disadvantages. What are the major things is, initially, we were studying about 4 into 1.5 megawatt. In fact, I was talking to our friends in IIST and all. But then I was looking at the last few couple of maybe weeks, 2-3 weeks, intensely looking at that. What is happening if a number of motors are increasing? There is what you call a benefit called lift generation capability can be included. Multi-motor configuration. Pashilkar has just shown that one. Thereby, the drag increases, weight increases, but the lift increases. So L by D increases. As a result, it looks to be a minimum of 6 if you are putting, there is a benefit in L by D. Okay, that maybe we should be able to do. In the evening, along with the propeller talk, Venkat Krishnan will be giving a short presentation about what are the benefits. Okay, I'm not going to cover that, but he will be talking about what is the kind of a benefit we are taking. For this today's presentation, I'm going to present to you for this study a 6 into 1 megawatt. shows that high temperature super motor would be more suitable for 3 megawatt and higher. But no such motor is available. A development is in progress. The correct are not yet available. Unfortunately, nowhere available. Distributed appears to offer improvement in aerodynamic efficiency. That's what I mentioned. He will, Krishnan will present. 6 distributed propulsion units do provide good improvements in aerodynamic compared to 4 distributed propulsion units. And 1 megawatt conventional motor for aeronautical applications have been developed, and this data is available very well, very well. It's a fairly good technology, and our colleagues have done the study. So this is the kind of idea we are talking about. You could see the propellers. We have to optimize the propellers and all that kind of thing, but it will energize that thing. But so-called laminar flow is not possible. It's not possible at all. But LVDV will improve. This is what we are talking about. And we looked at 2 options: battery powered and fuel cell powered. In the battery powered, as we all discussed with the battery, with the BMS, switching and protection, you have to give a supply to utilities. DC converter goes to utility, and motor controller, electric motor propeller, and all that good. Here, the propeller, in my opinion, while you can start experiment with the existing propeller, but a new propeller has to be designed, which will be optimized, taking into account the motor characteristics. The fuel cell powered, we are now talking about a hybrid one. It's not pure fuel cell. Takeoff and climb, we will do battery to support the fuel cell, but fuel cell will be right through. And I understand that is the best option today, tried elsewhere in the world also. The problem with any study is you have to do a sensitivity of key parameters. Data is not available. It's only, we just could get one study. I hope more study I can get from my colleagues from IIT Kharagpur and all. And but if you see, a lot of parameters can be varied. It's a MDO study has to be done. But what number of motors, what you call packaging and energy, okay? What you call specific energy. These are the key major parameters. If these can be targeted, but fortunately for about packaging, what I am seeing from what our studies have been done, initially the packaging from a cell to package, we used to lose about 25 to 30%. But today, what our studies we have done with the latest pouch cells, the increase is only 12%, 11 to 12%. So that is something good. So the sensitivity is not too high, but number of motors, weight will increase. But the other benefits we have to see. And of course, specific energy is a key parameter for our work. This is just broadly what people are talking. I am showing this report, which is March 2022, last month's report. This is what they say: carbon dioxide emissions, NOx emissions, contrails, good battery, fuel volume, fuel propulsion system mass, airport infrastructure. Quite good. Battery now it looks to be liquid fuel cell. Emissions and all are okay. All right in the three, but airport infrastructure is very difficult. That's what it states today. But gaseous hydrogen, I've given you that, plus battery also I've given that. With other thing also I've given. Okay, this is roughly the kind of thinking people are talking. People are talking about gas, liquid hydrogen, but a bigger aircraft. But I have a feeling for perhaps 70-90, what we are talking, maybe liquid could be that, but more detailed study has to be done and look at the technology, sizing and all that, and look at it. I want to bring to you an important concept called a Ford concept. What we are now talking is, these engines are not mounted directly on the engine, nor these energy sources are mounted on the engine. They are kept on a pod, and the pod is hung under the wing. Okay, so with pod, changes to fuselage weight horizontal will be minimal. Likely improvement structurally, the pod gives a relieving load. Because I have removed the fuel, so my relieving load with distributed propulsion wing efficiency improves. Development battery system, fuel cell system, and drive system could be localized to pod only without impacting the rest of the aircraft, which is an important thing. All my effort can go in. Marginal increase in weight, because pod means I have to put in a structure, maybe about 5% increase in the weight will be there to support the wing. Okay, otherwise I may get lot of benefits. It's a concept study, but I want to present to you what we are. This is the kind of what we are talking. I have my propeller, I got my motor, I got heat exchanger, cooling system, motor controller, inverter, battery unit along with the slave BMS, DC-DC converter, everything is here. Something similar for the fuel system. I couldn't get enough data from Professor Sonde. I couldn't make this for the thing, but we will be able to do it as we discuss and do that. This is the pod concept what we are talking. Mount it under the wing, and 6 such pods are there. It is just replication of these pods. So and this is the kind of diagram. Today, with a conventional gas turbine engine with a 90-40 seater, if I use a 150 engine what we have today, I can say what is there. But if I reduce it to 4,000 shaft horsepower, I don't need 5,000 because there is no engine we are using. If I reduce it to 5,000, my range increases, my endurance increases, everything increases. That's what we showed in the red line. Okay. But if I use now, I use it. I'm showing the ATR as a baseline here, and you could see that today we are if we are going for a varying ranges of what you call the battery and all, we are something like about 1,000 kilometers. That is what we can get with assumption of what you call the technology we are talking about, battery and fuel cell. So as regard the battery, this is the kind of projection I saw NASA, the old one, 4 years old, and they were talking about 600 watt hours per kilogram and 1,000 watt hours per kilogram and all that kind of a thing. But I'm very happy to note whatever they have predicted, the battery technology is moving much faster than this. And I am showing this is what our what you call our ANSA engine, what we are doing. By 2023, they are talking of 600, whereas the NASA think by 2030. That means the gradient of improvement in battery technology is very high. It is going on pretty good, and that gives us a good understanding that assuming about 750 or all is not a what you call imagination, something achievable. And today already 500 is available. Now let us look at these are the, if I want a 500 nautical miles, because 80% of the what you call city our flights and all are within about 900 kilometers. If you took 500 kilometers, you will come to roughly about 40-50%. We get some good efficiency, but is it a function of what you call cell? Here I'm talking cell means battery cell, what we are doing. I want to show a few slides. This is a March 2022. A lot of technology work we need to do. The technology we are talking about is electric motor, electronics, DC-DC, power electric inverter, fuel cell stack, thermal management system. I'm talking here no longer battery. I'm talking about only fuel cell and air supply system and electrical propulsion system. These are the kind. We are talking about what is what we call TRL level 6. You will be able to achieve by 2026. It is the world scenario. 2030, you are talking about power density. We are talking 23, 25 and all. Then we are talking fuel cell stack. From 7, we go to 9, we go to 16. These are the kind of what you call projection. We need to discuss and see what we are there. But this is the projection which was made last month by a think tank and institute in UK. Okay, they started the whole work last year. We are starting now. So this is what it is. And the electric motor roadmap is important for our colleagues who are working. This is what they call as motor technologies, cell-winding technologies, magnetic material technologies, manufacturing projects. The reports are all available in the depth, but they only talk about what to be done, what are predicted. How to be done, they won't tell. Naturally, they will not talk about. This is the power electronics, a very important area to remember. This is what is the technology roadmap, what they are talking about. It is very recent, that's why I thought the community here should get an idea about that. This is the electromotor roadmap, what we are talking about. And this is the power electronics roadmap. This is what we are talking about. One important thing, this is the fuel cell roadmap. Maybe the team must look at it much more in detail. This is what people are talking. And we need to keep in mind what is the kind of thinking we have in mind. There is a roadmap I have already shown. And I got back. This one slide I want to show. All these big things we are talking, major fellow in thermal management. If we don't concentrate on this, we will get into serious trouble. In fact, fuel cell and all what we have seen, even if you make it less, but with the thermal management, that will occupy. So parallelly, we have to work on thermal management along with fuel cell and battery. That is battery and fuel cell, enormous amount of heat is being generated. And this is an important area which thermal engineers and mechanical engineers must look at it. Now, configuration, what we are, if that pod is we are developing, same pod, two such pods, we can use it for a 19-seater aircraft. Because we are talking about 1300 SAPR, 1 megawatt, two such pods, we will go at 13. If we are using four such pods, I can do a 40-50-seater aircraft. And if I use what you call 6-1, I can do 17 to 90 seater, depending upon the payload and range requirement. That means one single pod, if I am putting all my effort and all, I will be able to take care of a 19, 40, 50, and 70, 90 seater. That is the benefit which we will get it. There are issues we have to solve, but I thought this is something this community can have a look at it and looks to be something good for a country like India. So way forward, introduction electoral propulsion is a revolution step, and it is good. Increasing investment, auto industry is helping us. Incremental investment we have to do. I do strongly believe we have a combination here. University, lab, and industry are working together to develop the technology, leading to realization of aircraft. Lot of experimental work we have to do on ground, in the air. This technology will enable the twin goals of elimination of emission and crude oil imports. I have not written here, but also we don't have to worry about gas turbine technology. What once developed could be used not only, that's what I said, but also 40, 50, and 90 seater. Commuter aircraft based on electrical power could be realized next 10 to 15 years. The regional aircraft may take 15 years. But technology development, there's a clear goals, and that is what we need to do. Thank you very much. Thank you all.
Thank you, sir. Some questions? No? That is one of the complicated, that the border is something, just remember when we are talking about atomic power, we talk about what this kind of system we are talking about. That gives a very, actually 1940 and then 70, something.
एक लाइन में होता है.
It is absolutely very happy one that I remember when we talked about the electrical opportunity was very good back 5 years back. I think the maximum seconds was on the quota and we needed to work maximum. I'm so happy to see this transformation back to quota. It is absolutely on the entry is already solid-state battery, which has charging time in minutes, has been tested. Charging time in minutes for a solid-state battery. I don't know how much time it takes for us, 20 years. But what use is the story that at 800 watt per kg, 2000 will have the RPA feasibility. Really, but I still have the combination of the
Will be right. Thank you, sir. Professor साहब, आपके बिना महत्व complete नहीं होगा. You have to make a comment.
These are very exciting directions, especially for a researcher like me. Just wondering, sir, why we are not talking about an electric helicopter?
Helicopter.
Yes, for
These are all subsets.
for urban transportation.
No, I am not talking about urban transportation.
No, no.
We have avoided urban transportation. This seminar is not talking of UAM. It's a gone story. It's a gone story. हो गया, हो जाएगा. हमें सेमिनार की जरूरत नहीं. Why we should? We are thinking about what India should do. There are enough startups here. We are already doing UAM. They are already doing. हमें इसमें फंसना क्या? But आपको, I also don't want you to spend too much time on urban transportation. Your research work should be जो हम बोल रहे हैं. हाँ, वो आपको करना है. Modeling, simulation, doing that, all that we need to do, and all the utilities we are using, convert them to electrical. That's why we have a session now, and we need to look at it.
I have a question.
Excellent. One question is, what is some type of thing about the part that we did. Centralizing the fuel tank. Yeah. I'm able to improve this. We have to see whether fuel can be liquid or gas. On an alternate like part for what you are doing. Okay, and that could be added to the part and the part. The part in such a way the motor driver, all that you don't touch it all. It will be left. Other fellow is like to bring down and put it back. That's so such a modern concept. Yeah, really. Okay, thank you very much. Okay. Any more questions? Let's take one or two from young people. Okay, louder and come closer.
Yeah. Thank you. Thank you. Good morning and thank you for the wonderful session. Sir, my only question before this. Well, we have an understanding of the case that electric aircraft and the ultimate fuel for these are the kind of technologies that we are using. And this particular program is towards acting as an eye opener or synergizer for the whole of the relation and the but then, what kind of initiative we should take still makes a question. Because I look at global warming, and like you said, between 2015 and 2025, a lot has happened. And we, as India, this is not a lot, and absolutely the right time to get into this, get that segment. So, I would like some questions. What is the kind of industrialization one? I'm aware that and users from all activities here. But then, that point, what kind of energy in the next 3 years we actually materialize and realize this as a practical technology change?
Good point. And we have a lot of sessions. We have a lot of sessions which will clarify all your doubts. Yeah. You have many sessions, madam. So it will get clarified by tomorrow afternoon. A lot of them. So what I can conclude from this session is, first we'll go for Hansa NG. There are good points that come because it is not good to start retrofitting as it is, which people have said, as rightly pointed out by the people, that existing Hansa NG airframe and aerodynamics needs to be improved. And as Goyal Sahib also concluded that 52 minutes and 60 minutes, nobody will fly the aircraft. Okay. So we need to do a lot of other groundwork to reduce the empty weight, as well as some suggestions have come about the aerodynamic improvements, because when the Hansa 3 to Hansa NG, we have almost reduced the count by 70. So there is further need of reducing the count to get aircraft at least 1.5 hours. Without 1.5 hour endurance, the aircraft is not even worth for flight test. That is what has to be taken a good suggestion from the people, and NL will work for it, because there are a lot of things needs to be there. Just some small fine tweeting I can say, which will take it to 1.5 hours. So that is what it is. About the glider, I think we need to take a call, because glider whether to take forward this thing. And Dr. Kota has bought a podded concept. So as podded concept is basically we have a nacelle onto the aircrafts, and if you want 2 engine, we put 2 nacelles. If you want 1 engine, we put 1 nacelle. So the nacelle will get replaced by pod, I believe. And supply
And the pod will have hybrid thing, I think, battery as well as fuel cell. And the supply will be as per the supply tank of normal propulsion. So that's how it is a good concept. And I think I must congratulate all the three speakers who has given insight and all the audience also for good interactions. Thank you very much. Thanks a lot.
Sir, on behalf of the organizing committee, I thank session chairman and all speakers for taking us to the journey of electric aircraft studies and giving us the global perspective. Thank you very much, sir.
Sure.
Dear participants, now we move on to the next technical session. That is technical session 2 on electric utility systems, a key area which needs to be addressed to have a successful aircraft program. To chair this session, I kindly request Sri Yogesh Kumar, advisor CSIR-NAL National Laboratories, to come on to the dais and chair this session.
Good morning, all. Very important session amongst the all-electric technology, electric utility systems. We have 4 lectures in this by eminent speakers. The first is on electromechanical actuation for landing gear, very important. Then we have electric environmental control system, the next lecture, and then we have electric braking system and more electric flight control. So this covers most of the general systems. So I would now invite in fact, the first speaker would be giving his talk by virtual this thing. So can we have the first speaker now? Electromechanical actuation for landing gear by Mr. Divakaran. He is ex-HAL. Most of the landing gears for the indigenous aircraft have been done by him and his team. And he will be the first speaker on landing gear electromechanical actuation. Can we get connected to him, please?
Sir, you can unmute and start your presentation, sir.
Good morning, Chairman.
Karan, sir.
Who are there? Am I audible? Am I audible? Hello?
Please go ahead, sir.
Am I audible to you?
Yeah.
Can you hear me?
Audible, sir.
Yeah, you are audible, sir.
Okay. Fine. Sir, the topic today I am going to present
Yes,
is
sir. You are audible. Please.
okay. Use of electromechanical landing is used in this presentation. I intend to cover of using RTA. As the size and speed are increased. So we can see actuators are used in aircraft for operation of flight control surfaces. That is, we have primary control surfaces like elevator, aileron, and rudder. Then we have secondary flap, and spoiler. Then landing gear, retraction and extraction and closing and opening of doors, opening of nose wheel steering, wheel brake, air brake, weapon bay door, cargo door, first reverser, landing gear up lock, down lock, engine during actuators are used in the aircraft in various places. The operation of the flight control surface and landing gear actuations are considered safety critical because failure of those actuators can lead to a safety issue. Go to the next slide, please. So actuator have various types of actuators have been developed. They are hydromechanical actuators, electro-hydraulic actuators, electro-hydrostatic actuators, then electromechanical actuators, and pneumatic actuators. Out of this, pneumatic actuators are of a very limited use in aircraft. So we will confine to the other four type of actuators. We are just explain them to you, and then we will go to our further studies. Mechanical actuators are hydraulic actuators, that is hydraulically powered actuators. Controls electromechanical valves. So in olden days, this electrical control was not there, so all the valves used to be controlled mechanically by the pilot. So such actuator was hydromechanical they offered good flight resiliency, power density, and response characteristics. Power density in the unit or characteristic. So both the accounts, the cyclic actuators were very good. Hydromechanical actuators dominated the scene for a few decades till they were
Sir, you can mute your video and speak. You can mute your video and speak. We have a bandwidth issue. Your audio is not clear.
okay. Then came electro-hydraulic actuators. Yeah. These electro-hydraulic actuators are also hydraulic powered actuators, but they were controlled through by electrically signaled selector valves or electro-hydraulic servo valves. The valves so we have, they are called electro-hydraulic actuators. So the electro-hydraulic servo valves were copper controlled servo valves, or the other one in the selector valves we have solenoid control valves. And in the direct drive valves, we don't have the pilot valve concept, but they are solenoid. They are solenoid of these pneumatic hydraulic actuators are widely used today. We can see in 90% of aircraft use that type of actuators. That's working. Hello. Previous slide, please. So the hydraulic actuator is fail safe as it reverts to a default damper mode on failure. That is the advantage of this hydraulic actuator. But both hydromechanical actuator and electro-hydraulic actuators require an aircraft hydraulic system, requiring lengthy pipelines, because as the aircraft increases, the pipeline has to be very long, down, and we end up with the problems of leakage, contamination, and there is a requirement to keep costly maintenance infrastructure. If you want to maintain a hydraulic system, the infrastructure to keep that is also costly because it has to be a dust-free environment and all those things. So hydraulic fluids are also not environment friendly. This is another problem with the hydraulic actuators. Next slide, please. So this is just a schematic showing how hydromechanical and hydraulic actuators are working in principle. That is, we have a hydraulic fluid contained in a reservoir. Then it will be pumped to higher pressure. Then we will have a relief valve to maintain the pressure in the system. Then we will have the control valves, which control the flow of fluid to the actuator, to the pressure side, and to the return side is going back to the reservoir. So this is a basic principle on which a hydraulic system is working. Next slide, please.
In electro-hydrostatic actuators, they are, this is an intermediate step between electro-hydraulic actuator and electromechanical actuator. This is here, this is, you can call it as a electrically powered hydraulic actuator, because the power is, we are giving electrically. The other one was hydraulically powered. That is, we call it power by pipe, but here it is power by wire. So electrically powered hydraulic actuator. So here what is done is, EHI is a hybrid device where a hydraulic actuator is supplied with the fluid from a zonal hydraulic system. We don't have a complete aircraft hydraulic system. Central system is not there. But wherever an actuation is required, there will be a local hydraulic system consisting of a constant displacement pump driven by a variable speed brushless DC motor, and it is controlled by power electronics, all built into the actuator body. That is a local hydraulic system or zonal hydraulic system is there. And all the power is transferred given wire to the motor. So in so how is generated as per demand, signaled electrically or digitally, and there is no need for an aircraft hydraulic system. So the problems we have seen, that leakage and maintenance in this one, all those things are not there in this. Yeah, and EHI is also give high power density as in the other hydraulic actuators. So it is also a fail-safe feature. It has fail-safe feature because if one on failure, it will go to the neutral damping mode, and it will not cause any problem in that way. So EHI is used in safety critical applications also. Because of this, EHI can be used in safety critical applications also. EHI has been developed only 2 decades back, 3 decades back. Next. This is that electro-hydrostatic actuator. So we have a local hydraulic system attached with the actuator. Next. So then we have the electromechanical actuators. Here we call them as power by wire actuators, because there is no hydraulic fluid here. So we have only power by wire, that is electric motor. It has consists of an DC electric motor, and it has got gearing and a ball screw to power a linear actuator rod. This is in case of linear actuator. EMAs are now matured enough. The advancement in rare earth permanent magnetic materials and power solid state devices, power electronics, and the microprocess based control system. Electromechanical actuators were developed long back, but the problem was they were very heavy and low power density, and there were other problems also associated with that. So it was not able to compete with hydraulic actuators till now. So now with the improvement in the design materials and power electronics, they are able to challenge other actuators because of reduced system weight. That is, still the weight of the actuator may be heavier, but they are claiming overall system weight will be less, and there will be ease of maintenance and precision in control. This is the advantage of EMA, electromechanical actuator. So it makes easier power distribution and eliminates infrastructure required for hydraulic systems. And health, another good point of this EMA is health monitoring is easier with EMA. So this is another. So this is a schematic of an electromechanical actuator. We will have a motor, gear, and a ball screw because and running the linear rod. Next slide, please. So, but there are many major problems in EMA still to be resolved. One is the ball screw jamming is a major concern, preventing it in safety critical applications. Safety critical applications are FCS and landing gear. So, so far they are not used EMA because of these two reasons. This reason, jamming problem. Not reaching the flight safety reliability as in a good dual or triple redundant hydromechanical system. So still we are having this concern. Then another concern is low power density compared to conventional actuators. but weight saving is achievable at the system level. So that the overall system level will be able to still save some weight. Use of EMA was hence limited to secondary flight controls and other non-safety critical applications so far. But tomorrow's scenario may be different. This is a ball screw where we have used the ball and the screw. So the problem is the ball screw, there is a chance of getting it jamming. So that is a problem which is still encountered in this ball screw. Next slide, please. So there are other problems of EMA. They are need for lubrication to avoid friction in the ball screw. That is, it has to be kept lubricated. Then wear and backlash. So once it starts wearing, backlash will keep it. Then temperature buildup and heat dissipation. Because here in hydraulic actuators, heat dissipation is not a problem because the hydraulic fluid itself will carry away the heat and the hydraulic fluid can be cooled elsewhere. But here that is not the issue. So temperature buildup and heat dissipation is an issue. Then another issue is linear speed control.
Divakaran
Yes.
Chairman sir wants to tell some. You come to the point because most of the things we knew, but the last one, few points which you have on electromechanical, can you please summarize quickly?
Yeah. Electromechanical problem is snubbing more electric aircraft and all electric aircraft. So this is where we are using more electric aircraft technology. So they are called more electric aircraft and all electric aircraft you know, but everything has to be done electrically. Next slide, please. So some examples of more electric aircraft, you can see A380 and Boeing 787. They call more electric aircraft, and they have used EMA and EHA in many applications. Slide, please. So mitigation of problems in EMA. So to mitigate the problems in EMA, we have to do fault tolerant design, fault diagnostics, and improved maintenance. Next slide, please. Fault tolerant design aims at providing a coupling to clutch to decouple or provide a dual dependent EMA with the summing lever. This is the fault tolerant design. Next slide, please. In fault diagnostics, we rely upon prognostic health monitoring to predict the residual life. So this can be, there are two methods in this. One is model based, other one is data driven, or it can be a hybrid approach also. In model based, we depend on the failure prediction based on the physics of failure and failure rates. The other one is dependent on the data received from testing. So we have to do a lot of testing and collect the data.
Go to the next.
Yeah, next. So other one is improved maintenance. To keep the maintenance inspection more shorter and so that you can avoid any failure of the EMF. Next. So in landing gear actuation requirements is landing gear actuation requires high power, but they are high reliability and safety, should withstand ambient conditions. High power density is required, and there will be high compatibility with the electromechanical environments. So next. Here we need to have a clutch arrangements to decouple the actuator in case of jamming. That is the requirement. So and kinematic selection has to be optimized so that EMA can be used in place to achieve a free fall by gravity. That is, after the actuator is disconnected, the landing gear should be able to free fall by gravity, and that type of kinematics has to be designed. Next. So uplock, we can have electromechanical actuator, we can have two actuators to push the trigger. And in the absence of this, another problem is in the electromechanical actuator, there is no cylindrical joint in the actuator, unlike a hydraulic actuator. So it has to be taken care, the geometry should be such that to avoid torque reaction on this structure from this flies. Next. So for EMA for landing gear operation in RTA, it is feasible to use EMA. Only thing is we have to design the kinematics suitably so that it is possible to have a free fall in the event of disconnection of the actuator. So next. So here this is RTA, the landing gear will be like this, retracting landing gear and forward retracting nose landing gear. Next. So I have made a rough estimation of the power requirement. If the weight of the aircraft is 30 tons, landing gear weight about 1350. So peak of power requirement will be about 2.65 kilowatt. And the energy required per cycle will be about 20 kilojoules. Next slide. So here, this type of geometry is suitable for actuation with electromechanical actuator. We have a folding side brace and landing gear can come freely by weight. Similar thing for the nose gear also. Next. Similar. Here also similar folding brace and the landing actuator. You can have electromechanical actuator. Next. So this is so conclusion is EMA route for landing gear operation is feasible, meeting the airworthiness requirement of flight safety by incorporating required kinematic features in the landing gear design. With the present technology readiness level of EMA, it is competitive to hydraulic actuation in terms of overall system weight, maintainability, and has better environment friendliness. That's all. My presentation is over. Thank you.
Thank you.
Thank you.
Maybe one or two questions we can have.
Yeah.
Any question, please?
Some modeling.
Yeah. The concept is good, and maybe at least we can make some sort of a simulation and model-based this thing, and we can try. Concept is good. Electromechanical is coming back after a long time with these ball screws and all that we used to hear and study long time back.
Thank you.
Thank you very much, Divakran.
Thank you. Thank you, sir. Thank you.
Thank you. Thank you. We have now the next speaker, Mr. Jaydev, who will be giving a talk on electric environmental control system. Mr. Jaydev. Jaydev is a part of ECS group in CSIR-NAL, and he is very actively involved in all the ECS related work on both 19-seater as well as going to be the RTA. So Jaydev.
Yes, sir. Good morning, respected Chairman, Director NAL, Kotarina sir, and all the distinguished attendees and the participants. So thank you, sir, for my brief introduction. So the title of the topic is More Electric Environmental Control System for 90-seat turboprop aircraft. So if I see in the beginning of the conference, the major requirement to migrate to all electric aircraft philosophy is power saving. Environmental control system is one of the major power extracted from the aircraft engine in terms of bleed air. So in this study, we have taken the 90-seat turboprop aircraft ECS as reference, on which previous work has been carried by our respected chair. So on top of it, we added some mods and presented a study. So to the interest of all the audience, so we need aircraft environmental control system in aircraft for cabin crew and passengers to provide comfort and to maintain required temperature, pressure and humidity levels inside the aircraft. So here I am showing the important cooling cases normally we consider for a civil aircraft in the various flight segments. One is hot day ground static and hot day cruise are the two major cases which forms a basis for system design and selection. So this is the brief overview of aircraft environmental control system. It can be segregated into three subsystems. One is air supply unit, another one is air conditioning unit, and the air distribution unit. So air supply unit in typical conventional ECS system, it is the from the jet engine, where we extract the engine bleed and regulate to the pressure through the bleed air system. And the air conditioning unit is a set of integrated turbo machinery which regulates the high temperature and pressure of the bleed air to the required pressure and temperature of the cabin. And the distribution system consists of a main distribution LH and RH ducts and the panka louvers for the passenger comfort. Here I am showing the cabin heat load estimation for RTA 90. So for the ECS system selection and design, the major driver is estimation of cabin heat load, which decides the capacity of ECS pack. So for RTA 90, the estimated heat load is 21 kilowatts for hot day ground static at 40 degrees C. The major contributors of heat load are convection, convection through the metal surface of the fuselage and
Yes, now the requirement is not even 40, it has gone up to 50. That's what we have done in Saras Mark II. So
yeah, yes, sir. Yeah, okay, fine. So this is the generic graph which is showing the heat load variation across the across the aircraft platforms, varying from 50 to 90 and 150. So it will be around 15 kilowatts to 35 kilowatts. So here in this slide, I will quickly cover the brief overview of the air cycle mission, which is the crucial constituent of the ECS system. Typically, we have turbofan kind of system where engine bleed will be cooled through the heat exchanger and directly expand on the turbine. So this kind of system we see in the Dornier 228 aircraft, and we have two wheel where the bleed air pressures are relatively less. So we need a compressor. This is the system existing in Saras PT1 and Mark II. So another thing is three wheel system. Heat exchanger ram air, there will be a fan to drive the coolant air. This is we can see in ATR 42. And for RTA 90, we are looking something like four-wheel system where we have a dual stage expansion for better performance. So coming to the conventional versus more electric ECS, the major difference is in conventional ECS, we extract the engine bleed air, cool it through a pre-cooler, and ECS pack will condition the air as per the requirement of aircraft cabin. Whereas in more electric, the engine source will be replaced with a compressor which takes atmospheric air and compresses to the desired variable pressure ratios as per the flight operating point and provides to the ECS pack. This compressor is driven by a DC motor with variable speed drive. So now I talk about the actual study that has been done for RTA 90 in terms of more electric ECS. So this is the architecture, that preliminary architecture that has been proposed for RTA 90 aircrafts. So the fuselage will be conditioned using two ECS packs. Each ECS pack will be receiving high pressure air, two compressors. Each compressor will be driven by a motor with DC motor with speed control drive. The reason for two compressors per ECS pack is in case of one compressor failure, still we will have sufficient mass flow rate for passenger comfort. So this is the typical proposed architecture for ECS pack for RTA 90. So as mentioned, this will be a four-wheel system with a dual expander in the ECS. So coming to the main study, the main basis of whether more electric ECS is suitable or the existing system is suitable, we have conducted fuel penalty study. These are the assumptions that have been, major assumptions that have been considered. So on HP bleed, pound minute of bleeder extraction, it leads to a penalty of 1.55 pounds per hour of fuel penalty. On LP, it is less, 0.55 pounds. Shaft octane penalty, where we need to take this parameter for electric compressor penalty estimation, it is 0.245. Equipment weight will have a 0.057 pound per hour weight of equipment. Another thing is for conventional ECS, previous works have been carried out. We have system performance weight estimation to the preliminary level. We don't have a weight estimation for the more electric for comparison. For this, we have taken the study done on Boeing 787 published in Society of Automotive Engineers, where they have compared bleedless, that is more electric, and conventional ECS. As per the study, if we take for Boeing 787, system weight is 560, ECS weight will be 560 pounds, which is 1.27% of max takeoff weight. If you migrate to all electric, it will lead to a weight increase it will be 880 pounds, which is 2% of max takeoff weight. So the major takeaway from this slide is for the same aircraft, if you migrate from conventional ECS to electric, there will be a weight increment by 1.57 times. This factor has been taken in our study. So to estimate the actual fuel penalty numbers, apart from the assumptions made, we have considered typical flight mission for two scenarios. So the flight mission is 3 minutes taxi, 10 minutes climb, 90 minutes cruise, and 10 minutes landing. The difference between mission A and mission B is in mission A, complete all the flight phases are ECS will run on HP bleed of the engine, whereas in case B, during cruise, which is the majority of the flight segment, ECS will be powered by the LP stage of the engine. So as per the system design requirement for all the flight segments, the bleed air requirement has been established. Taking 1 pound per passenger, we need 95 pounds at taxiing, and during cruise and descent, it is around 75 pounds. So this is the summary of the fuel penalty study for case A, where the complete ECS system is powered on HP bleed of the engine. So if we compare the conventional versus electric ECS, so conventional ECS leads to a fuel penalty of 340.3 pounds for this mission, whereas more electric ECS is leading to a fuel penalty of 257.8 pounds. So in this mission, we can see there is a fuel saving of 82.5 pounds achieved by migrating from conventional to more electric ECS. Considering the case B, if we can operate the cruise on LP, if we see in SARAS, we operate the complete mission profile for ECS bleed on HP. Whereas there are scenarios across the aircraft platforms where cruise is operated on LP also. If we consider LP bleed, the penalty is 227 pounds, electric is 257.8 pounds. In this scenario, it looks like conventional ECS on cruise on LP bleed has a little edge over electric ECS. And I will talk on the comparisons and conclusions about these two scenarios in the conclusion slide. Yeah.
Just a minute, just a minute.
Yeah.
No engine.
Yes, sir.
No, no.
You have to optimize that.
Yeah. Yeah.
It's not more electric, it's all electric.
Yeah.
No. 1 minute. If we are talking about a normal conventional power plant and we have to perforce use only HP, okay, for exercising or for powering the ECS, then we do have it fuel saving. Okay. Now, if the power plant can give me enough pressure to drive my ECS at the LP bleed, then it's only a touch and go, because we have taken 1.5 times the weight, which also adds to penalty. So it's a question of where, we need to have more engine data to do. Now, what?
There is no engine now.
That's fine.
So, only electric is the.
If it is all electric aircraft, then the fuel panel, then this paper is irrelevant.
No, the fuel saving what we have done.
Yes, sir.
Is converted into equivalent energy.
Yeah.
And that is well. Okay.
Now, if we are talking about all electric aircraft, then the fuel penalty doesn't come into picture.
Then the equivalent energy saving is there.
Yes.
I don't have to put so much of energy in my back. This is there.
And please remember, the ECS takes most of the energy. We need 1 kilowatt per passenger. So if we have 90-seater aircraft, I need 90 kilowatt to power my ECS. So that has to be considered while we are talking about. See, we have to study the all-electric propulsion in totality. We can't say, that only we need yeah. So I need 90 kilowatt of power to drive my ECS. Okay.
Yes, sir. So a good point. So yes, sir. Yeah. So coming to that development of more electric ECS, the ECS packs, already technology is existing. The only thing that needs development is compressor with motor with a DC motor with speed control drive. So we have estimated the preliminary power estimation of each compressor, which turns out to be 58.24 horsepower on hot day ground static scenario. On hot day use, it is around 40 pounds.
Yeah, 1 minute. You
Yeah.
come to the challenges.
Yeah.
It's fine.
Yeah.
There are many more challenges,
Yes,
even
yes.
if we go for all electric aircraft.
Yes, sir. So, coming to the conclusions and the challenges, whatever the study we have presented now, it needs to be revisited in detail, considering the actual penalty of the proposed engine for RTA, and also whatever the LP bleed looks little beneficial needs to be again revisited by taking the actual engine bleed data. The major challenges are development of high-speed high pressure ratio centrifugal compressor which can deliver constant pressure at all flight conditions. Our analysis shows that the pressure ratio on hot day ground static varies from 4.1 to 5.22 at this flow rate. So we need to develop a high-speed, high-pressure ratio centrifugal compressor on air bearings technology for this application.
Now, just a minute. Now, here I want to stress a little bit more. The major challenge in all electric ECS is the development of a centrifugal compressor. Now, these systems are constant flow systems, okay? We normally design ECS for a constant flow system, more or less. The problem is when we compare from ground cooling to high altitude cooling, the pressure ratio varies from almost 4.1 to 6 is to 1. To get 6 is to 1 from a single stage centrifugal compressor with constant flow or slightly varying flow is a major challenge, number one. That compressor is a high RPM compressor on coil bearings. I'm just throwing these challenges so somebody can pick up and start working on those technologies. Number one. Number two, it's a motor-driven compressor. So motor per se will also work at high RPM. What sort of coupling we have? Do we have magnetic coupling? Do we have a normal coupling? Number one. Number two, the compressor and motor set will have to be on coil bearings. You can't use conventional bearings because your RPMs are of the order of 90,000 to 100,000 RPM. So these are the few challenges which I thought we must mention.
Yes, sir. And the development of DC motor with precision speed control.
Yeah.
So this is the
Sir, if we don't go, why we go for high RPM? We will have this long diameter compressor. Yeah. We want to reduce the size. We have worked out preliminary sizing I have done for the centrifugal compressor. Even at 95,000 RPM, I am getting 4.1 inches wheel diameter. If I reduce the RPM to 50, it will be this big. Can't have space for that much. That's the point. In fact, and yeah.
Yes. Yeah, that's the end of my presentation, sir. Any questions? Yeah. Again, I take this.
More. Actually, we have already anticipated the questions and answered.
Yeah.
If there are any more, one or two we can take.
Yes.
Yeah, please.
Yeah.
Sorry? Sir, it is available, not available. There is a very thin line between. We have done, we'll take it up. We developed a foil bearing technology. I don't know, there is nobody from Lucknow way back in 1980s. What happened, sir? Even today they are doing. Today. Please listen. Can I just? We have a foil bearing technology even in propulsion division, but at 30 to 40,000 RPM beyond, it has some problem. Okay. So we have to work on it. All I am saying is, yeah.
Yes, sir.
We are not able.
Sir has some question.
Yeah. I mean, this is a relevant question today. See, in air travel is today considered risky from a COVID point of view, right?
Yeah.
So, because you are an air conditioning engineer, is there a way to consider the airflow pattern so that the air around each passenger will flow like a shower, will not mix. That's like it may, if you know this, it may also reduce your it may also reduce your load.
Now we have basically we go by the minimum certification requirement.
Yeah.
And that is what we have to meet. We don't, we can't compromise on that.
Okay, sir.
Thank you very much, Jaidev. Thank you. We have next lecture by our friend from Lucknow on electric braking system. An overview.
Hello and welcome to the presentation on an overview on electric braking system. I am Vibhor Asthana, Chief Manager Design, ASERDC, HAL Lucknow. At ASERDC, we had developed wheels and brake systems for all indigenous platforms as well as one external platform. And we had also taken up some preliminary studies with IIT Kanpur on electric brake system. So with this background, we'll start the presentation. So we are going to cover the introduction to aircraft brakes, what are the existing brakes we have. Then since we are going to imply a new system, we should also know the advantages of this system. So we're going to cover some advantages of your electrical brake system. Then we're going to discuss about the construction of electric brakes. Then if you have a hydraulic brake and you want to convert it to electric brake system, what all modifications are required. So we'll try to generate one equivalent electric brake system. And then we'll see what all are the challenges, the considerations in electric brake design. And above all these aspects is the user experience. So we'll also touch upon what all we need to take care to enhance this user experience. So starting with the introduction of the brakes, aircraft brakes are used to stop the aircraft in the designated distance, that is your runway distance. Then during taxiing also you need to limit the speed of the aircraft. For that we require brakes during taxiing phase. Then aircraft can be steered also with the use of differential braking. You have different braking on left and right brakes. Next, the brakes are also used for holding engine thrust, and of course for parking these brakes are used. For holding engine thrust and parking applications, the heat sink is not loaded. In rest all other conditions, heat sink is loaded. So now that we have seen the use of brakes, let's see the construction of the brakes. Any brake for that sense will have two systems. One will be your brake actuation system and the other one will be your heat pack and the supporting structures. The brake actuation system can be hydraulic or can be electrical, so it will be different for different systems. Whereas when it comes to your heat pack and supporting structure, it will be similar for both the brakes. You'll have your heat pack, that is your stator rotors, then your wheel assembly, top tube and thrust ring, as well as some spreader plate and axle bearings. So this will be common for both the brakes. So whatever we need to do for electric braking system is in this brake actuator system. So if you see the basic construction of aircraft braking system, this is explained in slight detail here. You can see you have your stators, rotors, the stators that are coupled to your top tube, and the rotors are coupled to the wheel. So they'll rotate along with the wheel. It depends on the brake how many rotors you have, 2 rotor system, 3 rotor system. So the more the number of rotors, more the number of interfaces that will create your braking torque with the same and load. So this all depends on your design calculation, how you are deciding the loads. The double stators will have friction surface on both the sides, so they will be slightly thicker, whereas the stators at the end would be slightly thinner. So they are called single stators or thrust stators. Then you have a system for uniformly applying the end load. So on one end where the actuation system is there, there you have a spreader blade that will spread the actuation loads, because you see in this diagram we have 4 actuators. They can vary to 6. So it depends on the design, what we have in the space constraint and the end load required. So, and on the other end, the reaction side, you have some mechanism to react the load, as well as you have a requirement that the line of load should not vary too much. So here in this configuration, we have shown thrust cones. So you have equally spaced thrust cones all along the circumference, and there would be a thrust ring that will provide the resisting end load. Here your top tube will be taking thrust loads as well as your torque. But it is not necessary that your torque calibration, how the landing gear is being attached to the wheel brake, it depends. So it may or may not carry torque, but yes, it has to be designed for the end loads. Then you have 2 circuits in a hydraulic system that would be required in electric brake as well. One is the input from pilot and metered down by your anti-skid, and then you have an emergency line that also caters to your parking side. So this is a shuffle ball that will decide where you are feeding the pressure, and accordingly the brake actuation will be carried out. Before we move on to any system, we need to know the advantages that system offers. So let us have a look at the advantages of electrical braking system. Electrical braking systems offer better reliability and redundancy. They lend themselves for quick assembly as well as repairs. You can simply plug and play those things, and whatever you're trying to repair, they are all modular. So just remove the thing, affected part, and simply screw in the new part. And maintenance is also very easy, as it comes on condition maintenance. Then this system is resistive to hazards like oil leakage, sealing, and fire, because it is all electric. So oil lines are all dealt with. So these hazards are not there. Then you can achieve considerable weight saving with the elimination of all hydraulic line systems. So as compared to brake alone, you may not achieve that much, but yes, as a whole system, considerable weight saving can be achieved. Then since it is all electrical systems, you can better integrate with health monitoring system that are now we are planning to equip on our aircrafts. So overall, electrical brakes offers us advantages that are not possible or difficult to achieve in hydraulic brakes. Coming to your brake schematic for electric brakes, it is a general schematic, and actual may vary slightly, but yeah, the basic principle is being listed here. So this will give us a fair idea how the system works. So you have a pedal potentiometer that is a direct input from the pilot. It is 2 systems, 1 and 2, and then you have a DC power supply to a electronic control unit. This electronic control unit is a part of signal circuit. Then this electronic control unit also has the input from wheel on weight sensors, both LH and RH, and it also takes input from your wheel speed transducer. So basically this ECU will decide if any skidding is happening or not. It will calculate, and then it will lower down the torque signal to the motor controllers. So this ECU will send your the torque requirement command to motor controller. That motor controller in turn is connected to your DC motors. So if you can see the coupling here, the left motor controller, the motor on the left side is coupled to 2 actuator motors on your LH side and 2 on the RH. Similarly, the other motor controller also coupled to 2 on the LH and 2 on the RH. So this objective of doing this thing is to achieve redundancy in case one of the motor controller fails. So the one of the motor controllers can decide the braking on both the wheels. although the load has to be increased, so that will be taken care of in the design. Also, in the event of a failure of your electromechanical actuator, this redundancy will be established and the load will be shared by other actuators. So this motor controller, you have a different power circuit, so because this will be all power circuits, whereas the above will be your signal circuits. Now let us have a look at the construction of electric brake system. So electric brake system consists of mainly four parts. One is your electromechanical actuator, that is comprised of a DC motor and a gearbox. Then you have a motor controller and an electronic control unit. This motor controller and electronic controller unit can also be clubbed as a one unit, but in principle they are two different units because they are part of two different circuits. One will be your signal circuit, other will be your power circuit. Then you have a electromechanical actuator carrier. So in this diagram that as we have explained earlier also, so here you have a ECU with inputs from pilot input, weight on wheel sensors and wheel speed transducers. Then the signal is sent to the motor controller and motor controller here drives this motor number one. Then you have a gearbox, that is this, shown by 2 and as well as 3. 3 is your ball and screw that will convert your rotary motion to translatory motion. And then 4 and 5 are your rotor disc and stator discs. Yeah, of these four basic units of electric brake system, the motor controller and electronic control unit are part of your aircraft systems. So as such, they are not part of electric brake system, but yes, they are part of aircraft systems. Coming to the heart of the electric brake construction, we have your electromechanical actuator. This electrical mechanical actuator is comprised of DC motor and a gearbox. So here we are covering the DC motor. So DC motor has to be a BLDC motor with a angular position sensor. You need to sense the position in order to drive it. Then the requirement is very stringent from this motor. We require a very high torque compared to the size of the motor. So it should deliver a high torque to size ratio. Again, since it is being used in a brake, it should be robust and have a long operating life. The brake temperatures can easily exceed around 1000 degrees centigrade in case of your carbon brakes. So the interface ambient operating temperature has to be something around 150 degrees centigrade. Below this, it will be difficult to contain. Then it should be capable of delivering variable torque with same efficiency. When you talk of the torque rating, it is a cumulative design point. So it has to be decided based on your gearbox ratios and end load requirements, even the number of actuators that you're planning to use, or maybe what you can fit in. The space is a major constraint here when you come to brake design. Then motor RPM will depend on the response time as well as the gearing ratio, how much reduction in speed you are taking from the gearbox. So this response time depends on your motor RPM. And now the most important part is your how do you provide this end load. You have two options. Either you can stall the motor at continuous torque rating, because once already the disc has been pressed against each other, you do not have any further axial motion. So that means your gearbox will be locked and in turn your motor will stall. So the motor has to stall for the whole braking cycle, say 30 seconds, 25 seconds, whatever is the braking cycle. So one of the options could be you can have a clutch there, which will, but the clutch has to transmit variable torques. So this is the most important design point of this motor, how it has to be achieved. Coming to actuator part of the electromechanical actuator, this is slightly straightforward. It comprises of a gearbox and an actuating piston. So the motor torque is converted to end load in this actuator. The gearbox is coupled with the available space, whatever ratio you are planning, it has to fit in that space, the end load required, and as well as the motor torque. As you have told, it is a cumulative design point. So all these things need to be fixed in perspective, how you are able to fit it. The ball screw arrangement is used to convert this rotary motion to translatory motion. And again, your gearbox should be able to deliver the variable torque requirement as communicated by the ECU. Coming to the execution portion of it, we have the motor controller that is part of the power circuit. The motor controller's basic job is to control and monitor the LDC motor. It has to execute the current and torque requirement as set by your ECU. Motor controller is responsible for your engaging and disengaging brake. As soon as the foot pedal is released, the brake motor has to be reversed, and then brake has to come back to its original position, taking into account any wear and all. So then it should be able to execute redundancy measures in case you have failure from one of the controller. The other controller should be able to take over. Then each motor controller should be able to independently control each motor, so that, as we have listed earlier, you have each motor controller is attached to two to the LH side and two to the RH side in a 4 actuator configuration. So in case you want differential braking, so this motor controller should be capable of achieving that. Now next is the brain of the system, the electronic control unit. It is part of the signal electronics. Now it should be able to convey your torque requirement to motor controller. It decides how much torque is to be applied or govern the current to the motors. So this governs the motor controllers basically. And then it takes input from weight on wheel sensors. So it should have a touchdown protection. The braking should not happen before the aircraft is landed. So it takes signals from your weight on wheel sensors. Then it has to offer your locked wheel protection. So for that it takes input from your wheel speed transducers. So basically it functions as an anti-skid, has to be performed by the electronic control unit. Then any differential braking requirement has to be communicated to the controller and motors. So ECU decides how to do it. Then you should also have an anti-skid override at low speeds. So at low speeds, this anti-skid should be disengaged. So that also is a part of the electronic control unit. Then since it is doing all the input from all the sensors and all, so this has to be integrated with the health monitoring systems. So they should have a built-in capability to test its system and then deliver it to the HMS, main HMS. Then in case of any failure is seen, the redundancy has to be taken over, and execution of the redundancy is also a function of this electronic control unit. So this is the most important part of the system as it controls the performance of the system. Next is your electromechanical structural part that needs to take your end loads and sometimes that torque load with heat sink because your torque tube will be interfaced with this. So thermal aspect has to be taken care of in this only. Any heat loading air generated by the motor has to be dissipated through this carrier itself. Then it also distributes and loads uniformly since you will be arranging your EAs in this. So the arrangement has to be symmetric so that the loads are distributed uniformly. Now to create an electric brake system, just you need to remove this actuation area of the hydraulic brake and replace it with your electrical actuation system. So as in this figure we can see the electric brake system has been interfaced with your heat sink system. So now this should function as the electric brake. So now let's see the challenges that needs to be addressed in electric brake design. So from the motor controller and torque requirement point of view, the motor has to offer a high torque with the size. So that is a major constraint, finding a motor that can deliver the required torque in that available size. Then you have to have precise control in terms of motion and torque because the end loads are generated based on your motion only. So that has to be very precise. Then you have to combine multiple inputs from your anti-skid, your pilot demand, and then you have to decide the torque that's generated and then has to be communicated to your actuation system. Then what we talked about was providing meter torque in stalled condition or use of a clutch. Then the major requirement is that once the braking cycle is finished, the actuation system, the piston is pulled back and the preset clearance is maintained between the spreader plate and the piston. So that mechanism is there in hydraulic braking system. You use the tandem compound pistons arrangement there. So every time any wear happens, so the piston is moved back by the same amount. So that mechanism has to be built in the electric brake design as well. From the gearbox side, you should have a consistent gearbox performance. Again, size is a consideration, working environments. Then you need to have a lubrication mechanism that ensures a constant friction coefficient, because if friction coefficient changes, the end torque will change and your end loads will change. So it is a concern. So that has to be taken care of. Then electric brakes also prone to mechanical jamming. So that is also needs to be addressed here. So that is the challenge with the gearbox performance. Then you have the thermal considerations. See, hydraulic brakes do know that hydraulic actuation system does not produce any heat of its own, considerable heat. But here, electric motors, when will be running in installed condition or slipping through a clutch, they will generate a lot of heat based on the torque requirement. So that needs to be dissipated. So mechanism has to be in place to do that. Then you have, since electrical wirings are not there, so that insulation integrity also needs to be addressed. Then some provisions for cooling of the motor can be put in place. As we already told, the heat pack temperatures can already exceed an excess of 1000 degrees centigrade. Then this positive clearance that we already explained above, like when it's moved back, it has to maintain the clearance, so that has to be taken into account. Then one of the important requirements from a brake system is the parking mechanism. So hydraulics, they have emergency system and parking brake system in which the accumulator holds some pressure and that can be used to apply a parking brake. Whereas in electrical system, it would be slightly difficult, as when the aircraft is powered down, there won't be any power to apply the torque. So we need to have arrangements from some friction locking of the motor shaft. So it applies the parking torque, parking load, end load, and then the motor shaft is locked, and then the power can be shut down. So that has arrangement has to be brought in. Next is your anti-skid and response time. The anti-skid logic has to be built in by ECU, as we have discussed already. Then response time, you will have, since we're using a mechanical gearbox, you'll have some backlash in gearbox and mechanical inertia. Then so that has to be taken care of in the response time. So for digital response, that around 4 to 5 milliseconds, that what we are talking right now for anti-skids. So that has to be communicated through this gearbox. So that is the consideration here. Then you have your backup system in the case of power failure. How do you ensure a consistent power supply that will provide you with this required torque, or the algorithm that will be built in ECU? So that has to be taken care of. And just to give the idea of it, for our Saras Mark II platform, the total end load per brake for normal braking is around 22.3 kilonewtons. So this should give you the idea how much load the EA has to generate. So based on this, as we have seen that a lot of load will be required for the EAs if you dump all the energy to the brakes. So it is better if you use some other methods that can reduce the load on your brakes, so that you have more efficient brakes, electric brakes. The use of thrust reversals, air brakes and spoilers, drag chute if possible. Then relaxing some space constraint for e-brakes is also a requirement, because finding so much miniaturized motors and gearboxes would be difficult. Next, coming to the user experience, this is a major thing, because if you design a system that is not functional or not functional as per expectation of the customer, is of no use. It's only of academic consideration in that case. So the user experience is a primary factor. Response of electric brake should be similar to hydraulic brakes. The user is habitual to a hydraulic system. So your brake feedback should be linear with the pedal movement. That is, and then hydraulics have some inherent damping characteristics also. Braking action is smooth, and the response time is less. So that all thing has to be replicated on the electric brakes. So that is also a major challenge or consideration in the design of the system. So this brings to the end of the presentation. So to simply just quickly conclude this thing, we have discussed the design of both hydraulic and electric brake system is similar, and just it's a difference is in the actuation system part of it. Then electric brake system is more reliable, consistent, modular, and easy to maintain. Major challenges also we have seen electric brake system. The major challenges are the size, thermal, and control logic, and of course a parking mechanism. So a lot of people have done it, and we are sure that we will do it too. Thank you, and we'll be happy to answer if you have any questions. Mail ID is also listed in case you need to reach to us for any query.
Sir. Questions to be put.
You made a statement that much efficient you have electrical braking compared to conventional. If this is so, I have never found the real I could have played they also put that one quality. Secondly, the way you explain this stuff, it looks much more complex which actually I use that. So correct designing electric aircraft and still give the hydraulic braking and make a small power and self-contained there itself and use it by electrical power. So it can be electro-hydraulic braking. That's much simpler. When if I do all the digital benefit, these two are related, both are independent.
Sir, can you just repeat the question, sir? We are not able to get it properly. The voice was breaking.
Yes, sir. No, they're unmuted, sir. They have got a part of the question.
Okay. Sir, can you repeat it? So since you have the mic, can you repeat it, please? We are not able to hear it properly. So
Right now, but usually you said it is much more efficient to have electrical braking compared to hydraulic braking. I don't know, but if this is so, then we have it for a conventional. Why do I have full braking that case? Because there is a power level.
it is not audible, sir. Sir, can you repeat it, sir? Okay.
So this is the second time.
Can you please repeat the thing, sir? Since you have the mic, your voice is clear.
Okay.
Sir, actually, we are not able, we are not getting clear voice message.
Voice is clear, Mr. Asthana?
Your voice is clear. Yes, sir. Yes, sir.
Now voice is clear?
Yes, sir. Yes, sir. Yes, sir.
Yeah. What is Goel's question is, you have made a statement that electrical braking is more efficient than hydraulic braking.
Right.
In current aircraft, it is not used.
Sir, actually, presently, in that case, we have to make a full electric aircraft. As on date, we don't have all electric aircraft. If we build all electric aircraft, then electrical brake can also be used. So using electrical brake on a conventional aircraft is not feasible, sir. That is the one main reason.
No, the question has to be taken in a different spirit. Let us say today we are having a hydraulic braking system.
Right.
And the brake system goes into the hub of the wheel. Okay, everything gets managed into that, and the hydraulic comes as the input. Now, if you go for an electrical braking, and the way you are shown on that actuator, ball screw, gearing, bevel gear, and all that thing, is it accommodatable into the same volume? That is his question actually. So,
yes.
Yeah.
Please continue. Sir, it is possible provided we have the resources that we have asked for in the presentation. We have shown some challenges. Actually, we tried to develop one prototype also. But since we faced the challenges, everything was not available as of now. But yes, we can fit in. So actually, the major challenge in electrical brake is the difference in the use of motor. Actually, all the other actuators, we have a motor working when they are in motion. In electrical based system, motor has to install and then it will be doing its function. So as the motor installs, the
as the motor installs there are a lot of I square R losses. The motor coil gets heated up. That is one challenge. And the second challenge is that for the mechanical actuation system, it should be backlash free, because eventually you require looking for 3 to 4 millisecond response time from anti-skid signal. So the major challenge remains getting electrical motor which is capable of working in stall condition, and second is that getting a mechanism which is backlash free.
Okay. Okay.
Thank you, sir.
Yeah. Okay.
Okay. So in case you have any questions, if you write to us in email, we will be able to reply better, because we were not able to get the message.
Thank you, Vibhor. Thank you. Thank you very much.
Thank you.
Sir, it is the same braking. Yeah. Okay, fine. So we have the next talk by Dr. Amitabh Saraf on more flight control system. Dr. Amitabh.
Good afternoon, everyone. So it's a pleasure to be here talking about, more electric flight control system. The only thing which is really not electric in a flight control system primarily is the flight control actuator. So I just changed the topic to more electric. Okay. Yes, like that. Okay, so I basically talk about flight control actuators for more electric aircraft, talking about the emerging technologies, challenges in migration, and way ahead. So what I had actually planned for this presentation was to give a little brief on various. Why is this not moving? Okay. So I was initially planning to talk a little bit about how electrical actuation differs from hydraulic actuation, application of electrical actuators so far, evolution, and what kind of challenges are faced. But I think this part of it has already been covered in the previous talk, so I'll not spend too much time on that. We will quickly come over to the case study, which is trying to understand for RTA. If you take RTA as a case study, what is the kind of actuators we need, what kind of weights are required, what kind of power requirements are there, and stuff like that. So, okay, so now this particular work has been done by our team. They are the experts for making actuators for LCA. And I would request Nagesh also to join with me, and he will talk about this case study in more detail, when we come to that. So this part has already been covered. Just a better picture to explain to audiences what, how over time the actuation system has migrated from hydraulic systems to the actual mechanical actuation, and in between the process of hydrostatic actuators. But I'll not cover that. This portion has also been discussed, that overall in terms of various parameters that we look at, which are the when we look at hydraulic system or the electric system, which one has what kind of advantages. So again, I'll not spend time on this. Little bit of history, in the sense in service aircraft where electrohydrostatic actuators or electric backup hydrostatic actuators. As we see over time, people have started experimenting and trying to put these all electrical type of actuators rather than the hydrostatic actuators. So if you look at Airbus A380, which came in service since 2007, we have about 24 hydrostatic actuators. Hydro servo actuators, hydraulic servo actuators. 8 of them are electrohydrostatic actuators, and this is the electric backup hydrostatic actuators. This was in A380. In Airbus, it has 12 of them are still hydrostatic, hydraulic servo actuators, and the electrohydrostatic actuators are 4 of them, and 4 of them are EVHAs. And like this, we see over a period of time, more of these electric actuators have started playing a role in the aircraft industry, and we are getting more of them incorporated. However, still there are several challenges. So most of the actuators still continue to be in the standard hydraulic servo actuator domain. So different types of EMAs, the geared ones, which are the linear actuators, the geared ones, the direct drive ones, and the ones which are the rotary actuators. So essentially, inherently, they have a much better position accuracy, higher control bandwidth, and speed independent torque limiting capability. Sorry. Okay, so now the EMAs actually are getting more and more popular over time. The primary reason for that is as compared to hydraulic systems, the commanded position and speed over time can be changed to reduce impact loads and fatigue of the actuation system. So as the innovation progresses more and more, we are getting much better bandwidth. What you see in this green one is the electromechanical actuation system, which has a much better bandwidth as compared to the hydraulic drive systems, as well as it's possible to tune the requirements so that overall fatigue and the impact loads can be reduced. The other innovations which are happening over time is we're getting magnetic gear units which have the inherent torque limiting feature and the absence of mechanical contacts as well as play. So this is something which is coming up, and we need to work on this to get it incorporated in our system as well. The servos, sorry, the transducers that we have for the sensors that we have for getting a better control over the position of these actuators. New concepts are coming up using giant magnetoresistive effect transducers, and they are able to give much better accuracy. It removes the need for LVDTs in the system, and it can become a completely standalone sensor system available with the actuators themselves. The major problems with electromechanical kind of actuators has been the redundancy management part, which is how do we develop systems which are fail-off, fail-off, fail-safe systems. So a lot of work has been going on this. This is just one of the examples where the overall redundancy is achieved by actually having different 4 different motors along with their braking mechanisms. There are 4 motors driven by 4 different control electronics and the various commands which come from the different channels of the flight control computer. The actual mechanism that it has a differential gearbox, so that even if there is a jam in one of them, the whole system continues to operate. And the design is such that out of the 4 channels, even 2 of them are sufficient to completely drive it. In case of the further failure, it's possible to break the system and hold the flight controls surfaces to its neutral position. We already have talked about various innovations that are happening in the permanent magnets, which helps in getting low rotor inertia as well as good dynamic response. Then essentially what's happening, I will just summarize what we have seen. The electromechanical actuation using BLDCs is a possible alternative to electro-hydraulic actuation for many applications. The real problems are for the jamming that can happen and the redundancy which we require. So that also a lot of work is happening to make it better and better. In terms of sizing, which is what we are going to talk about now for the RTA as an example, the important things which we look at is essentially the load velocity curve, which has to be, at different loads, what kind of velocities that you require from the actuation system, overall frequency responses. And in this particular case, even this duty cycle has become very important for determining the size of the actuator. Highest external load, of course, determines the stall load and the loaded velocity of the actuators. Thing which has to be taken care of is the motor, the coupling ratio itself. So a higher coupling ratio results in a smaller motor to meet a specified load velocity slope. And the limitation comes in terms of the maximum current that can be put into these PLC motors. So duty cycle is important. This is something which is something to be taken care of when we go for electromechanical actuation systems. Essentially, because of the coil temperatures go up when the duty cycle is high, continuously operating thing produces more heat. So there is a requirement that the whole actuator design gets determined not just by the load curves, but it also by the kind of currents and the temperature that gets generated into these coils. So now I'll request Nagesh to please join me, and we'll talk about the case study that we have done for electrical actuator design for the RT.
Yeah, good afternoon, sirs. Thank you for the opportunity. We have just done a preliminary, I would say, a rough order of magnitude kind of study on the preliminary inputs what were available for the flight control surfaces of RTA, considering EMA as an option which is to be studied. So I'll just go through in these are the aircraft picture which is showing all the control surfaces here, the elevator, ailerons, rudders, the multifunction flaps, and the trailing, the trimmable, the horizontal stabilizer, which is all moving surface. So what we did was, as the primary requirement, or normally what we consider during our design is that the primary flight control is for the pitch bowl and the yaw axis, and command stability and augmentation in all these three axes. And secondary controls, we are taking it basically through the spoilers. And the kind of redundancy or the PLOC, probability of loss of control, we are aiming that 1 in 10 power minus 9. That is what is the commercial aircraft mandate which is to be taken. And this calls for a kind of a system which will be fail off, and fail safe kind of a system. So here the flight control surfaces number, what we have done is pitch control is through the pair of elevators. The horizontal stabilizers provide the trim capabilities. The roll control is through the pair of ailerons. Rudder is done through the yaw control. The yaw control is through rudder. And the flaps which are there are used as high lift devices, and there are 4 multifunction spoilers which are also used for the kind of that ground dumping which are required for the landing purposes. So in fact, we studied from the configuration what the conventional one to the migrated one. So the first configuration essentially says here is that 2 hydraulic servo actuators per surface, and it is purely driven on the hydraulic way. Yeah, I'm coming to that, sir. Just a slide, the migration. Exactly.
Yeah. So one part was to look at what is the kind of power requirement we have when we have different systems. So that is what is the main focus.
What are they not available for requirement? I think that the development, political protection, leadership.
So we'll come to that.
Yeah,
We will come to that.
I'll do that thing. So I'll just keep out this. So here I'd like to just tell that last point, sir, that is, if we go for an all electric option, 15.5 kilowatt will be the kind of power drop out of magnitude what we are looking for.
Nagesh, what you are telling is if we go for EMAs, we need 15 or odd.
Yes.
So that
was the point what I wanted to tell is that. Yes, sir. 1 HA, 1 EMA, sir. No, but the point what I want to make here is the primary flight controls is essentially to be driven while we say EHA. Yeah.
I can have a fully hydraulic system. driven by a motor. Driven by a motor. Motor is electric.
Yeah, exactly.
Take. But motor is there in the open house. The camera. Safety to brake also. But we have to see what is the optimum way, what are the alternatives.
When
They can look at workshop to look at alternate. That's what they are doing. But we send to them. Okay.
We are listening. There's a small question. Configuration fee. Why it is one EHS one?
Sir, I'll tell you why. I'll tell you what is my apprehension. EMS is a technology where jamming and all other things have to be mastered. So today EHA, when we say, it is also an all electric actuator only. It is that power by wire locally to that.
I don't accept that. You cannot say that you have EMA which is prone to jamming. There's no talent.
No, not that.
What you are saying? See, what happens is when you talk to sometimes in the large vehicles or satellite, we do that. If there's no new technology which is strong, we want to test it with that point, not because it is a problem. It's a problem not to do it.
No, not that.
No.
When we say EHA, and our understanding of EHA is, it is all electric. It is that we connect the power directly at that. It has a localized pump, a localized small.
Yeah, instead of taking the central hydraulic system, the local hydraulic pump, it is driven by the electric. They are just asking you your mind.
Yeah.
Why 1 year and why 1 year?
Yeah.
That's all you answer.
Yeah.
You don't get further.
So if you can see here, the primary controls were primarily shown with EHA and with the EMA as a backup.
Why technology backup? See, you're not getting. You are buying hormones from different technologies, any failure. You make any system more reliable.
Yeah.
There's no error for that.
Yes.
ठीक है. Okay.
There are issues, there are problems, there are problems. We'll discuss that. Why EMA did not introduce so much. We'll discuss that. There is a reason for that. The technology was not available. Now only it is available. I don't understand that. People in aircraft business, they are not too sure about the technology. They say, I will have a proven one and not so proven one. Later on, I will change over. This is how it is done.
Okay, Nage.
One next stuff I would agree.
Yeah, that's what we're talking here. After you build confidence, you have done about 1 million hours of flying. Then I will.
Sir, EMA will take much more studies on reliability. That's why one EHAMA has been given there. Yes. So many other problems are.
Told about the safety. Then he said, I'll do a better Please go ahead.
Okay, so sir, in terms of the power and the typical hinge movement capabilities, these are the typical numbers what we have worked out, which eventually, if I go for an EMA actuator, it will take about 1600 watts for aileron. Rudder, it will take about 2250. That is, these are the kind of numbers what we have worked out from the sizing perspective. And
So these are peak powers.
The peak power, you should really look for average power. The average power is very important to know.
Yeah, this was only for the sizing of the actuator part that we have done. Yeah. So it is not a continuous requirement.
He's not talking about that total energy requirement.
Yeah.
Come on.
Yeah. In terms of the weight, yes, this is the kind of typical weights what we are going to have for the particular actuators.
And so this particular thing has been done based upon different literatures that is available. Typical sizes depending upon what is the energy requirement, and then from that scale down to what we may require for RT.
So this is actually showing the control surface configuration in terms of the flight computer to this. As already Dr. Sarab had covered this. This is that two channel, and then two channels are driven with one side of the actuator and the other side of the actuator with two other channels. And in terms of the failure rates, when we consider, these are the kind of failure rates what we have typically taken to arrive at that the PLOC, whatever I had earlier showed you, in terms of the bus interface or the power control unit or the control loops to the rest of the connected links. And overall, for a kind of elevator, this is the kind of typical number what we get when we cumulatively add the whole loop of our numbers for the PLS.
Yeah, so sir, these calculations are also done just to get a feel for what kind of reliability we can expect from the system.
Showing reliability with EHF.
Yeah, yeah.
When you introduce 1 EMA, what is coming into our questions are
correct. So the problem is for EMAs currently there is not so much clarity in terms of index computation. Right now, answer is not there. We will have to work on it, sir, to generate.
We are putting that okay, but there is a way of finding out the reliability, otherwise from algorithm better.
Yes, sir.
Correct. We have got EMA, and then how many parts, how many moving parts.
Correct.
From that,
yes. Right, sir. It has to be done. We haven't really reached that level right now. Whatever was straightforward, we could present it right now, but that needs more work.
Carry on.
So by telling all about the requirements and the configuration, the typical specifications, if you would have taken a 28 volts power output, would be something like, with reference to this, would be an output power of around 0.6 kilowatt. And if it would have gone for a 270 kilowatt, 270 watt power availability, these are the numbers what we are having in terms of the sizing with reference to the motor currents and as well as the power with reference to 28 volt as well as the 270 volts if there is available made on the aircraft. So mainly I think, sir, I think this was more a requirement slide from the perspective. So today, sir, as we all are aware on the TRLs, we are having a very good understanding on the BLDC motors and the transmission. These are very clearly understood. Where we have problem is in terms of the power drive electronics, the motor control technologies, and the thermal management. This has been talked about earlier by our earlier speakers also. And it is the same thing what we are also telling here, that we have to improve upon in these areas for reaching our end goal on all electric actuation systems. So way forward, what I felt was like, the BLDC electric motors are very clearly understood by our friends at RCI, NFTDC, VSSC, IT, Bombay and all. So the first two are more or less an achievable platform with reference to when we migrate to a flying platform aircraft, wherein which work has to be done in terms of the endurance, meeting the endurance requirements. Like, the one-shot operation to this one, when we do, that is more challenging. In terms of the other aspects like the motor control technologies, IDT, pumps, all these things, we have identified certain the people who are relevant in this field. We have to take it forward over a period of time. We will achieve all these milestones to meet the requirements of humans. Yeah, what we felt is we can bring these teams together to work upon as a kind of consortium or joint work. Yeah. But even our VSC or Biju sitting here, they have also done quite good amount of work with Vita Technologies and other people. There are not many people around. So that part is good, sir. But then the power drive, only thing is we have to have that endurance capability for longer duration. We have to test it for longer hours, loading capability. All these things are the ones which I think that is where the connect is really to happen. To know, bring it to the transport aircraft.
Yeah. Okay.
So that's all, sir. We are concluding here. So takeaways are that the fault tolerant design and with the deterministic health monitoring are the key enabling technologies. Highly dependable electrical power, once again, and electrical power to be designed that will have a region capability wherein which when there is a load back drive that could be taken and backfed to my battery to generate the power. And in terms of the power management, we have to have a very good understanding to use for a longer durations, 28 volts and 270 volts, with the temperature management and all other things. And no, what I wanted to tell in that case was, in case of hydraulic power, when the load comes, it just damps and then the energy is lost. What I mean to say is, I can take advantage of that loading back and put back EMF and then power the batteries.
Yes, sir.
Oh.
You are in autopilot. You are at some angle also. You can take power out. So that time your braking system is depends upon it depends upon what you are doing. Because once you are in autopilot, you will be able to take more or less power cannot one rudder. That is elevator, keep the aircraft steady. That you may be taking it forward. So that just look at every your idea is okay.
Fine, sir.
Thank you, Nagesh, and
thank you, sir.
There are so many questions, it means you are excited every question.
Yes. Any more?
That is the whole purpose of this today's session.
Okay, any one or two exciting question? Offline, okay.
100 emails are with us.
Yes. It's a good study. Good study. There are some things to be added. EMA,
Okay.
My suggestion is supposed to do someone should do in your library for somewhere.
For the EMA.
Library to the library.
Yeah.
That's what they do.
Yes.
Will do.
Thank you very much.
Thank you.
Okay, so this brings us to the end of this session. We had 4 eminent speakers who spoke about various important subjects like landing gear, environmental control, brakes and wheels, and flight control. Some broad architectures were given, and way forward challenges and all that were shown, and a lot of work to do. I will only add one challenge is the thermal management. I can tell you the way we have recently seen all those scooters exploding on the road is only because of not enough attention given to thermal management. We had, sir, in the case of Tesla in 2013 to 15, number of explosions took place, and then and Boeing 787 is an example. 2 years the aircraft was grounded because thermal management was not addressed for lithium iron battery pack. So thermal management, which rightly shown as level 2, has to go to level 6, and that's going to be a challenge.
Story so far. We have to learn how to do thermal management.
Yes.
For the whole exam.
Yes, thermal management will be the key issue in all these new advanced technology aircraft. Thank you very much.
Well, we can't question with the chairman.
Sir?
We made a statement, not question the chairman. We made a statement. Environmental control required 1 kilowatt per man.
Per passenger. Yeah.
Average dissipation by one human being is around 42 kilowatt. Heat dissipation by human being is around 40 per man, around 41.
Yeah.
Why should I need 1 kilowatt per day?
Because it is not only metabolism which is adding heat into the cabin. We have solar, we have electronics, we have electrical, we have metabolism. And to remove that heat with the added inefficiencies, we need 1 kilowatt. No, that is not for civil aircraft as much, because civil aircraft cooling is mostly because of metabolism and solar and electrical. Fighter, you are right. Fighter, we have cooling requirement mostly from kinetic heating. You are right actually. But civil, we have a different requirement. Civil is different, sir.
Sir, thank you.
Thank you very much.
Thank you very much for interesting and interactive session.
Good afternoon. We are starting session 3, which is one of the very important sessions on electric motor and the powertrain. A lot of debate and discussions have taken place in this area because this is very crucial for all electric aircraft that we have been discussing. We have 4 talks here. The first one is on power electronics and electric drives for electric regional transport aircraft by Professor Sudarshan Karthik. He is himself is a associate professor at IAST Thiruvananthapuram. He has a team with him who are specialized in different aspects of power electronics and electric drives. And the second talk is on electric motor and powertrain technologies. That is from Viju Prasad from VSSC, who is a pioneer in developing the electromechanical actuation system for entire launch vehicle. And the next is again they have brought industry also as part of this session. Dr. Karthik Sitapati is an industrialist. Himself has done PhD and then has done a lot of work in the electric motor design and simulation. He's from Vita Technology Private Limited in Bangalore. I think they will give the perspective from the industry point of view. The fourth lecture is also from one of the startups, I think, our industry, Dr. K.V. Narasimham, Pontian World Private Limited. That's also one of the important topics that we are going to cover. So I would request all the speakers to stick to the time so that we are able to, we are there in 25 minutes time. And what I request is let us bring the points that are relevant to the discussion rather than giving the general areas. We can try to avoid that. So with these viewers, let me welcome all the speakers and request Professor Sudarshan to take over and go ahead with your presentation.
Thank you, sir. Good afternoon. So this is going to be the overall scope of the presentation. When we talk about powertrain, there is an inverter, there is a motor, and there are certain auxiliary converters which have to supply power to the environmental control systems. So this overall theme will be covered in 4 topics. Myself, I'll be covering on overview of the whole system, then go into some of the specific details of power electronics. And the motor specifically will be handled by Viju Prasad, and motor fabrication details by Dr. Karthik Sitapati and by Dr. Narasimha, the future. So this is just the textbook thing. You see that the requirement for the power density is going up. Whenever we see from general purpose motor to EV drive to future aircraft propulsion motor. Currently, we are around 5 to 7 kilowatt per kg, and now we have to up into 13 kilowatt per kg. And the different technologies are used for this. Even within the conventional motors, we have so many ways to classify the motor, and whatever be the technology that we adopt, finally we end up with the last option, that is the PMSM with additional reluctance torque, what we call as interior permanent magnet motor with additional torque which we get from the synchronous reluctance mechanism of that. So there are several names by which that motor is in the market. Some people call it as PMAC motor. Some people call it as permanent magnet assisted synchronous reluctance motor. Whatever it is, this is the motor that we kind of end up with in terms of the topology when we consider the conventional motor technology. While looking at this tree, DC motors obviously has a problem of reliability, so we are not considering it. In AC motors, there is asynchronous and synchronous. Induction motor is one viable candidate for Hansa application, where we are talking about power levels of 100 kilowatt to 120 kilowatt, that power level. The biggest challenge there is how do we cool the rotor, because rotor has currents, it heats up, rotor is a moving component and it's difficult to cool that. But when we go for synchronous technology, there is permanent magnet reluctance type, there is very minimal heating in the rotor, so that problem is solved, but stator still gets hot because it's the copper conductors in the stator who carry currents. So the last row is the one that I would like your attention. So here I have listed motors that are currently used in certain products. One use case for for induction motor is the use in Tesla S or Tesla X model, where they have used 225 kilowatt SCAM, but that's squirrel cage induction motor. But later on they have moved to IPM CSIR-NAL, that is the latest vehicles come with that. Then for brushless DC motors, we have several industries like MGM, Monroe, Rotex, and so on. And similarly for IPM CSIR-NAL, this is the technology that I was talking about, permanent magnet synchronous machines with reluctance mechanism. We have MRAX, Siemens, and Rolls-Royce, which are currently working on that particular motor. Now, if we just boil down the whole motor topology into one equation that can represent its torque generation mechanism, is the torque that is generated can be divided into two parts. One is because of the magnet or the magnetic flux that is present in the motor. Other one is the reluctance torque. It is basically a balancing act between these two, and how do we optimize to get maximum out of the motor. Say for example, one design method that is used is we punch holes in the rotor here. So what is the advantage? We have control on the reluctance, and at the same time we reduce the weight of the rotor. But then when we punch holes, we are also losing out on flux. We could have placed permanent magnets there, but now it's just air that is present. So then we end up with this configuration, the third configuration, where we have permanent magnets to set up flux. At the same time, we have air gaps in the rotor to give us proper paths for our reluctance torque to act upon. So in this context of using synchronous machines, we have one set of machines which is traditional permanent magnet synchronous machines, where we are totally dependent on magnet torque. It has very high power density. Then another class where we don't depend on the magnet torque, but we depend on reluctance torque alone. The issue with this is the power density is quite low. So now this is the technology trend where we have magnet torque plus reluctance torque, and we are able to achieve reasonably high power densities. In fact, all electric vehicles, the custom-made motors are of this topology. One more specific motor that is capable of very high power density is the axial flux machine. The advantage is it is some kind of, we don't have a long rotor anymore, but it is almost like a disc. An important aspect here is it has very high number of poles, so it is very easy to get very high torque from the motor for a given cross-sectional area. And more details about this will be covered in the subsequent presentations. One technology which can be a deal breaker, especially for high power systems greater than 2 megawatt or so, is the high temperature superconducting motors. Yes, sir. So that is a class of, that is called an outrunner configuration. The topology is very similar to this topology. Could be permanent magnet. It is just a mechanical modification. So one specific advantage here in terms of high temperature superconducting motors is the problem that we had in the stator heating because of conductors carrying current is no longer present here. There is very minimal thermal load that is going to be generated, and the rotor also has superconductors embedded in it. So this part of the rotor, see, this is the stator that has semiconductors, so there is no heating. And in this rotor, we have superconductors placed. So instead of air gap, we have superconductors placed, which means we still have the independent, or we have the control over how the flux goes, and we can depend on the reluctance torque of the system. So here I have put the winding, how the winding looks like, and it is claimed that the current densities of 500 amp per centimeter square is possible, and magnetic field intensity of almost 16 to 20 Tesla is possible with the superconducting magnets. And for a static application, this has been proven. Now let us go into the next aspect, that is the motor controller, and we'll go into a little bit more detail in this aspect of the powertrain. So when we talk about motor controller, it has an inverter which has all the semiconductors, DC capacitors, bus bars, sensing, and thermal management, and isolated gate drivers, multi-channel sensors, signal conditioning, DSP. Everything put together is what is called a motor controller. So one important thing here is the reliability of the electric motor is proven to be very high, but the reliability of the controller is at least one order of magnitude lower. So we have to bring certain amount of redundancy in the system to match that kind of reliability for this aircraft application. So here I am presenting a survey of what are the available motor controllers for power levels around 100 kilowatt, which is the use case for Hansa. And here I have given the power density metric. There is one candidate here, which is HBC 400, which has very high power density. And again, the important aspect is this power density is calculated by excluding the thermal management system. So it is possible that at the end of the day, when we look at it from the system perspective, we would end up with a fairly low number, probably around 14 to 15 kilowatt per kg. So again here, none of these motors have reached the TRL levels of even 4, but here we have a list of motors which are capable of a few megawatts of power. So here, whatever efficiency is shown, that is all considering the motor is loaded to its optimal condition, that is the peak efficiency. And when we are operating the motor at a lower power, obviously the efficiency will drop. And here, one interesting aspect is, yeah, this company, Right Electric, sir? Yes, sir. Normal. Not. Yes, these are normal. Some motors are even air cooled. Yes, sir. Sorry, this is normal cooling, liquid cooling. Yes, liquid cooling. Not cryogenic, sir, liquid. This is for the motor controller, not the motor. Okay, now specifically looking at the technical requirements from the motor controller's perspective, Hansa aircraft has to handle around 100 kilowatts of power, 90-seater ERTA has to handle around 6 megawatts of power, and for Hansa, it is more of a design challenge than a technology challenge. How do we basically improve the reliability? How do we condense the system to get sufficient power density? And those aspects should be handled for Hansa, whereas for ERTA, it is more of a technology challenge. We have to work on the configuration of converters for the motor controllers and for the motor in an integrated manner. So these are the typical numbers that we have. And one technology direction which I would like to highlight for the case study that I will be presenting is use of silicon carbide switches instead of silicon. All the survey that I have made was based on silicon devices. Though at starting point, if you look at the peak efficiency, both are competitive. Even I would get 98% with silicon and 98% silicon carbide. But when I'm operating the aircraft in cruise mode, where the power level is around 40%, you would see a drastic drop in the efficiency when you're using silicon devices. In terms of for the 90-seater ERTA, the challenge here is we would need a very high DC link voltage. Otherwise, the current requirement would be very high, probably in kiloamps, 1.5 kiloamps or so. So only way to do that is go for a multi-level converter, either 3-level or 4-level, whichever is feasible. And that is because we are restricted by this silicon carbide or silicon switches, which has a peak blocking capability of 1.7 kilowatt. Now, if it is 1.7 kilowatt, we would have to maintain a nominal DC link voltage of around 1.2 kilowatt to have certain control margin and for the protection of the device. So that puts a requirement on the system to have a multi-level converter. So certain topologies that can be considered, especially considering this limitation that we have, inavailability of high voltage devices at this power level. One alternative is to use two converters. This is what is normally done, and this is what is called open-end wound motor. And the idea is you feed power from both ends of the motor winding so that the DC link requirement reduces to 50%. Suppose we are having a requirement of 2 kilovolts, then we can operate the system with 1 kilovolt with this particular topology. Another technology direction which we can consider is using a multi-level converter. So here I have shown a 5-level system. This is a hybrid converter, a flying capacitor as well as a cascaded switch. The advantage here is we are going to be switching somewhere around 500 to 700 amperes of current. And switching that kind of current at 1 kilohertz or 2 kilohertz is not a good solution because we will run into so many EMI and DMC problems. So in that case, going for a multi-level inverter means we are reducing the switching of each leg. That is one. And second thing is we have an intermediate voltage level where we will be able to get a much better profile for the output voltage. And third direction that we can consider from the electric machine perspective is the use of a multi-phase machine. So here also, by having additional number of phases in the motor, we are reducing the current per winding of the motor, which means we can operate with low current switches. Second thing is we have additional reliability increases because even if one winding goes bad because of short circuit or say insulation degradation, then we will be able to operate the motor with remaining set of windings and an improvement in torque level and so on. One difference, in fact, if you look at the technology trend, there is also axial flux machine that I was talking about. We can also operate that axial flux machine as a multi-phase motor as well. Only thing is we will have to have that kind of switching algorithm present in the motor controller to enable that mechanism. Now, in terms of semi-connected devices, so initially we talked about motors, then we went into controller topologies. Now I'm coming down to devices. There is this silicon carbide technology which is catching up. It is there. It was there in commercial sector and renewable energy sector for quite some time. But now with the new technologies, for example, GE and Mitsubishi are claiming that they have aerospace grade silicon carbide devices, which is a very welcome fact. So in that context, we did a short case study where we took a motor. The use cases are in Hansa with 100 kilowatt shaft horsepower, and we took a 20-pole permanent magnet assisted synchronous reluctance motor, which is the best alternative that is available with a very skewed up D-axis and Q-axis inductance. This is one of the very important design parameter for the motor. This just means that the reluctance torque is multiplied by the factor of 9 compared to LD equal to LQ. That is the idea here. So with this configuration, which we thought about, we did two case studies, two separate simulations with silicon IGBTs and silicon carbide MOSFETs, and the duty cycle and the load, the operational condition is for a typical hands-on mission. It was there, and this power versus propeller speed is corresponding to Rotax 912 motor. So this is, I believe that it will replicate the conditions of Hansa mission properly. And we took standard 6-pack converter with the thermal model of the IGBT or the silicon carbide MOSFET, and modeled switching loss, conduction loss, all the kinds of things which are specific to the device. So here, switching loss is a function of voltage, temperature. Conduction loss is, of course, a function of device current and temperature and so on. So what we found is this: at high power level, at 100% load, when we are operating at the system at 100% load, the efficiency of silicon IGBTs converter is 97%. For silicon carbide is 99%. There's a 2% improvement, which is not much looking at the options that we have for silicon, because we can easily add multiple silicon devices to improve this. But the yes, right. So the thermal management has to take care. But what is more interesting point that I would like to make here, probably I was blocking this. See the efficiency at 50% load, that is dropping to 74% in case of silicon. But this silicon carbide converter is more resilient to changes in the load. So though this simulation does not include stray losses or bus bar losses or capacitor losses, this gives us a baseline, what we can get maximum out of the converter. From that perspective, the silicon carbide technology is the best way to go. Another technology is gallium nitride, that is usually used for low voltage applications and high current applications. So I'm not considering it for electric aircraft. So this can be translated to an increase in the cruise time for that mission, and approximately 11 minutes can be gained by just changing the switches, and remaining system would be intact. Now, now that we have covered controller, topology, and switches, I would like to just highlight on some control aspects of motor. One control aspect, one important aspect is this is a permanent magnet mission. So the one that determines the torque for the mission is dependent on the current IS and the load angle. So if we increase the load angle, obviously the torque is going to increase. So it's very straightforward that way. So this is what is called load angle control. The problem that we have is it is non-linear. So there's a sine 2 delta term. So when this was the initial control method that was used and still being used in very non-critical applications where the phase of the motor is not very important for the control purpose. Another motor is called independent or decoupled control, also known as field-oriented control, where we can independently control the flux and the torque of the motor. So quadrature axis current controls the torque and direct axis current controls the flux, just as a takeaway. So we can underflux the mission, we can overflux the mission and still get good amount of efficiency out of it. And one challenge for the controller is large asymmetry in DMQ axis inductance. This large asymmetry also boils down to non-sinusoidal flux in the mission. So this problem arises because the flux in the mission is non-sinusoidal, and the controller has to somehow take care of it. Now, I would like to give some information about testing requirements for the drivetrain. So this conventional testing approach is that we have a dynamometer, which is again an inverter and a mission, which is shown here, and this is the electric drive system to be tested. We have a test mission, we have our motor controller which is driving, and both are coupled, and there is a drive inverter or controller which is driving this. This is the traditional setup. But now, when the development begins, this motor and this drive inverter is invariably developed in a parallel or a phased manner. So what happens is the inverter development should wait till the test mission is fabricated. In order to avoid that problem, now recently this power hardware in the loop testing philosophy is being followed by several EV companies and motor developers. The idea is we emulate the motor using a power power electronic system. So this power electronic system is an inverter and an inductor or an interface element. And then this is the system that we have to test. Suppose the motor controller is there. This would be a 100 kilowatt motor controller, and this would be a mission emulator which will connect to the motor controller. And this, the currents and voltage that this motor emulator system would mimic will be at the actual power levels of the system. One other advantage of this system, suppose we are dealing with 2 megawatt system for in the case of ERT, or one megawatt system, the power requirement for testing will be approximately 20% to 30%, because we can recirculate the power to this system. So long duration tests and tests where some faults can be introduced, all these things can be done with this particular emulation system. So key aspects for this test system is we cannot go back to the basics and use some parameter based system. It has to be a distributed parameter based model. Saturation, cross coupling, slot harmonics, torque ripple, cogging torque, all these are to be extracted from the machine's design, basically the finite element design, and then fed into the model. And this model should be emulated in real time. So here I have tried to visualize what is the variation of inductances and what is the variation of torque with respect to several of the parameters. So what this power emulator would do is it would detect what is the current present operating point, and it would look at this map, calculate what should be the current that is being drawn, and allow that current to the converter. So it would demand that kind of current from the controller. And this all has to be done in real time. It is basically a 6-dimensional system, but I'll just try to put that into 3-dimensional. So this is the tool flow. We have the motor design. We have the FEA model of that. From that FEA model, using multiphysics engines, we have to get these plots. What are the inductances? What is the electrical viewpoint of that motor? And then that is going to be fed as the input to our motor emulator. So here, this waveform, this is the predicted, then the red line is the predicted one and blue line is the experimental one. They don't match because we have been using the conventional models, the lump parameter models, but then using a detailed machine model with cross saturation, cogging effects, all these things, then we get a better match. And this is exactly what is required when we go for motor emulation. First thing is prediction, second thing is validation, and once the system is validated, we will be able to use it for different use cases. Second case, this is with the torque ripple that exists in the motor. It is not, as you see, it is not sinusoidal. And now the question is whether our testing system can present such non-linear, non-sinusoidal case for our motor controller to be tested, and that is also possible when we use a hybrid system. And this is how the overall system looks like. And automation can be done. We can give different drive cycles. I've shown drive cycle for an electric vehicle, but the mission profile for electric car, ERTA and HANSA also can be presented. Automation can be done, and the performance of the inverter can be evaluated. One important thing to do is, even if we call this as emulation, the inverter itself is being tested at the full power level. So that is the key takeaway. So here are some aspects about
you will have to speed up now.
Yes, sir. About the emulator control strategy. I just tell key takeaways out of this. We need a very detailed mission model. Then emulator should have sufficient bandwidth and sufficient power level to mimic all the non-linearities. And then the design of this coupling element is very important. So with this, I would like to summarize with some key takeaways. First thing is silicon carbide technology is the future. We have to adopt it. We have to look for aerospace grade devices and redesign our gate drivers, whatever the auxiliary systems to match that. That is point number one. Point number two is two technologies for conventional systems. One is the interior permanent magnet synchronous reluctance emission and axial flux emission. These are the future. We have to look at these technologies. And third thing is about the testing methods where we can use power electronic emulator to load the motor controller to its fullest possible extent and introduce faults and see its performance at full power level. So with these three takeaways, I conclude my presentation. Thank you.
Thank you for the introduction. We can take maybe one or two questions. Any question from yes, Dr. Roy?
I don't think inverter definitely possible, sir. Motor maybe with lesser efficiency it is possible in the first iteration. I'm not sure about the motor yet. But it is possible. We will get close. Yeah.
What is the only
Let's
stop.
Sorry. No, that is for superconducting motors. Yeah, super cryo cooler as well. Cryo. So the whole rotor is in vacuum with argon gas, and the temperature, the pressure would be around 10 power minus 5 bar. So it is very easy to cool. It's an integrated cryo cooler is what is planned.
The one thing which has come very clear is in Kota's presentation morning, we used to debate and discuss a lot on the power of the motor. I think today he gave a solution very clearly that if we use 2 motors, 3 megawatt, 4, 1.5, 6 means 1 megawatt.
1 megawatt, yes, sir.
And also he concluded that 6 is much better than the 2 or 4, if I'm correct. So that makes life a lot simpler, really.
Yeah.
So, now I think, this is the whole idea of workshop. You get a very good clarity and you can go back and work on that.
Yes.
Anyway, the decisions will come later. But I think situation is not all that difficult as we had imagined.
Yes.
Isn't it? That's
Yes,
what
sir. Yes, sir. The pod concept is something that we have to do seriously.
Okay, thank you, Professor. Now we move on to the next topic. It is Biju Prasad, who is a pioneer in development of the electromechanical actuator. Not only developed, tested, designed, they are all flying with different capacities. Over to you, Biju.
Good afternoon to all. First of all, let me thank the team for giving me this opportunity, specifically to Dr. Suresh sir, for giving me this opportunity to contribute to this very exciting and challenging project. I would also like to thank my young team in BSSC who did this work in the last 10 days, along with the other commitments. In this presentation, we'll see the global scenario of the electric aircraft and particularly concentrating on the motors. And I will also show one slide on the fault tolerant actuators EMAs, what we have developed with quadruplex redundancy for the Gaganyaan mission, that is for the man-rated vehicle and also the motors. And we have done a study on the type of motor and the power rating what we require for HANSA Nest NG as well as ERTA. I didn't go too much detail into the ERTA. Then as everyone was telling about the thermal design aspect, we have done some initial simulation studies for which IAST helped us in getting an evaluation package, ANSYS MotorCAD, that is a 15-day trial package, which seems to be very good. And finally, I will touch upon the design philosophy, how to develop this motor. First, we can make a subscale motor, then test and prove, and then go for the final one. That's the same way we did for the S200 system, which is the most powerful one, and also the qualification plan. I will not delve much into this. Okay, this is the evolution. If you see the aviation sector, starting from 1904, from 90s, the early 70s, people started working on the electric aircraft. The first one being MBE-1, which used a Siemens motor. And but then, as you can see, the change in launch vehicle technology also. That is after 2000, for all the new launch vehicles that is designed world over, started using electric actuators in place of the conventional hydraulic. The primary reason being the tremendous advancement in magnetics, that is NDFEB magnets, then the advancement in battery, and also the power electronics, the high voltage, high current, IGBT started replacing the MOSFET. So similar trend we are seeing in the aircraft sector also after 2000. The latest, for example, if you take the extra 330 LE, that is having a power rating of around 250 kilowatts, and E-fan also is in the similar range. And we are expecting a similar trend, an exponential increase in the automotive sector as well as in the aircraft sector in the next decade. That is a prediction in the next 10 years. Now, if you look into the kind of motors that has been developed, I'm just showing 4 motors. One is the one what was developed for the Cessna Caravan. That is giving an output power of 640 kilowatts. And you see the power rating, it is 3.2 kilowatts per kg, and the cooling is by liquid. This information is not available in this form. So it was like a puzzle in various papers, websites, and also we put all this information together. Then the extra 330L, that also uses a brushless motor, 260 kilowatts, and the power density is 5.2 kilowatts per kg. They have triplex redundancy, and oil cooling is used in both these motors. For the spirit of innovation, which is very famous, they use an axial flux motor, like what was suggested by Dr. Sudarshan Karthik. The power range, again, it's in the range of 250 kilowatts, power density 5 kilowatts per kg, and again, liquid cooling. The next one, MRAX, which is being discussed for HANSA. That power density is 9 kilowatts per kg. It's a question mark. We don't know how they will be achieving with liquid cooling. We need to know more about that because we see that as the odd one out. But the power range is around 380 kilowatts. Now, coming to our expertise, what we have in ISRO, these are the actuators what we have developed for the Gaganyaan program. You can see the motor that is the actuator, which is quadruplex redundant in motor, as well, that is motor windings, commutation, sensors, and also the feedback, that is a quadruplex LVDT. All these components were developed by Vita Technology, who Dr. Karthik will be giving that next presentation. So we work together to develop all these things. The power range starting from 1 kilowatts, that's for the cryogenic stage of human rated Mark III. Then for the L1 stage, 4 kilowatts is output. And for SSLV, the next small satellite launch vehicle also, we have 6.5 kilowatts. And S200 being the most powerful, because once flown, that will set a world record for that, because nobody else has flown EMA in this power range, that is 64 kilowatts. It works at 270 volt. All these actuators, we have redundancy, and wherein the coils are physically separated and isolated in the 4 quadrants of the stator, so that any failure happening to one coil should not migrate to the other. And all uses brushless DC motor. Now coming to the HANSA and ERTA, which we have been discussing from the morning. So our focus was on the design and development of electric drivetrain, particularly on the motor for HANSA and ERTA. For HANSA NG, we got the 3-dimensional model. That is the portion around the nose cone, where the engine is put and the propeller is there. We have an available volume of around 0.56 meter cube and a maximum allowable diameter of 400 mm. That was the design constraint for us. And the duty cycle, takeoff 68 kilowatts, then climb 46, then cruise for 1 hour, 29 kilowatts, and for the descent 4 kilowatts, and for the landing, that is just final flyer maneuver, 17 kilowatts. So totally around 1.5 hours of operation. This was the duty cycle. The present Hansa uses an engine with a gearbox. So when we go to motor, we will avoid the gearbox because we go for a direct coupling, and it increases the efficiency as well as it reduces the acoustics inside the cabin. And for ERTA, I was very happy when Kota sir was suggesting that instead of 2 motors, 6 is the best, because it, as Dr. Sureshwar sir was also saying, that when we are bringing down the motor from the power range of 3 kilowatts or 6 kilowatts to 1 kilowatts, I feel that it is within our 1 megawatt, sorry, 1 megawatt. I think it's within our reach. So our design philosophy, we'll go ahead like this. First, we have to choose a right motor because we have different types of motors like BLDC, synchronous motor, PMAC, induction motor. We'll select the right one, and we'll also select. We have to decide on the fault tolerance, whether it should be dual, triplex, quadruplex. Then the electrical winding design details. See that Dr. Karthik will be presenting on that in the next presentation. And I will present some preliminary thermal simulation results, what we did on the Hansa. And then the type of cooling, one person was asking about the cooling system to be adopted. And finally, the fabrication and realization, because if you are going to select the axial flux motor, fabrication is going to be a great challenge. We have to overcome that. And also the functional and environmental qualification that is required. Because when we are going to replace the engine, then I don't know whether we have to set new standards or the existing standards can be followed for that. Which motor to choose? We have a range of motors starting from brushed. Anyway, brushed is not the option here because it has its own spark and limited life. Brushless motor extensively used in launch vehicle technology. It is proven. But the problem is that the power density is 1 kilowatts per kg, primarily due to the trapezoidal commutation, wherein only 2 phases, for example, a 3-phase motor, only 2 phases conducts at any point of time. So we are not taking the full juice out of the motor. Then induction motor, it's anyway, again, it's low power density, as permanent magnet is not used here. Synchronous reluctance motor, here also, since permanent magnet is not there, the power density is low. So the best options, no doubt it is a superconducting magnet motor, but it has got its own technical challenges as well as the design challenge. If you see all the motors being developed, many of them are in the lab, still in the lab, but we can target for that. But going through the Kotasa's presentation, we have to really think on whether we have to go for superconducting motor for even RTA. There the power range is, the power density is greater than 10 kilowatts per kg. For permanent magnet AC motor, that is very much feasible. We can make it in a very short time frame. And the power density is also good, 6 kilowatts per kg. And it is in the range of all the other motors what we have seen through the literature. And here one advantage is that we can use an absolute encoder and go for a sinusoidal commutation wherein we can energize all the phases together at any point of time. So we can take the maximum out of the motor. Then the question is whether should we go for axial flux or radial flux. So what's the difference? All these motors what we see in the catalog conventional, that is radial flux motor, where we do the winding like this. That is, winding direction will be axial and the flux will be perpendicular to that will be in the radial direction. And the magnets will be sitting on the, for an inside rotor, magnets will be sit inside. But for an axial flux motor, the direction is opposite. So what we wind like this, so that the flux will be in the axial direction. So the winding is just opposite to the radial flux, radial motor, and naturally the magnets has to be positioned at the end for the electromagnetic effect. So since we have both the left side and right side, we pack with the magnets. And also this is an ideal choice for a high torque motor because we can take these magnets well away from the axis, so we can get very good mechanical advantage also. But one of the major challenges is that for a radial flux motor, we stack one, for the stator's lamination, we stack one over the other. It's very easy, do the wire cut and then stack one over the other, put adhesive and bond it, you get the stator. But here, to reduce the eddy current losses, we have to stack in like a one hollow cylinder, then over that another hollow cylinder. So then stacking construction becomes very complex. So we have to see that, but people have done that. Then the type of motor, as I told earlier, PMAC is the best option, both from the electrical loading point of view, also from the specific magnetic loading also, because we can go up, we can get up to 20 to 30 kilo ampere per meter for electrical loading, and for magnetic loading, we can reach up to 1 Tesla. And as I told, all the three phases conduct simultaneously. We can decide that axial flux PMAC with an appropriate cooling system will be the best option for an ANSA NG. But if we face any difficulty, we can go to the radial flux option also if it is within the weight range. For ERTA, axial flux PMAC or superconducting magnet motor, but then 1 megawatt, we have to think maybe superconducting may not be required. During the future of discussion, we can decide on that. Coming to the level of fault tolerance, we suggest that it's better to go for quadruplex redundancy because we have to tolerate one failure, at least one failure. So suppose if you go for a duplex configuration, you have to design the motor for 200%, because one coil failure, you will get 100%. If it is duplex, it is 150%. So the motor size goes up. So today morning when I was seeing the weight budget, it is very, very stringent. Each and every kg matters. So from the weight point of view, 133% design with one coil failure, you will get 100%. So once we cross the takeoff, then we have a bonus that if it is quadruplex, with available even 2 coils, even with one more failure, we don't have any issue. So that, in fact, once you cross that 30 seconds takeoff phase, then you can tolerate 2 failures. So for a case study, we did the design for a 100 kilowatts motor. So that with one coil failure, we get 75 kilowatts. That's a requirement for HANSA. So the motor was designed by Dr. Karthik of Beta. So these are the design inputs. And these are some of the preliminary thermal simulation we did on the ANSYS MotorCAD. What you see on the right side, the total losses for this motor is around 6 kilowatts coming from the winding loss. Then that is basically the copper loss, backhand loss of 1 kilowatts, and for the eddy current loss also around 1, total 6 kilowatts. With since this motor is sitting just behind the propeller, so it will get some cooling, force cooling due to the natural configuration. So we did a simulation that, and we found that the temperature is going to around 225 degrees Celsius. It was going to around close to 240 degrees Celsius. But whereas even for the class C winding, it can withstand only up to 225 degrees Celsius. So we have to do something over that. And if the higher the temperature, the chances of demagnetization also is high. And the resistance also goes up, it again adds up to the copper loss. So we had to go for a good thermal design. So what are the options? One is the stator body. Anyway, we can put fins, heat pipes, external liquid coolant jackets are possible. But if you put an external liquid coolant jacket, you are blocking that forced convection effect. So that is the disadvantage of that. And but end winding, yes, you can do an oil spray cooling effectively. That is very good. And also we can think of putting a thermally conductive epoxy compound, which we use in our launch vehicle program, because our usage is only for a few minutes, maybe 5 minutes or 4 minutes or 10 minutes. So this will suck the heat out of the coil, and it will protect well below its limit. Then slot cooling is another option. We mill the slots in the stator, and this coolant can circulate. And lit fire is another method in which the multi-strand, again multi-stranded wires are used to reduce the skin effect and to increase the efficiency of the motor. And also oil flooded stator also can be used. rotor cooling, hollow shaft cooling, spray cooling are also employed. So what we did was, we had the option of, anyway, natural convection is there. Forced convection is there. Then with forced convection alone, we found that it is around 240. Then forced cooling with fins is one option. That also we did. The peak was coming to 207. Then housing water jacket with forced cooling, that was coming to, peak was coming to 225. Then slot cooling with forced convection, it was coming, the peak was coming to 135. And finally, the slot cooling with N winding spray and forced convection. That is technically slightly complex, but we can make an attempt. I feel that it is possible. The peak temperature during the transient after the takeoff phase was coming to 118. But once after the takeoff, during the cruise, it is around 80 degree or 85 degrees Celsius only. So these are the,
can move faster.
yeah. This is one another concept what we have in our mind, that is a dual stator configuration. This is got nothing to do with the earlier slide. So this one concept what we will be studying, because we can use the empty space inside, so that we will have one rotor and two stators. So it is a dual stator configuration. That also we will see, and because the thermally we can this thermal energy can be dissipated in a much better way. This superconducting electric motor, as was mentioned earlier by Dr. Sudarshan, is one option for ERTA, but going through today's presentation, we may not have required that. And these are the quality standards. Why I am mentioning is that these are the, when we went through the list of tests or qualification required, these are the typical tests to be required. So the reference what we took was RTCA DO 160E. We have to see whether this motor can be applicable for this. And our plan is to make a subscale model of the Hansa, that is 110 model with 10 kilowatts, prove it, and then once the magnetics is proved, then the scaling up is not a concern at all. And we can test this both in the dynamometer facility, dynamometer, wherein the specific loading corresponding to the duty cycle of takeoff, cruise, and all can be simulated. And also, finally, we can do an integrated thrust and all with propeller also. And the development plan will be the study in the complexity of high temperature superconducting motors versus conventionally cooled axial has to be studied for ERTA. And the challenges related to the design of axial flux in the power range. Manufacturing this motor in the megawatt range also is a challenge. We have to find out which industries can do this. And the testing protocols and the setting up the dynamometer and the integrated test facility has to be worked out immediately. As a conclusion, we can say that the axial flux PMAC motor in the 100 kilowatts can be developed in a short time frame for ANSA NG. And the design, development, fabrication, and qualification of this can be achieved using the existing expertise available in our organization like ISRO, DRDO, NAL, and HAL. And flight testing of HANSA will bring a lot of confidence and impetus for the development of powertrain for ERTA. Axial flux using the superconducting magnet technologies can be the primary choice. Anyway, today we have to rethink on that for ERTA. And for this, technological partnership from IAC and IITC should also be pursued for this development. That's all. Thank you.
Thank you. Any questions? Anybody else? Yes, please. You have to use mic. It's not reaching here.
This motor developed to meet the propulsion load, or it is also will generate electrical power to meet the other?
Only for the propulsion. Only for the propulsion.
Only for the propulsion. So there are some requirements in the regulation. So some of the systems need to be powered by independent sources. So normally we use one generating system for the propulsion. Not from the battery. So the requirement is also there. The experimental activity is taken or it is still in the implementation?
So only we have studied last 2 weeks. Only we did the simulation.
Most of them are in study phase.
Study phase.
There is you can promote the development. There is how there.
heat will be taken away, separate will come back in exchanger, 2 kilowatt or 6 kilowatt, that can be done.
Yeah.
So we are doing some language and we are doing the gas becomes loss.
Hi. Yeah, you are right. Yeah, you are right. We have gone through the literature. There are a number of people working on that. So it is feasible. So good to know that people are working on that.
Thank you, Vijay Prasad. Now, let me call upon Dr. Karthik Sitapati, who is the Director of Vita Technology Private Limited, and he has developed number of motors for various aerospace applications. Over to you, Dr. Karthik Sitapati.
Good afternoon, everybody. Thank you, Chairman, for inviting me to join this committee. It's a great honor. I will be talking about the electric motor that was designed for Hansa as a initial, as a starting point. I'll be going into the details of the design. I will also be going into some of the different motors and what is applicable for us. So let me just go over the overview. We have background. The conventional motor, I mean a BLDC, which is typically used by almost all aerospace applications right now. What are the inputs that I provided to the thermal engine? We'll talk briefly about other conventional topologies, that is the rotor and motor topology. Brushless, permanent magnet brushless DC or AC motor. So a couple of equations will tell us why, which is superior, especially when weight and size is critical. And then the axial flux design. Around 10 years back, Vita has made a prototype. Some construction challenges, and then I will conclude. And also, before the conclusion, I will be just opening IEEE paper written by Chinese on an axial flux motor. And the reason I'll be doing that is the torque requirement is exactly the same as required for Hansa. That is 300 Newton meter. And Hansa requires the torque at 2,400 RPM. But the Chinese paper talks about a 15,000 RPM motor. Of course, we can modify that, take what we want from that. So the permanent magnets, why are we using? Because it has the highest energy density compared to an electromagnet in the same volume. This is the choice for applications where size is critical. And the BLDC is used because it's a trapezoidal commutation. It's called a 6-step also. Even though the back EMF need not be trapezoidal in BLDC motor, a trapezoidal drive will still deliver torque with slightly higher torque ripple, but that can be washed away by the inertia of the load. Sine drive schemes are used in advanced servo systems in machine tool industry where higher speed is required. And that's where the LD and LQ becomes critical. But in this particular application for Hansa, we are already designed for maximum speed, maximum power. So the LD, LQ scheme may not be necessarily applicable because LD, LQ is used in constant torque applications up to base speed and then constant power applications after the base speed is reached. So here we have already designed for the base speed is the max power point. So the LD and LQ may not be strictly important for this particular application. And we have AC and DC permanent magnet motors, radial and axial flux. So BLDC, this, like I just said, it was designed with a peak torque at higher speed. And the preliminary design was to test various parameters in simulations. And then the same stator can be converted to an AC motor at a second stage. The motor needs to work very closely with the drive. So right now there isn't too much, we have not worked together on the implementing the drive details. So I stopped with just a PM DC motor. This is the motor. I think Mr. Viju sir also showed the same motor. This was designed at 300 Newton meter at 2,400 RPM. And the holes are there for cooling. And rare earth neodymium magnets were used with 35 MGOE because they have a 200-degree max operating temperature. If we go to a 42 or 45 MGOE energy product, the operating temperature comes down to 150 and 120 respectively. And of course, we have used cobalt alloy for this, which can handle up to 2.5 Tesla, whereas the silicon steel will handle maybe 1.8 or 1.9. So the motor was designed analytically, and for validation, second order finite element analysis was used. You can see the mesh generation generated on partial, we need only 1/8 of the motor because of symmetry. And there are approximately 60,000 nodes, 30,000 elements, and 4,000 edges. 3 air gap layers, where the air gap is where the torque is produced. So a lot of attention is given to the air gap. I don't have a picture of this zoomed in on the air gap, but there are 3 air gap layers. And on the OD, we assumed the magnetic potential to be 0. And on the edges of the geometry, it's a Neumann boundary condition. So basically, it's the same thing repeats on both sides because this is one pole pair. Here are the no-load finite element analysis results. On the right side is the flux density. On the left side is the relative permeability of the entire cross-section with the flux lines. And you can see the magnet is almost like air because the relative permeability of magnet is just a little larger than air, 1.05 or so. And there is no saturation at no load. Coil produces, this is a loaded, the loaded condition. You can see from the left that the permeability is quite high everywhere and there is no saturation. One thing I forgot to mention now, you can see the bifurcations, that is each
pointer is there. Is there a pointer?
Yeah. You can see the bifurcation here on the teeth. You can see that clearly on this side. That is because of the cooling pipes. We are not going to skew this stator. So the cooling pipes can be inserted straight. If we have a skew, there will be a helix and the cooling pipe can't make good contact with the stator. So the rotor thinks there's 196 into 2. That is 192 slots are there in the stator. So the cogging will be very less without skew. So what was provided to the thermal engine was the copper loss distributed over the slots, core loss in the stator teeth and the stator yoke. The eddy current loss in the magnets has not been modeled yet, so we could not provide that loss, but that will be 3% or 4% of the total losses. Rotational losses, that is the bearing and windage, were not provided. We need to define the cooling method, and that is still unknown. The other rotor topologies for the AC motor is the 3 cross sections I have shown you. The magnets are buried, and one of the benefits of doing this is flux focusing. Higher air gap flux density can be obtained rather higher than the magnet's remnants. And the top, the one is called a buried spoke type. This one is a buried surface type. And on the right side is something that I personally call a lotus type because they look like a lotus and very high flux density is possible in the air gap. And in the right side, the lotus type of rotor, there is a large difference in Q-axis, D-axis and Q-axis inductance. And this would be very good to drive the motor in higher than base speed, which is not necessary for us, but we might end up in a rotor like that if we choose a radial flux machine. Now, the permanent magnet DC or AC, it's I will skip the first few lines. The torque is proportional to current times KT in a brushless DC motor, and only 2 phases are conducting. But for the same KT, the torque is going to be I1 plus I2 plus I3 times KT, but the currents are displaced by 120 degrees. So the KT is also displaced by 120 degrees because that KT basically in SI units follows the same waveform as the back EMF. So we have both KT and I displaced by 120 degrees. And if we multiply it out, we get the last line, we get that equation, and that turns out to be 1.5 times current times torque constant. So theoretically, practically, we may not be able to pump so much current. We may have to pump slightly lower current due to thermal issues. But it is possible to get 50% more torque when we use sine wave and use all three phases. So obviously we need to use a AC drive for Hansa. We can't go with a BLDC scheme. We have to go with a BLAC scheme. Finally, I just want to talk about the axial flux design. In radial field motors, the general equation for output torque, okay, that's not an equation. I'm saying the torque is proportional to d squared L, where L is the active length of the motor and D is the air gap diameter, not the outer diameter of the stator. Whereas in an axial flux motor, the general equation is torque is proportional to d cube, and that d is not the air gap diameter, it is the mean diameter between the OD and the ID of the magnet. So the larger the diameter of the rotor, the torque is proportional to the cube of the mean diameter of the magnet. So that is the fundamental reason why the axial flux has such a high power density. It's very clear here. And then 10 years back, we have made an axial flux design. And I have brought it here to show you. Viju sir, can I request you to please show the committee members at least. The rotor and stator are separate. Can you please put on the light?
Lights can be on.
The rotor and stator are not joined together because this is a single, the rotor is only on one side. So if we join it, this is the, what, sir, you can take it out, sir. So this is the stator of the sample I have brought here. This thing on the left is lamination strip rolled between the ID and OD. So it is axially, it is radially laminated. And once the silicon steel was rolled tightly, it was welded on the OD and ID, and the slots were milled. What you see, the solid lines are the slot opening. And here the slot cross section area is the same from the ID to the OD, because the same number of conductors are in the slot. But the teeth, they increase in area because the magnet increases in not the angle stays the same, but the length of the magnet, the area of the magnet increases in higher diameters. So the teeth also are increased to handle the flux. Now, before I go to the last slide, which is my conclusion, yeah, I just want to show this. This is, I think, the committee, the organizers will make this available to anybody, this paper. What we require is 3D finite element analysis, both thermal point of view and electromagnetic point of view. What they have here is, this shows two types of axial flux motors. I'll just focus on the one of them. So to reduce the losses in the magnet, they have used segmented magnets. That is on figure C. That means the magnet is not a single piece. It is segmented and insulation is applied between the magnets to reduce the eddy current loss. And also, this is a yokeless axial flux machine to reduce the losses. And one of the highest power density axial flux motor manufacturers use for aerospace, it's called Magnix. I don't have there, I should have put something from their website here. They are also using yokeless. So the only ion are in the teeth in this topology. The ion, there is no back ion losses at all. And to cancel out the axial forces, they have two sets of rotors. And here, two sets of stators in this topology. You can see that there is only one physical stator connected together by a thin section. And there are two sets of coils, one inserted from the left end, one inserted from the right end. And then there are two rotors. So the magnetic forces are balanced between the two rotors. The bearings will feel only the differential axial force. So I think this is something that we should look at for Hansa as well as maybe for the electric, for the regional transport. I think this is not mine. Sorry. Oh yeah. So I think more discussions when I wrote this, but I think it's getting more clear that we should be moving towards an axial flux motor, maybe a dual rotor, dual stator with the yokeless. Let me just go back to the see, this is the 3D finite element analysis that they have done. So on the right side, the four machines, they are all very similar. There are four machines. I showed you four cross sections. There were four different machines. It's a 300 Newton meter. So this very similar to Hansa's power range. And he has also given us the size of the machine. And he's also has a photograph. What I don't understand is how they have assembled this. On the left side, you can see the machine. But I think with so many mechanical experts around, that shouldn't be a problem. But we have a very good starting point already because somebody has done something extremely close to the Hansa's requirement. And we can, if we have a dual stator design, it is easy for the redundancy also because each stator can have 50% of the power out. This paper can. So we have many construction challenges also. We might end up with a different topology. And for the RTA superconducting materials may be used. And one of the things for the problem with the axial flux machine is if we go with back iron, we can tie the cobalt alloy and mill the slots. And then we have to untie the cobalt alloy and then anneal it. And then after annealing, applying adhesive to create the insulation, rolling it back into the axial form, tooling is extremely critical because if there's any misalignment, the slot openings will start shifting. So that's all, and thank you very much.
Thank you. Any question, anybody else? Yes, Dr.
Make some power you have designed and put any time you want to produce. Make some power you have.
Sir, I think over here the maximum power would be the S200 motor, which is what is required is 65 kilowatts, but that is capable of 80 or 90 kilowatts. It was slightly over.
Yes. Cooling may not be much.
Yes.
From industry point of view, you're running for hours and all that.
The 20 kilowatts, 30 kilowatts. But it again finally depends on the size. If the size is not a constraint, you can make it much bigger and it will run very cool.
For Hansa.
No, that's what. So for Hansa, this motor which I showed you, whatever simulated, was 92% efficiency was guaranteed. So this is the first iteration, just playing with it a little bit. Anyway, it's a simulation on a computer. It takes few hours, that's all. So we can up it to 95, 96. It is because the output is 100 kilowatts, even 1% is 1 kilowatt of loss. So
there was no requirement of cooling anytime so far. Once the requirement comes, that can be addressed here.
And even the yes, sir. No, even the actuators for VSSC, we do thermal testing. We inject DC into the current and see what is the time constant. We switch off the current when it reaches around 120 degrees centigrade, and we have up to 1 minute.
No, one step for aircraft. The outside. Normally, inside. Somehow I was reading somewhere that outside you get much more advantage in terms of the aircraft application.
So
And
that,
look at that part.
yes, that is called the outrunner motor. That's called the outer rotating motor. The problem is cooling. That is a problem because the stator is inside the rotor. If we have a good cooling mechanism, we can look at that also.
We can. I'm asking because see, anyway, the big part outside means popular now.
Yes, but that is what Biju sir showed the concept with the dual stator. So we have outside stator and inside stator also. If we remove the outside stator, it becomes the outer rotating motor. So that concept he showed a slide.
Can you look at it? The efficiency of the overall the popular application.
Certainly, we can look at that, sir.
Even the launch vehicle actuators, although in the actual usage it's only for a few minutes, but during the simulation, when you do actuated loop simulation, continuously it will be burning for hours and hours actually. Nothing we have observed in any of those cases. Because isn't it, in all actuated loop simulation, sometimes 1 day, 2 days, 3 days, like that, continuously they'll be running to complete the total simulation and get the data with multiple dispersion combinations.
90% life is
That won't be used for any other purposes. They have separately kept it for those purposes, but that's a very good test where you get some kind of experience on that really. It's not just only 5 minutes, 10 minutes, even earlier also it was like that actually. Okay, thank you very much.
Thank you very much.
I think we now invite Mr. Sri K.V. Narasimhan. He's a co-founder of Pontian Powertrains Private Limited, and of course he has a lot of experience in design and manufacture of axial flux motors for electric vehicles and beyond. Yeah.
Thank you, Chairman, sir. It's always a wondrous task to have a session immediately after lunch, and especially when you are bringing up the rear of a session, it becomes even more daunting. So having with that, good afternoon, ladies and gentlemen. I am Commander Narasimhan, and we are a startup incubated in IIT Delhi. And now that I'm the fourth speaker, a lot of the things that we are doing has been touched. So maybe my flow will be a little bit disjointed because some of the things the earlier speakers have covered. So I'll come to the crux of the matter, what people have highlighted insofar as the axial flux is concerned. So I plan to cover my presentation under these heads, but we will just go a little bit. So essentially, our idea was to democratize axial flux, and taking from what Dr. Goyal just mentioned about outrunner, the whole idea was IC engine cannot produce a high torque. So as a result, you have high RPM, you have a gearbox, you have a transmission line, because at the wheel, you needed a lower RPM. So, and of course, being in the forces, weight and volume has always been critical. And axial flux was something that we had done as part of our certain studies and analysis. And our idea when we started our journey was to make motors which can go into the wheel, essentially high torque, low RPM. And that is how our journey started. So I'll be covering that just to put in context the comments that you made. These are just a clutch of ships where me and my colleague had the opportunity to serve. So that is what gave us the necessary sea legs to sail and probably stand before you all and sharing our work today. So our idea was that there is a need to have homegrown technology, especially machine design. And 2018, EVs were catching the fancy, but everything was then coming from China. And unfortunately, COVID happened, India-China geopolitics, the government giving the push that things have to be indigenous. And that's how now today where we stand, we are developing our own designs. Some of them are going into production in various radial flux, axial flux, and the gate. But now the realization has come big time, especially with the present Ukraine-Russia fiasco, that you need homegrown technologies. And the beginning has to be made somewhere. And it was just sheer good luck that I think one of my presentations was floating around, somebody in NAL, I think Dr. Day saw it, and I got in it was a singular honor to speak to Dr. Kota. I mean, we looked up to him when we were in service, when Tejas came, and thank you so much, sir. So with that in background, we started. We are fortunate that we could raise investment because hardware development needs money, and we are fortunate to do that. And So this I've already, basically our idea was to get the machine design on the table, whether it is an electrical vehicle manufacturer, whether it is an industrial motor, whether it is an aircraft, whatever be the case. The idea was that get the core technology to design a motor which can be any application, and that is what we intend to do. So we use Dassault Opera. I think VSSC also has a license. I'm not too sure. But essentially, this is a tool which was the most capable when we started our journey because axial flux requires us 3D simulation and 3D FEA. So when we were looking for a tool at that point of time, ANSYS, Altair, JMAG, none of them had the capability. Now everybody is developing that skill set as well because they know that axial flux is the evolving future. So I think some of them are already allied to the topology. It's just a matter of geometry. I mean, in a conventional radial flux motor, you have two concentric cylinders. In an axial flux, it's a disk. So you have a higher diameter, which translates to a higher torque. I mean, that's what becomes very important in mobility applications because you need a much higher torque more than anything else. And obviously, efficiency uptake is just about marginal. But the biggest advantage is an axial flux gives you much, much higher torque, peak torque compared to a radial flux motor. This, I think somebody's already shown, so I would just skip it. And theoretically, it's possible to have 7 times higher flux density in an axial flux vis-a-vis a radial flux. Though there are machining and manufacturing tolerances, but still you can definitely achieve about 3 to 4 times of power and torque density. I think I would skip this. This already I've touched upon. Now coming to a lot of tools which we use today have been all optimized for radial flux. So because our training is in radial flux, all tools got developed, a lot of templates got made. So a lot of people can actually use existing templates and then take it forward. But when we started, for us, it was absolutely a clean. So we had to do our own scripting because in Opera, it was actually, it gave us the enablement, but there was just no way we could expedite. So we virtually had to do, I mean, every step we created, we started scripting it so that then we made our process simple. Now, this particular activity took us about more than a year and a half. But today, if I have to make a PMSF motor, it is just the analytical calculation, my model is ready. And then it's just the processing time. So likewise, we have done for induction as well as switch reluctance insofar as axial flux go, but we want to take it one step at a time. So right now we are focusing more on the surface mounted magnets because a PMSM configuration in axial flux can meet most of the requirements, especially for the mobility sector, which is what we are focusing presently on. So essentially, this just gives you all the parameters that we analytically calculate and we input in the model. And we called it the Jarvis, essentially. We are all big Marvel fans. So that's how the name came about. So I think I'll just run it through and the model gets ready. So the first time we created this model, it took us about 8 to 9 months. And unfortunately, every tool has certain pluses, certain minuses. In this tool, making a coiling is a nightmare. In fact, we had purchased a license from Altair because we were so happy with the tooling which it provides for winding. It was just a click of a button. But 1 year, Altair worked with us. They could not make a model for us. And then virtually we had to shelve it. But so every tool has its pluses and minuses. And this has served a purpose so far. And this is how, so for me now, this model, for any kind of motor, it's just an analytical calculation for which also we have done our Excel sheets and other things. And we plow back all the design data that we validate over testing so that then my design journey becomes very, very smooth. So I think some of them are already covered. The biggest advantage axial flux gives you is it allows you to use grain-oriented steel, so which automatically brings down your core losses. Unlike the case in radial flux, you're forced to use the non-grain-oriented. So that is one of the biggest advantages which axial flux enables us to do that. Other than that, the classic is rectangular cross-section. I think somebody mentioned about skin effect. So when you use rectangular cross-section conductors, the skin effect automatically comes down and the fill factors are much better. Now coming to the challenging part, I think what was just shown is a yoke design. So we have worked on yoke axial flux as well, but that's very, very specific for certain applications. Insofar as mobility, the yokeless design makes much more business end of things. So if you just notice this particular slot profile, from the left to right, it's a taper. So essentially, every lamination is a 0.35 mm. Every profile is different. So manufacturing this to scale is a big challenge. So in fact, in the next slide, I will probably show you. The first lot we made took us about 6 months. So if you carefully notice, this was a uniform stack, which was machine cut. So the first prototyping, what we did in our POCs, we had done that, but we realized that that's a no-go. Thereafter, now what we have done is we have figured out a way to do laser cut, and the tooling also has been done for volume production. In fact, Nippon Steel has supported us by providing a specific grade of CRGO steel which we need, because that is a much thicker grade to be used in a transformer. I mean, it is too low end for a transformer, but it is very good for me. So we had to get that coil of steel right from Japan, and the tooling trials have been done for that. So this is what we do now for our prototyping. It's just simple laser cut. And this particular slot, what you're seeing is there was a requirement from Navy where we had to work on a design which I could do rewinding on board, because there are certain applications the motor fails. I mean, I cannot get stranded. So this was the design we had worked for them. So as somebody pointed out, how do you hold these particular slots together? So these are all the manufacturing process challenges which actually precluded axial flux technology to proliferate. And our effort has been to get all those things in place so that it can get mainstream. So if you see the first proto that we did, I think the video is there, I will show subsequently. We used a particular thing, we realized it's okay for a one-off, but it's not something which is sustainable. What you see is the next version, which we did for the naval application where I could use. So we had to use, if you see the holding structure, it's a solid metal, so it provides eddy losses. So we developed EMI shielding so that I could reduce my impact of eddy losses. And that was that. Now we have moved ahead of this as well. And if you now notice, the conductors are about 5 by 2. Unfortunately, I'm not carrying it. They're very thick. Unlike the existing motor windings, which are very, very thin strands, these are actually, I mean, if I hold it straight, they may just bend about with. So it leads a lot of tension and torque to make the winding. So all these tooling has been developed now. And if you see the motor on the right, this is how it looks like. Unfortunately, I'm not carrying a radial flux open slot. If you look at the end-turn windings, it's a nightmare. I mean, this looks much, much beautiful as compared to a radial flux. And on top of it, it reduces your end-turn. The entire heat loss in a radial flux machine is, of course, one is the torque part, and the second is the end-turn windings. And they contribute to very much of losses, which virtually is negligent in axial flux. This, I think I will just skip. Essentially, this is how we go about designing for a vehicular application, because somebody has already covered about the process journey, I think. So I don't want to touch upon. But yes, we go about all the various aspects of the requirement and then flow back when you come to the finalized design. I think this about sums up what axial flux can do. I mean, it virtually kills our length. I mean, all the motors that we have done so far, none of them is longer than 5 inch in length. That's about it. I mean, I increase the diameter as per the application, and my length is only about 5.5 inches. So now I think I will quickly go over. These are some of the radial flux motors we have designed getting commercialized. So I would skip this also. So this is the axial flux yokeless motor that's been designed for a two-wheeler application, which is 8 kilowatt. It weighs about 9 kgs. The testbed trials are completed, and about 2 months' time, they will go for vehicle level trials. The next one is a higher capacity, 12 kilowatt, and this is for a three-wheeler application. Testbed trials are ongoing, and this would also go into vehicle level trials in about 3 months. The previous two motors are going into production. All the testing, homologation has been completed for that. And incidentally, this motor, if you see here, this is a 8 to 10 kilowatt, depending on the requirement. This is a radial flux induction. This weighs about 26 kgs. And this motor is far more powerful. It can give you much higher torque, and it only weighs 12 kgs. And all these motor designs we have done essentially keeping in our Indian conditions, wherein your thermal management is key, as Dr. Kota was also referring. So all these motors have been designed in a manner to keep the current densities low, so that we can easily operate them without any requirement of cooling. In fact, when when I got the thing that the MRAX motor was taken as a datum, this same motor, if I introduce cooling and I push it, we can probably take it to about 50, 60 kilowatts. So that's the flexibility of an axial flux because it's got a linear torque profile. As long as you have a DC link voltage and you take care of the cooling, you can push it to wherever you want. So this was the outrunner motors which you spoke about. So the first motor that we prototyped was 11-inch frame, 15 kilowatt, 72 volt DC system, and 250 Newton meter of peak torque. So our idea was give this to two-wheelers because all the two-wheelers, if you see, the low end, the initial two-wheelers came with the outrunner motor because it makes your architecture clean. You just have a battery, your rear wheel is the motor. But the moment they wanted higher speed, because in radial flux, you cannot achieve beyond a particular level of torque. So they could not. So people had to move to a mid-mount motor, and then you have a chain drive or a pulley, gear train, and then you take it forward. So our idea was to give this to the industry. So when we made this and gave it to the OEMs, they just raised their hands. They said, we don't have the chassis development R&D. So now that was the case about 2.5 years back. Now, like we are giving 4 motors of this kind to DRDO for an amphibious platform which they want to make because they need the high torque. In a 13-inch frame, we are able to generate about 300 Newton meter of torque, which is quite decent. And if you put 4 of them, it can give them a lot of capability. So this was one which we did. This is the second one, which is a 19-inch diameter. And so this is about 1250 Newton meters of peak torque at 380 volts. So when I was looking at the braking thing, they actually need something like this, which is very high torque and low RPM. So after doing this, this was the proof of concept that we established, and then we moved on from there. This is another e-axle design that we are working in, which we are basically leveraging our strength on axial flux to create an e-axle, which is more for the commercial segment, which can make, essentially axial flux allows me to increase the diameter where there is space, and I can use the lever action to reduce my current density. So I can operate for a longer time at a very low current and meeting the torque requirements. So now coming to, yes, what was being discussed. Unfortunately, I'm new to this aviation side of things, and I had very limited input. So with that, we just did a little datum. So essentially, we basically, since we realized that about 100 Newton meter is something which is being used for the maximum time, so we designed a model taking that as a datum, so that as a rated torque. And these are just the specs which we chose as a first cut design. So we could keep our back EMF to about 0.052, and we could push up to 6,000 RPM. In fact, we can go higher because the voltage is there. So this was essentially, we did a static analysis for 100 Newton meter, and we could manage it at about 9 amps per mm squared. So typically for my operation without cooling, we operated between 4 to 5. And at 9, I just need to give a little bit of cooling. And essentially, the advantage that I have is if there is space available, you can optimize the design in a manner to give what is needed. And especially if like the work which Dr. Karthik was sharing about multi-phase and other things, there are so many flexibility that we can bring on the table if I know the controller what the requirement is. Like our fundamental frequencies are much lesser, which makes the job much easier. And my current levels are also much lesser compared to a radial flux machine. So all these actually come together. So this essentially just shows the flux lines, how the pole formation happens. So if you see this, if you see, this is just a 3D simulation of a PMSM machine. How when you do the rotational analysis, how the flux lines move and how the rotor rotates. So this is just an indication of what the FEA can enable us. So likewise, we also did, as Dr. Kota was mentioning, that we can do away with a gearbox. So we did that also. So one unique characteristic of axial flux is, if you notice, the torque linearly increases in this, which is very unlike a radial flux, wherein after a certain window, the increase in torque is not linear. So essentially, you will keep pumping in current, but the proportionate increase in torque doesn't happen. So that is something which is a unique characteristic of axial flux, which comes in very handy to make very, very compact size motors. Similarly, we also did, in fact, this motor we had designed for another client who had a 600 Newton meter requirement. So we didn't change anything. We just toned it down a bit for the 300 amps, which is without gearbox. So basically, if you take a 375 mm as your OD, in about 10 amps per mm squared current density, you can achieve a 300 Newton meter. So this can take away the gearbox. So this is briefly what I wanted to share. So essentially, what we have managed to achieve is solve that so-called riddle of axial flux and how it can be done and implemented on the ground. So I think I have finished. Yes, this is a little bit what we are doing from our end to embrace EV. Not that I'm a Tata ambassador, but yes, so just to have the green quotient going. So I think I have finished, sir. So any questions?
Thank you. Any questions?
Sir.
Ask for even more. Now, what is the maximum the power you have done from the machine? Second is, particularly, you heard that before. In fact, they talk about the building in terms of thousands and all that. You said it's also very difficult for this action force. But if you are talking on numbers,
sir,
how would it be?
It is not. That's what I'm saying. We are, I mean, Yasha, since people refer to it, they sell their motors anywhere between 12 to 15 lakhs a piece. We want to sell it at 15,000. So we have done all the manufacturing processes are already in place. In fact, probably in the next 6 to 8 months, we would be scaling up for low volume manufacturing. So Hansa volumes are nothing compared to a two-wheeler or a three-wheeler market that we're trying to do. So we have done all the hard work. I mean, all the bulwark to get these things off the ground is already in place. And that is what
maximum efficiency you expect and 1 megawatt level.
See, so 1 megawatt is something I have not done. So I would not, like my take probably would be, I mean, rather than going for a single motor, I mean, axial flux motors are very thin. You can actually cascade them. You either make 2 500 or 4 of 250. It doesn't matter. Like the motor that I showed you, 19-inch diameter 5.5, is 55 kilowatts at 1000 RPM. I ramp it up to 3000 RPM, I will get 200 kilowatts. So I put 4 of them. It's all, you're stacking them in just about 30, 40 inches. It's about 30, 40 inches together. That's it. So there can be multiple ways you can implement it. Because, but that has to be decided A on the DC link and B from the controller. Rated, you will easily get about 94 to 95 at rated RPM. And the band can again be tuned. Like if I tune a motor wherein you are pushing maximum utilization at higher RPM, axial flux will give you much better efficiencies. Unlike other motors which at higher RPMs will not. In axial flux, if I design a motor in which I am operating it at the other extreme of the efficiency, RPM, my efficiency remain high. So basically, if your efficiency delta for the majority is say between a band of 300-400 RPM, you will continue to operate upwards of 90% continuously.
Yeah, of course, we like to optimize for the cruising period.
No, that's what. So for me, it is the torque and RPM. So for me, it's only torque RPM. It doesn't matter the other side. So we can always design it as per that. So for me, it is more important that the controller, what they want, what they are comfortable. If they say, I don't want higher currents, we can accordingly make it into the design part. If they are able to handle higher currents, we can do that. So the idea is to have a very flexible approach. I mean, we are not rigid that, okay, this is the shape you took it, because we are custom designing. So thereafter, a lot of things can become much simpler. So weight, as I told you, the air is about 1 kilowatt per kg. That is air cooled. So if I introduce cooling, it can go up to 10 kilowatt per kg, even more.
Weight of the cooling will come in.
Weight of the cooling is just, for me, it's a line. I mean, yes, because it's, yeah, but in a motor, typically you give a dry weight. So if you see, I mean, that's assumed to be a casualty. I mean, you don't factor it in the motor weight, but insofar as the power density or torque density is concerned, it's more on the cooling. So like all our motor designs, we have ensured that we don't cross 95 degrees. All our testing.
IP67 or...
So for EV, it is IP67. No hydrogen. IP6. Okay. No, IP67 can, that's what is required in the EV space. Some people say IP69, but I don't find particularly any utility of it. But IP67 is easily possible. I mean, it's not an issue at all. IP67 can be achieved. 67 can be easily achieved for these motors.
Okay, thank you, Mr. Mann.
Thank you, sir.
Good. We had a lot of apprehension as well as the motors and powertrain and power system. I must say that the last 1.5 hours, the excellent exposition by 4 eminent speakers have answered several questions. I think a lot of good clarity has emerged. Yes. For example, on the motor controller, I think the overall architecture and all that, now we have got a very good base understanding, and one can debate and then try to modify it, take it forward. So also the converter topology and including the addressing the multi-phase machines, I think now we have got very good clarity. And of course, when it comes to semiconductor device, it has been very clearly brought out that silicon carbide technology is more relevant to loads, and we must more look towards in that direction. And the control aspects of the motor have been sufficiently well addressed, and we have a very good base for which we can take it forward without any difficulty. Testing methodology of the motor as well as the entire control chain has been brought out very clearly. And what I liked was the bringing the machine emulate system. I think that will ease out our whole way of we are going to work. And motor options, I think we debated quite a lot earlier also, that today I think beautiful clarity exists. We addressed all these permanent magnets, superconducting, axial flux, radial flux. Almost they zeroed in, I must say, for the answer, which one to take and go forward. And what is more important is thermal analysis. I think very clearly the sample analysis has been brought. That only shows that we have the enough expertise, tools, they are available, and we can take it forward. And also the motor test plan also is very exhaustively brought. What are the various tests we need to carry out, and it has been clearly brought out, and it is quite nice. And coming to the industries, we can rest assured that we have enough expertise as far as the realization, design, manufacturing, including challenges you brought, but I'm sure that you will also have the solution for all those challenges. We have that belief that we can certainly address that. Whatever that we can do that. And also, I am very nice to hear that they can design the motor for any application. That only shows that they have all the design tools that are available, without which it is not possible to do. Just like as you go and buy something somewhere, it's all available with them, then only we can do that. So definitely challenges are there. It is for all of us to understand, but I am very happy that this 1.5 hours has been very productive session. And I think Gota and Dr. Goyal, we used to see always that how to get solution. I think a lot of good work has been done. Give them all a very big hand, I think. All 4 with this, thank you very much. Thanks for all the audience, and hand over to the organizers to announce the next set of action.
Sir, thank you very much for very interesting and very good session, very interactive session. And this session addressed various technical challenges related to electric motor and powertrain technology. On behalf of organizers, I thank both speakers and session chairman for this wonderful session. Thank you very much, sir. But now, before we move on to the last session of the day, again, a gentle reminder regarding those who want to visit our aircraft hangar, please register your name at our help desk. Now, we will move on to our last session of the day. The session will be on propeller. And to chair this session, I kindly request Dr. B.R. Pai to come on the dais and moderate this.
Oh, they had it there.
Yes, sir, it's there in the same.
Good afternoon, gentlemen. So I have this task of chairing the last session, which is now half an hour late. But can we assume that we have 1 hour available, and in which case, since we have now 3 papers to accommodate, I would request each paper to be only about 15 minutes. Out of which one is online and two are physical, colors, and one paper on distributed electric propulsion by Dr. Venkat Krishna. Yeah, so I would request Sri Pratap Naika to make a presentation.
Yeah, good afternoon, sir. So actually, in the country, all propellers are imported. The question people are talking, why you want propellers? Already ANSA propeller is there, we'll use same propeller. That is a question always everybody is raising, same propeller we will use. But issue is, there is some other problems with propeller. It's not easy that we will use same propeller because motors, torque level and speed, those things have to be matched with the propeller with this one. So I am Pratap Naika. We are actually working almost 20 years in propellers. Earlier we have developed the propellers for smaller UAVs and all. Even we design, develop, test flown those things. At the same time, the people who started in Europe, they started the companies, they are exporting. With the government support, they made a company. But here, due to our setup, we are discontinued. Then again, our Saraswat sir, Kota sir, and our director Jala sir, now they again restarted our work for developing the propellers. So recently we started developing propellers. This first propeller, what here we are showing you, this is a ANSA propeller. This is purely indigenous design. We are developed design that, and already we are in advanced stage. We are going for a fabrication. Maybe in another couple of months, we will have a hardware of this propeller. And we are also working. This is next one is high speed turbine test facility. Then we are working small engines also. We are developing with our own interest small gas turbine engines. The team is myself and Vinod Kumar, and I have one more scientist, that is Agnimitra. We are three, but we are actively involved. These are the things what I am showing is recently actively what we are working continuously. Apart from supporting our Saras propeller also, Saras propeller anyway we bought that propeller and we are installed that. Yeah, actually we are seeing all good work by electrical. We thought that all the motors were importing, but the last three, four presentation, we saw that the technology is available. We can even get a motors indigenously, and we can configure those motors to our propeller exactly to match our propeller. So this is from the NASA. As what are the types of electric propellers? Yeah, this is already gone. So here we are aiming for the all. Main thing is this all electric. What we are that second, this one in the middle. So that is our aim. So there we are going for a all electric. So there here we can. So this also now we know what are the where we are operating in turboprop engine. So this is a turboprop, how turboprop works, and what is the altitude we can fly with turboprops. And now come to our single engine and twin engine aircraft. Actually here using propeller in the single engine and twin engine, there is a lot of difference in this. Single engine, even though the ANSA what we are using and the propellers elsewhere we are using, it is not full pitch change mechanism. We have a slide like here, we have a 15-degree pitch change where to get only the efficiency during the takeoff or little climb. Whereas in twin engine, the primary issue is the pitch change mechanism is the safety. That is a major thing. So that's why twin engine aircraft need a full-fledged, because even that's a certification requirement. It has to have a full-fledged the pitch change mechanism where it should have a reverse pitch also. Those are the regulatory requirements because of the safety. Where when what happens in twin engine aircraft, if by chance engine fails, governor fails, or something else fails, the windmilling effect of the propeller, which creates the parasite drag equal to parasite drag, which can remove this control of the aircraft can go out of the pilot within a few milliseconds. That much of effect the windmilling drag in the twin engine, multi-engine aircraft propeller are having in the event of failure. There you have to control that it has to go to, if anything happens, the propeller will go to the feathering position. So where it has to stop there. So then the windmilling drag will reduce the one side, and using other engine, we can land the arc, go to nearby airport and land it. And also when we are investing so much on this pitch change mechanism, we can use it for efficiency. We can exploit this pitch change mechanism for efficiencies at the different operating condition. Also, we can use it for the landing time. We can get an assist from this. So all those things we can get from the pitch change mechanism in the twin engine aircraft. But it's a regulatory requirement because of the main is the safety. Apart from that, we can use it for efficiency purpose also. This is how the aircraft operation during engine failure. So if any engine fails, that propeller will not keep quiet, because if it is having a feathering, any fine pitch or coarse pitch, it will start rotating, and that will create a huge drag. So to nullify that, the immediate mechanism is made in such a way that this will go to the feathering position where it will stop rotation, and that's how aircraft further it can go for a nearby landing. So this is that is the penalty we here is the pitch change mechanism. The pitch change mechanism is very complex, and because of this complexity, the design complexity, manufacturing complexity, the cost of the propeller is also very high, and also weight will also go up. And also this pitch change mechanism will help in one way to size in bigger aircraft like gas turbine engine, the turboprop engine, to size the gearbox, because it's generally the constant constant speed and variable pitch propellers we are using in the pitch change mechanism. There we can even engine also, the free power turbine and the engine can operate at the elevated efficiencies, because they are at part load, they are very inefficient gas turbine engine. And also gearbox sizing, gearbox speeds and all we can keep in a normal way using the pitch change mechanism. But again, this will add up for this, and it's now for a twin engine regulatory requirement. But for a single engine aircraft, coming to this we can get anywhere in the internet. We can maintain the constant efficiencies during the propeller operation at different pitch if we use at constant speed. So when you change the pitch, you can see that we can have a constant efficiencies. So these are the advantages with pitch change mechanism. However, now coming to SARAS, these are the actual, we bought the empty propeller for our SARAS aircraft. These are the actual numbers for the SARAS aircraft. We can say takeoff, the pitch angle is 31 degree, and efficiency we can hit up to 52%. Max climb it can go up to 77 we are hitting, and max cruise this is operating at the 87%. This is because of the pitch change mechanism. Now coming to single engine, whether really we need a pitch change mechanism in single engine. Single engine aircraft, actually the safety when anything fails, engine fails or some other things happen, so this will not create so much negative effect as like a twin engines. But however, this can be, it will create a drag. Still we can land the aircraft because it will not lose the control. Aircraft will not lose the control like a twin engine aircraft. And here to get a little better efficiency during the takeoff and climb, we are using like Hansa. Hansa is again empty propeller we are using. There is a 15-degree pitch change we have. So it's anyway bought out aircraft propeller. It's not ours. And this mainly in small single engine aircraft, we are using the smaller pitch change mechanism to get a better efficiency. That can be obtained in the battery propulsion. That means motor by changing the RPM. So there we can completely get rid of the pitch change mechanism as well as the gearbox, if you size the motor and the propeller in proper way. And as you have seen that there is a pitch change mechanism will have a weight, complexity of design, and other issues, operating control, everything, and it's good for the single engine aircraft. So this is our Hansa aircraft. Currently, what is operating is with the empty propeller. These are the efficiency level with the smaller pitch change. That's a 15-degree pitch change we have. So at takeoff now it is actually operating at 61% of efficiency, climb 71%, and max cruise is 83%.
So this is the level of efficiencies. ANSA is working currently. If you match to this with without having pitch change and motor, sorry, gearbox with our own design, that itself is a good achievement. And now currently, because this electric, since morning we are hearing everywhere electric propulsion, electric transportation is gaining momentum. Propellers also will come. When propellers will come from the, because there are very few countries they are fabricating and selling the propellers. They need a standard motor. Now also there are engines. They are already certified engines. For that they have developed the propellers. Similar way, when standard motors are available, they will make because they it's economics. Or if anybody want to approach them, they will ask the money will be in maybe millions. They will ask for the developmental cost and all. So for that, any program currently they are either something like a smaller UAV distributed propulsion. They are going because smaller UAV propellers are fixed pitch variable speed propellers are available. Other than that, if you want to go for such aircraft, we have to develop the propeller, or we have to contact propeller developers by paying some used money. So these are the plots which are not available. This I am showing. This is our tunnel test. Actually, these are the fixed pitch variable propeller tunnel test. As we have seen there, when we are changing the pitch of the propeller, how we are getting the efficiency change. Here also we can see that when we are operating at the different RPM. So here we can see at 4,000 RPM, it's the propeller is working same. These are all same pitch, working at 50%. When we are going around close to 5,000, it is going up to some 68%. Here also we can see these are going up to some 68, close to 70. These are all smaller propellers, so that's why the efficiency levels are lower. These are because of the low Reynolds number propellers. This is UAV propeller. So just to show that I am showing here. This also you can see the efficiencies. When we change the RPM, we can increase the efficiencies from even as low as 20%. It can go up to close to 65, above 65. So this is the one we can use the variable RPM with fixed pitch by getting rid of pitch change mechanism. Anyway, this I'm just showing because now spirit is high. Nobody want to hear this. Why I am showing this is currently, if you want to go for a purely electric propulsion, mostly the vehicles are smaller vehicles, smaller aircraft currently. So they may not need a complete full-fledged pitch change mechanism. We can go with a either distributed propulsion for slightly higher passenger capacity, or lower this one we can go with a single engine propeller. There we can use a single pitch constant pitch and variable speed propeller. As I told, we have been working in this propeller design, and these are the steps we are following for the propeller design, and we have developed our own in-house design software also. Even there are JBlade, QProp, JavaProp propellers are available open literature for designing the propeller. However, we developed our own software so that we know what is inside and we can change whenever we want whatever parameters we want. And we have even compared with this JavaProp, which is widely used across the world for designing of propellers, with our own design. You can see that we found a good match with Laravel and Atkins methodology when we use. Then, as I told, we have developed earlier a lot of propellers like for a UAV application. This is a 6-inch propeller, 3-blade, 2-blade. Even we compared those propellers with the experimental CFD analysis also. Then 4-inch propeller, 3-inch propeller also we have designed. Here the efficiencies are slightly lower because of the low Reynolds number problem. So these are the actual propeller we fabricated. This is completely done in NAL. Even fabrication, the testing, design, everything is done in NAL. That's what at that time when we did this similar work, people in Europe, now they made a companies, and recently they visited us to sell their product. But we have technologies, we need to see how to take forward. And recently now we are working on apps. There we are, this is a commercial propeller we have taken because time was short for our TD. This is TD1. Here we shortlisted commercial motor and propeller. So this we have carried out the complete test, and this is how the propulsion system is meeting the requirement. So these are the charts developed by us in the, this is the test experimental data, actual experimental data for that our propulsion system. Yeah, we have shown even the different operating conditions here also. All this I am just to showing that what are the capabilities we have in the propulsion propeller. And this is a full scale propeller. This is indigenously we have developed this propeller. This is
About 3 minutes.
okay, sir. So this is a 2.4 meter propeller we have developed indigenously, and we are going for fabrication also. Now we have completed all the analysis, everything we have done. And coming to Hansa two-seater aircraft indigenous propeller development. So this propeller we have, as I told earlier, indigenously we have developed. This is a 1.75 meter propeller. The existing one is 1.73 meter, and these are the real requirements of the aircraft. We have carried out the CFD, and then now actually mechanical design in this propeller for a manned aircraft is really challenging, because this is we are going for a composite propeller where inside core is the wood core. So here it's a wood core, and leading edge is the metallic leading edge. We have to embed the metallic leading edge, then CFRP outside. So these are the design also carried out. Very shortly we are going for a fabrication of. And this is we are now working for the ANSA electrical aircraft. Because the speed is high, we have reduced the, there it's a 1.75 meter, but now it's a 1.1 meter. But Kota sir is unhappy about efficiency, but this is the first design. We are working on that. Further, we are fine tuning this to get to the efficiency level what current Hansa is flying without pitch change. So we are aim is to at different RPM we have to get close to that efficiency. Anyway, mechanical challenges are safe, but we are already encountered that we have designed, we got experience, so this can will make this propeller quickly for once aerodynamic design comes. Thank you, sir.
Thank you. Any questions, please? Well,
You mentioned the good design of the.
Yes, sir.
And you give it back. That's a very popular portrait of some other design adopted for this.
Yes, sir.
And you said if we made match this number. Much better. Because that is your for somewhere someone designed for something else and just match it. So if you are designing it yourself. What numbers should have it much better. Secondly, there are two propellers also. I don't know. Economy of the speed and all that. Electrical is, I would say, a little bit. Is switching again. Like some better machine,
Twin engine aircraft, what you have seen, that is a proven aircraft propeller. We imported that propeller. That's what we are using. Efficiency levels are not lower. That's how we will maximum we will get the efficiency. Even international propellers, what they have.
Get that point. He does not design the propeller for your Hansa.
Sir, actually, I will tell you one thing, sir. No, sir, here I want to clarify one thing. Sir, in the world is built around the propulsion system. No propulsion system in the world for any aircraft, it is never developed for an individual. However, what you said is we can develop a better propeller. That's what you are mentioning.
You said you are the propulsion.
Yes, sir.
You are designing for Hansa.
Yes, sir.
Whereas someone will design for someone else.
No. That is, sir, that propeller is designed for the particular engine. That engine and propeller that we got and we built the Hansa aircraft around that propulsion system. So those are the efficiencies, 82% efficiency for propeller in that class that can currently international standard that can maximum efficiency can get. Beyond that, still we have to do a lot of work. People are working on that. Getting that much efficiency itself is a really challenge. No, we are so. No, sir, not sir. What is the question?
I think he has given the proper answer. That is, the mechanical aspects are very challenging. If he manages to run this propeller safely, I will give him 100 marks. The efficiency entirely depends on the profile chosen, and you can optimize it for time or thing. They're very well aware of that, so they will make a good job.
Sir, certainly improve the efficiency with a great act. This is in your hand. Okay.
Yes, sir.
Pratap Naik, so developer.
So we'll definitely do that, but what sir said, close this one, sir, matching that itself is a great, because the propeller technology like a gas turbine engine also, it's currently Europe, only Germany is doing, America is doing, Russia is doing. No, sir, not GDI. I am comparing with myself with the international standard. I am not comparing.
Okay, I think we can discuss afterwards because we are.
No, sir. Propeller designing, developing itself is a great challenge. No, sir, not.
Okay, I think. Okay. Any other questions we can? Yeah. Any other? Okay. So I think.
Yeah.
I am Zubin from HA. Basically, my role is a power plant maintainer. And I think you have discussed about the propeller when you don't have a variable pitch mechanism.
Yes, sir.
But as you know, most of the aircraft, electric aircraft which are flying elsewhere, they are all constantly variable pitch mechanism.
Correct, sir.
So, particularly for a electric motor, what is the kind of mechanism you would be adopting for in that case? Because I read a lot in the internet, but I couldn't find out what is particularly that mechanism they are adopting to.
Now, they are mostly using constant pitch, variable speed propeller. That's what we are also planning to develop.
You need to say that they are getting rid of all the hydraulic system for the pitch.
Correct.
They are also using
Completely, they are getting rid of.
constant speed.
Yes.
But again, the question remains that the efficiency of the propeller drastically goes down when the RPM field. Will that actually matter for your 95% efficiency which electric motors are ultimately using?
See, actually, in this class, what Saras and Hansa class, what we are talking, even 80%, if we get above 80% efficiency, that will be the international standard efficiency, what we can achieve now.
I totally agree with that.
Yeah.
But my broader question is, the whole purpose of moving for an electric motor is that you are able to achieve 95%. And ultimately, when you are converting into thrust, you still you are able to get quite a bit of leverage on. But when you go for a constant pitch variable RPM, you are compromising on ultimate system efficiency.
No, we are not compromising on efficiency.
Thank you. Okay, we can discuss afterwards. Yes. Okay. Thank you, Pratap. Good presentation.
Thank you, sir.
So, Abhishek, we request you to take 15 minutes for your presentation.
I'll try, sir. Because originally I was told total time was 30 minutes. So anyhow, so the topic is the design and development of propellers for electric aircraft. I hope my audio is clear.
Yes, sir. Please go ahead.
Perfect. So this is the outline. I'll start with quick motivation, approach, and so on. So let's get going because we have less amount of time. So clearly, I mean, the motivation is out there. I mean, there is so much of stuff happening in the domain of aviation and electric aerial vehicles. So here I put pictures of two popular designs. One is Pipistrel WhatsApp, which is a sort of a converted small fixed-wing aerial vehicle developed by Pipistrel. And the second picture is NASA X-57 Maxwell, which is supposed to fly next year, which offers a sort of a distributed propulsion system where you have two larger propeller systems at the tips and a set of small propellers distributed along the span of the wing. Beyond that, there is a lot of stuff happening also in the VTOL domain or eVTOL domain, as we can call electric VTOL systems. Because I work mostly on VTOL, so I was quite tempted to put some of them here. So this is the electric vehicle in the center, which has been developed at IT Kanpur. It's a pure electric vehicle, a small unmanned aerial vehicle. On the right, we can see picture of Vahana, which interestingly has 8 propellers, so it has distributed electric propulsion. All the propeller and motor systems on this actually also have variable speed and variable pitch. So I believe, I mean, variable pitch is not something which we can start getting rid of as of yet. I'll come to that why later. And then at IIT Kanpur, our students participated in some competition where we tried to design a personal aerial vehicle, again a VTOL system using octa-rotor design and certain things. So anyway, there's a lot of it going on. So we have enough motivation to look into the design and development of propellers for electric aerial vehicles. So the state of the art of design of conventional propellers is already very well established. I mean, people have done a significant amount of work. But I would say that this process, these designs, these ideas are still stuck in the last century. The reason for being that once the turbofan engine came into being, the aviation industry as such had very little interest in working on propellers further. But now with the advent of electric propulsion, the fact that we can now power our propellers using electric motors, that actually has added a new dimension. So now we have sort of two control parameters available which can determine or dictate the performance of our motor propeller combination. So we have option to change the pitch and also option to change the rotor speed. And both of them actually have interesting roles to play. And I mean, so far right now, I don't have a clear-cut answer, but I point out what I understand so far. So variable pitch ensures that we have high efficiency over a range of air speeds, not just advanced range of air speeds. While variable rotor speed would be very beneficial to enable lower power consumption under different flight regimes, this is extremely critical for VTOL vehicles because sometimes same motor propeller combination has to give you thrust also for takeoff and then or rather lift also for takeoff and then thrust for forward flight, and the forward flight thrust is much lower compared to your lift required in initial takeoff. And also the fact that distributed propulsion actually tends to affect our aerodynamic behavior of our wing, and we have done some little bit of work on that, so I'll present that also. Right, so requirement for, so question is, I mean, how do I go about propeller design? I mean, it's a well-known field, so I'll quickly summarize that, and it's not something very new. So what I was mentioning is that not much research has gone. I mean, if you go and search on any scholar database, you will find that there will be very, very sparse number of papers on propeller designs over the last 20 years, I would say. I mean, you can count them on your fingers, pretty much. So that tells you that, I mean, this area has not been explored much recently, but probably there is a need. So propeller design for, yes, and if you look, I mean, some of these are actually for VTOL aircraft or unmanned aerial vehicles or something like that. So those are some of the papers which are out there. And the reason being that there are conflicting requirements for VTOL aircrafts that you require a high thrust lifter and relatively low thrust propulsor. So that actually presents a new challenge. And the performance often actually comes out to be a compromise between hovering flight and forward flight. Anyway, that is not the main focus here. Now, to design this propeller, we require certain things. Okay. And first is, of course, a tool which will allow you to predict the performance of these propellers. And of course, traditionally, blade element momentum theory has been used for quite some time. But then there are now more enhanced version of BEMT theory available out there, which allows us to enhance performance significantly. Also, CFD is there. CFD is better to do the, I would say, final validation of your design instead of using it in the design stage itself, where a lot of computation has to be done. And of course, I mean, when we want to carry out the design, we need a process, a method, some kind of function to parameterize the geometry of the propeller. That is, how do I define the chord? How do I define the twist? How do I define pitch? And so on and so forth. And eventually, you will have to put some objective function, which we'll try to minimize to get the optimal design. This is a quick survey. I mean, beyond conventional BMT, which was discovered long back for marine propellers, probably initially, and then used extensively for helicopters. In 2012, Leishman and his student Stahlert, I mean, they modified BMT and proposed a model in which you can also incorporate swirl, because normal BMT doesn't account for swirl. So with this inclusion of swirl, your capability enhances somewhat. For parameterization, of course, B-spline, you can use higher order polynomials, you can use incremental change from some root values. So there are many ways by which you can parameterize, and you have wide choice of functions that can be used to describe the geometry of a propeller. And finally, for optimization, again, it's a very well-established area. You have gradient-based methods, you have meta-heuristic methods, genetic algorithm, particle swarm optimization, and colony optimization and whatnot. So the goal is, of course, in the design process is to optimize something, and most of the time it is optimizing the aerodynamic performance. But there are recently papers where people have tried to simultaneously optimize the aerodynamic and aeroacoustic performance. Because if I'm making an electric aerial vehicle, I would want to be very, very quiet. Now I cannot blame the noise on my engine. I have to now say that all the noise is coming from the propeller, and if I can simultaneously design this in a way that I can also cut down on noise, that would be a really great thing. Sometimes, you may want to do combined aeroelastic design optimization. So that could be also something which people do. So that brings us to the design space. That okay, how do we go about designing it? We have input as cost distribution, pitch distribution, choice of airfoils. So we can have different airfoils stacked up. We can decide which airfoil to stack at what particular location. And then whether we want to bring in the pitch and RPM as also input parameters, whether we are going to work with variable RPM systems or fixed RPM systems. Traditionally, they were fixed RPM designs. Now, we have this additional power in our hand to change the RPM also. But all this has to be done to ensure that we meet the thrust requirement that my aircraft is going to have. Because without that, all my design has no meaning. So the approach, if we go with modified BMT, the advantage it offers is that it incorporates high angles in formulation. It also accounts for swirl or in-plane velocity. And it is fairly fast and quite reasonable answers can be obtained using this. Easy to hook up to optimizers. So this is the difference. You have now azimuthal flow ratio, which normally is neglected in conventional BEMT analysis. So I'll not go into the mathematical details due to lack of time. It's all available in literature out there. Yeah. Another advantage of BEMT is that now I can actually bring in the lookup tables for my lift, drag, etc., which tremendously enhances the prediction capability of these tools, even though they may be simple. And I can bring in new airfoils also to analyze, because I don't think we have spent enough time to analyze and select suitable propellers for wide range of applications. Hardly a lot of new airfoils probably have been developed in the last 20, 30 years, but we have not explored them, whether they are good choices for improving the performance of propeller to new levels. So finally, in the modified BMT, we combine everything together and we set up an equation where we try to solve for the phi, which is the induced inflow angle, and that is only unknown. And we can solve this by using not fixed point retracement, but we'll use bracketed bisection method. So we have developed our own software actually in a MATLAB, which does all this and gives us performance for MATLAB, performance for prediction of propeller, thrust, power, etc., etc. So I'll come to some sample results in a moment. So then we have to also set up the optimization problem, which is going to be a constraint optimization problem. It's not an unconstrained problem. We have to set right constraints in terms of geometry constraints, in terms of thrust requirements, and some other things. And finally, we minimize whatever we intend to minimize. This is a standard process. You throw in a design to your cost function and see if it works for you. If it doesn't work, then you call the optimizer and try to change the design, modify the design to take it towards the optimal solution. So all these options are available. Skip this slide. Now cost functions, normally when I design a helicopter rotor, I look at the power loading, I try to maximize that. But when I'm designing a normal propeller for a fixed wing airplane, I'll try to minimize the power consumption or maximize the efficiency. At the same time, this has to be done by keeping in mind that my thrust has to be maintained. I should be able to demand a given amount of thrust from the propeller that I'm trying to design. For other systems which actually operate in hybrid mode, I'm again giving example of eVTOL systems, the total energy may be minimized. So that could be my cost function here. And I may bring in power for hover, time required for hover, power for forward flight, and time required for forward flight, and then total energy could be minimized. So another example of constraints, how constraints can be posed. So you can have constraints that thrust has to be at a certain level. Your geometry may have certain constraints that I cannot have big enough propeller because it may interfere with certain things. There may be some other constraints about tip velocity that I don't want it to go in supersonic condition or transonic conditions. So this is some example how we set up the constraints, how we discretize. So we can use polynomials, we can use B-splines, we can use even. So if we start with a simple new design of a propeller, I can use linear twist and linear chord. So a linear taper in that sense, and also start with that. So all those options are available when we try to sort of parameterize our geometry of the propeller. Then this is also same idea that I start with some root chord and root pitch, and then every other segment will have a delta value change from the previous value. So this way you set up number of variables, and then using those variables you try to optimize. So some more example about how you can bound the various coefficients also. So these are, I mean, things I've taken from our past work where we have tried to optimize propellers for various applications, be it a VTOL aerial vehicle or be it a edgewise rotor for a multi-rotor or something. So let's look at some examples, how this tool that we have stacks up. So we took off the cell propeller, we scanned the geometry, we got the chord distribution, the pitch distribution, and we took it on a load cell and measured the performance, and we see that thrust prediction is excellent and torque prediction is also quite satisfactory. Then something similar we carried out for forward flight condition. So in this case, we took off-the-cell propeller information available in literature, and we compared that result with UIUC experiment for CT versus the advanced ratio, and we saw that the current modified BMP performs fairly well compared to experimental data that is out there. Now comes doing the fundamental understanding. I mean, of course, these things are not something very, very new. These are already well known. This is the design of a propeller that we were exploring for our VTOL, biplane VTOL aerial vehicle, and we are trying to see what pitch setting we have to use and how it is going to stack up. So, of course, the key parameter in the design is the twist rate. And we see that, I mean, the higher the negative twist rate, my efficiency is better. Be it, I mean, you are operating at 5-degree root pitch or 10-degree root pitch. Increasing the root pitch, of course, you can see, I mean, is slowly pushing my efficiency up. The reason for all this is, I mean, the reason why I'm in the high negative twist. So higher the speed, higher the negative twist will be. So if you are designing something which is going to fly at 100 meters per second or more, then maybe we will be operating at minus 45, minus 50 kind of pitch setting or something. So the reason is the propeller experiences very high inflow angles near the root, and inflow angle decreases along the span. So once you go outward towards the span, the inflow actually decreases, angle decreases. So therefore, a blade with high negative blade twist is preferred. So that
send him a chat message or something, or how to tell him?
So operates at optimum lift coefficient, and so that was, I mean, the effect of changing the pitch angle as also changing the twist for different designs and how it affects my propeller efficiency.
We'll have to finish in 2 minutes.
Question about how my propeller efficiency changes when I vary the RPM. So that is this particular graph where we see that it's pretty much possible for me to maintain the efficiency of the propeller by decreasing the RPM at different speeds. But this is not giving the entire picture. So the earlier speaker mentioned that, okay, now, I mean, I can get high efficiency by changing the RPM. So this is a good thing, but we have to be very, very careful before we make this claim. We need to check what is the thrust output I'm getting at these particular speeds and this particular efficiency. Does it meet my trim requirement or not? So without having checked that, I mean, it is very, I would say, risky to claim that variable RPM is enough for me and I don't require a pitch change mechanism. So we need to check the thrust output before we can claim. But yes, changing my RPM actually now allows me to sort of enhance my efficiency for different speeds as well, which is very, very similar to what we saw for changing of pitch angle as well. So the outcome of these kinds of optimization studies, typically we end up getting some chord distribution, some pitch distribution. So this is the study which we did actually, where we tried to do a delta change from some baseline values. And finally, we found that the optimal propeller actually was reasonably good compared to various other propellers which are available in stock. And it was a good compromise for both hovering flight as well as forward flight. Now, before I close, I'll just have a couple of more slides regarding another aspect of distributed electric propulsion. So we actually conducted some experiments in wind tunnel where we try to see how does the propeller interact with the wind, how it actually enhances or diminishes the overall performance. And these are some results we obtained, and we found that depending on how far my propeller plane is from the leading edge of the wing, my lift and drag actually changes. And at certain spacing, I found that my L/D actually could be higher than, I mean, what it was actually for a case when it is too far away or too close to it. So clearly we see that the L/D can be altered by having propellers distributed across the entire wing. And because the blade was, the propeller we tested with actually was a 2-blade propeller. So we were able to see the effect of the 2 per rev on the wing loading also. So that is, sorry. Beyond that, another aspect that needs to be considered is that the sense of rotation of propellers, spacing of propellers. So I don't go into the spacing part so much right now, but sometimes, I mean, when we are designing vehicles and we have, say, tandem wing design or something, then it is important to see that the propeller which is at the tip, should it be in the direction of the tip vortex or it should be in the direction opposite to the tip vortex. So in that case, we found that if I actually have a propeller position at the tip of the wing, in a sense that it actually tries to cancel the direction of the tip vortex. So it is in the opposite direction to the direction in which the tip vortex is winding up. Excuse me. So in that case, we see tremendous benefits, and we can see that my lift actually is enhanced significantly when I actually try to counter the tip vortex. So this also is actually kind of augmentation in the performance of the wing. This is my last slide. So, well, I mean, we do a lot of work at IIT Kanpur with rotors and so on. And in that process, we have developed now various tools which can be used to design propellers, rotor blades of any size or scale. Influence of variable RPM and pitch as control parameter must be explored some more before we can for sure say that, I mean, RPM is enough and I don't require variable pitch. I mean, I do a lot of work on VTOL, so I just have put one line about what, I mean, we have learned about VTOL systems. So typically, minus 30 to minus 35 degree negative twist rate is good for these VTOL propellers. It's a nice compromise for hovering flight also and forward flight also. And yeah, distributed propulsion has to be also explored, I mean, significantly, because it definitely promises to have some interesting impact on the overall performance. So that is all. Thank you very much.
Thank you. Yeah, that was an interesting presentation. If there are any questions for Professor Abhishek?
Very nice work. We compliment you.
I'm not able to hear, sir. You may have to come to some mic or something, sir.
Abhishek is an excellent work, and we appreciate that you have developed a design code for any type of propeller or any requirement. What I wanted to really just check with you all, you have done a lot of characterization. Has it been physically validated that whatever you wanted to achieve at different speeds or different operating conditions, whether it meets the requirement? I didn't get that feel whether you have really validated.
We have done, sir. We have validated actually, I mean, quite significantly. We don't publish any work without thorough validation. So everything we develop is all, I mean, point to point validated actually. So we do a lot of tests in our National Internal Facility at IIT Kanpur. So we have experimental data for both hovering propellers, rotors, as well as forward flight propellers, and we have done thorough validation.
Good.
Okay, thank you.
That's Abhishek.
Yes, sir.
You were just looking at the electric Hansan.
Right.
Where I thought the pitch mechanism is a little complicated.
Okay.
Can we get rid of the pitch but varying the RPM, because the torque for this class of motors can be constant.
Right, sir.
RPM. But can we get the kind of efficiency? We are not talking about 90% the torque.
No, sir. I mean, efficiency can be maintained. I mean, sir, efficiency can be easily maintained, but we have to see, we have to make sure that are we able to get enough thrust. So that is because the moment you drop your RPM, your thrust will also drop.
No, if I have the constant torque between fairly good range of RPM, that should be good enough to get me the power I'm looking for.
Right, sir. Power is fine, but I mean, the question is that how much inflow is going through the rotor and what is the inflow being induced by the rotor, sir. Okay. So, I mean, I have not looked at it, I mean, in detail enough, because only now I started thinking about it actually when I started preparing my presentation. So,
provide you some input, because you can just have a look at it and see whether
I'll do that, sir. Absolutely. Absolutely. I'll do that, sir. Thank you, sir. Yes, thank you so much.
Good afternoon, everyone. So basically, I'm the last talk of the day, so I'm standing between you and the exit. So I'll make it in 10 minutes. So the whole theme of this talk is I'll basically justify what Dr. Kota mentioned in the morning, that it is enough to have a low, say 1 megawatt motor and have multiple rotors and propellers and get aerodynamic benefit out of it. So the
summary of the presentation goes like this. We basically will show that you get a high L by D due to a high local dynamic head, and you get a delayed stall. Yeah, the flow itself, when laminar, will induce an early transition, and so there is no separation bubble. Though low Reynolds number is not really relevant in the context of either HANSA or the ERTA, and there is an interaction of the slipstreams. Now, whether it's beneficial or not is something which we really have to work on. And what happens to control surfaces and high lift devices? And finally, the current status of the CFD experiments. One question which we'll come back to at the very last slide is it important to consider aerodynamic configurations as part of the initial design process with the DEP? So now, basically, it has we already know that it has a lot of potential in the LEAP program for the leading edge asynchronous propeller technology, and this features multiple small propellers over that. Well, there have been aircraft designs with even a dozen of them, but we are not talking so many. We are just talking like 3 or 4 per wing. And this basically increases the local dynamic pressure over the wings. And near stall speed, you do not have the normal problems associated with low speed aerodynamics, which is there for every aircraft, say during takeoff. Now, again, all the propellers need not be running at all times, so you can have all of them on when you need both the lift and the thrust, and then some of them can be feathered where they can be feathered, and where they cannot, they can be aligned in such a manner so as to reduce drag. There are several benefits, including noise reduction, because we know noise also scales with the diameter. So automatically, when you have smaller propeller diameters, you also reduce the noise. You have better flight ranges because greater efficiency, and you have shorter takeoff and landing, so simply because you are getting high lift. We'll see in a moment how that is true. So now you can optimize this without the complexity of variable pitch, simply because you have individual control, and that's where the word asynchronous propeller comes from, because you can control each propeller individually depending upon your flight regime and what you hope to achieve. Which comes to the next point, that toggling the operation of individual propellers can give you control to match the characteristics that you want to the condition that you are flying in, which is not so in a conventional aircraft. And this also provides, why do they say redundant? Because in cruise, you do not have to keep all the propellers on all the time. So you have redundant propulsion, and at low speeds, you have much greater maneuvering capability because of your ability to individually control each propeller. So there are a number of variables which have to consider. So you can see on the right side this cartoon, which basically shows the propeller and the vortex sheet from the blades and slipstream tube. Professor Abhishek already mentioned a couple of them, including the sense of rotation of the propeller, the positioning of the propeller, the inclination of the propeller. Now, the sense of rotation will come to in a minute. I have a chart on that. The positioning, as he already mentioned, you have to keep it at a certain point from the wing leading edge to extract the maximum L by D, so you can optimize that location. The inclination of the propeller has been shown, especially when inclined down, to give you a greater lift over that area of the wing. Now, these become important as against conventional aircraft, because now you have so many of them covering the entire span of the wing. Whereas in a conventional aircraft, these things may not have mattered so much because you were affecting only a little bit of the wing. Then the wing geometry itself, because you are producing much higher lift, you can have, in principle, a lesser chord. So you are reducing weight. You are producing higher lift. You do not require your high mechanisms. You can do away with your double slotted flaps, slats and flaps and such. You can have a simpler mechanism. and the flaps themselves behave like blown flaps due to the slipstream effect, thereby enhancing the aerodynamic efficiency. And the propeller itself can be designed in such a manner, depending upon where in the span you are going to put it, to give you the optimal benefit. Because all the propellers may not be the same. Finally, this shows also that you have slipstream induced velocities over the wing. You have the wing itself behaves like a stator wing. It affects the swirl recovery. It also attenuates the tip vortex of the propeller, and there's basically the vortex cutting and bending due to its interaction with the wing, which is all part of the wing propeller interaction phenomenon which is going on. So I'll come back to this in a minute. I have a cleaner slide on this. So there have been several studies, including those on the Airbus 400M, which most of you are already familiar, wind tunnel studies as well as CFD studies, which have looked at the direction of the motion too. So these studies at UIUC, I think this is the study which Professor Abhishek also mentioned, have looked at multiple fans and the interaction with the multiple fans with different percentage throttles and how both the CL and CD of the wing behind it behave. And you can see you can, by a judicious combination, get much higher L by D by a distributed propulsion as opposed to a single propeller. This shows, for example, the effect of the propeller on the wing. And we know at low takeoff speeds, you can have a flow separation due to the low dynamic heads, but any separated bubble is eliminated due to the propeller-induced flow, as is seen in this oil flow vis. And this is not just for low Reynolds number flow, it is true for even normal aircraft, because at takeoff speeds, the speeds are pretty low. In fact, LeapTech did a full-scale test, and the height of the ring here was decided so as to keep it out of ground effect on, I think, the salt flats, wherein they showed clearly how, of course, they have like 8 or 10 propellers on each half span, which is maybe one too many, but they showed how it can benefit significantly. And the CFD showed that the reason why it was anyway, it was nothing to do with any ground effects. It was just to do with the propeller effects. Similar studies have been carried out on at Southampton on electric propulsion UAVs also, showing greater L by D as opposed to a normal configuration, conventional configuration. Now, this here is quite interesting. So you can see at the left, basically the tip vortex and the vorticity surfaces of isovorticity going over the wing. And one has to decide and optimize the spacing of the propellers, so that now is slipstream interaction a good thing or a bad thing? Secondly, what happens if a propeller is switched off in flight? What is the condition of the flow over the wing? Well, once you have switched off the propeller, these are all still open questions. One thing which is not in doubt is that a propeller at the tip, which was also mentioned in the previous one, so he made my job easy, is that it reduces the tip vortex, as shown in this this study, which I point you to the right, and you can see that this is the conventional configuration, the column on the left, wingtip mounted on the right, and you can see that the moment you have the propeller mounted a wingtip, the tip vortex is gone. It's totally mitigated. So many of the aircraft have the tip vortex propellers running and shut the others off when required. So there have also been a lot of CFD studies on the sense of rotation of the propeller. So you can have the inboard spinning counterclockwise, inboard spinning clockwise, outboard counterclockwise, and even combinations of the two. Now here it already shows that propeller spinning counterclockwise inboard will give you the best CL over that chord. And if you go further, you'll see if you are looking in combinations, you see that the best combination is achieved by the green line if you integrate the area under that. So you'll see that the inboard propeller should be counterclockwise and the outboard should be clockwise. So basically this combination. So we can see there's so much parameter space to work with in order to improve the aerodynamic performance of the wing with the distributed propulsion, which normally is not so much a field of study simply because we just have the one propeller which is put where structures allow that to be done. In fact, it has a significant effect even on the wing, a different angle of attack of the wing, and it shows that you can optimize it in such a manner that the takeoff conditions have the best performance. And these propellers can be shut off after that to restore the wing back to whatever cruise performance which you wanted to. So in summary, I'm done. This is the last slide. So while it's quite obvious no laminar flow is possible, the increased depth much greater than the increased drag will give much higher L by D. So the second is there is a lesser need for high lift devices. So you have lesser complexity, lesser weight. Third, it works as a high lift device majorly due to the increase in dynamic head, that's understood. And you can toggle individual propeller to match the flight conditions that you want. And you can have an optimal solution at cruise so that you can optimize for both the energy requirements as well as for drag requirements. So the lift coefficient of course improves if the diameter to chord increases. So this is a general guideline for propeller design, of course. And the effect of DEP on traditional aircraft, if you were to retrofit DEP on traditional aircraft, look at it through an MDO cycle because it seems to affect much more than just putting multiple sources of thrust on a wing. And the final thing is it does have a noise benefit, which is known. So if you're designing from scratch, is it important to consider aerodynamic configurations as part of the initial design? Absolutely, yes. But to answer the question or justify the statement that does having lower power motors and more number of propellers give a substantial improvement in L by D and efficiency? Answer is also yes. So thank you.
Sure, thank you very much. So any quick questions? It's a new area. Will be...
Quantify how much is the increase? I mean, it's improved, but there's a very qualitative.
Yes, yes. So basically, as you see, a lot of this is from published literature, which also is, hostage to the actual conditions which they have done. We have just now started on looking at this. So right now, I will not want to put a number based on other people's work.
One related question, right? That if you want to operate now at a cruise board, what kind of a distance between the two impellers you would like to have?
Okay, that's
your under control.
Yes.
That make this number 4 and number 3.
Yes, yes.
Which will aid each other in
Yes.
and therefore you can better perform.
There should also be borne in mind that the current DEP configurations often have counter-rotating pairs. So now if you are going to shut something off, any other effects of those should also be borne in mind. So my answer is I don't know yet. So what is this is like in twin engine fighter aircraft, there's always a sweet spot for jet spacing so that the jets do not interact with each other. For propellers, it's still an open question because at best, currently there are two props on a wing, and most of the time these are heavy lift aircraft, and these are the wings are huge, so the slipstreams don't interact. So if you are putting on a conventional, a small transport aircraft, then definitely there is going to be slipstream interaction, and some part of the flow will be over a control surface, an aileron, or maybe over a flap. So you want to decide, are you going to turn that off or not? Answer is no. There are too many variables to give a clean answer right now. Maybe it's a good thing because you can ask for funding for research.
Okay. If there are no more questions, thank you, Dr. Venkat. It was very interesting. So that brings us to a conclusion of this session, in which we had 3 very interesting papers on propellers. Pratap Naika emphasized the basic design and relevance to our current projects of ANSA and SARAS. And if we can indigenize those propellers, I think it's not a mean feat by any means. I think we should continue that work. The other 2 papers have given more new angles to the whole problem. One is the optimization of the propeller design by Professor Abhishek. That could result in some good outcome. And but again, it involves a very big design cycle, including fabrication and testing. So if we get some promising design, we can certainly take it further. And this matter of distributed propulsion it is quite new to me because I was always thinking that the wing must get as clean flow as possible. And that's why the pushers were preferred. But now it's been turned around to say, no, the disturbance caused by the propeller is actually helping the flow. Well, I think it needs a lot of investigation before we can close the chapter on that. But what worries me is the statement that if you're going to stop some of the propellers, they need to be in feathered condition. Otherwise, they'll be windmilling like anything. Or you have to have a brake, which is very complex. So I hate to see you have got 12 propellers with variable pitch, which makes life very complex. So, but this is a research problem, so I think we'll keep our mind open. So we have had a very interesting session. So I think with that, we'll close the session. Thank you.
Thank you. Now, under this committee, I thank the session chairman and all 3 speakers for enlightening us regarding various aspects of propellers. So thank you very much, sir. So now we have come to the end of day 1 proceeding. Before we close, those who are desired to visit our hangar, vehicle is arranged just opposite to this seminar hall. And it will take you to the hangar and drop you back to the Kodihalli reception, from where you can collect your mobile phone. Thank you very much. We will meet tomorrow at 9:30 a.m. sharply. Thank you all.